This works. It works. It's pointer. This is clicker and this is the yeah. Good morning to all of you.
Morning.
Yes, so there was a little technical hitch. Now we have overcome it. So we will be starting soon. Very good morning to all of you. Myself is Naveen Kumar. I work as a professor in Amrita School of Engineering and Execom of ComSoc. So what we have today, I think there are colleagues online as well in the BEVEX. So I would like to welcome all of you to this whole day very packed session, Bharat 6G Summit. So let us begin. In fact, the ComSoc will bring you very latest technology, and this has been one of the premier events that we used to do. If we recall, in 2014, we started 5G Summit and 5G workshop. Since then, we ensured that every year, at least twice 5G workshop happen. And that continued until last year. Last year, we started 6G, and from this year, it is official 6G Summit, which will continue at least every year once. So this is where all of you enjoy, and we bring the latest development, latest technology in front of you, the Communication Society IEEE Bangalore. This event is supported by Bangalore section, Signal Processing, Future Network. Dr. Asutosh is here today representing that, and 5G, 6G Innovation Testbed. And we have a sponsored, would like to thank everyone being here today. So I'm just going to, because already we are running short of. So I will introduce our chair, ComSoc Bangalore, Anindya Saha. So Anindya Saha is currently the chair of ComSoc Bangalore, and he is a CTO Sankhya Lab, now taken by Tejas Network. He has over 26 years of experience. He is an expert on SDR and has led the design and development of baseband and RF subsystem for Sankhya products in wireless communication. He holds 30 plus approved US and India patents on wireless radio, RF baseband, BLIW, CPU architecture, and SDR platform. He has authored several IEEE publications and contributed to these standards. He is a recipient of Hall of Fame Award from TSDSI in 22 for his contribution to broadband broadcast coverage work. He is a senior member IEEE and participate in standardization TSDSI, ORAN, and 3GPP activity. I would like to welcome and invite Nindya for introductory talk.
Hello, am I audible? Okay. So I have a little bit brief about what ComSoc Bangalore does, so I will not take too much time. So essentially, we are part of the worldwide IEEE Communication Society. We have a very strong Execom team, which comprises of industry and academia people. Very good diversity in terms of the mix. In terms of the number of members, right now we stand at 752. We have grown about 22% from what we were last year. And, we have a lot of achievements, Chapter of the Year Award in 2021. And then we had a hat trick of, accomplishments in terms of the Society Chapter Achievement Award in 2019, 2020, and 2021. So I just wanted to highlight that in terms of the kind of work which we are doing. This was basically the broad vision. So the reason I'm mentioning this is because, how did we start this conference? Why did we thought about it? Is mainly because this was one of the main goals when we started, set out to put our goals for this year. I think the first one where I had put a lot of focus is strengthening the student branches. So we have a lot of students who are joining online today. And of course, there are a lot of flagship programs that we have, and I'll come to that. Thematic activities, this is basically centered around 6G, which is one of the reasons why we are having this summit today. And of course, collaboration with other chapters and societies. So I thank Signal Processing Society, Future Networks Initiative, Dr. Ashutosh is here, and of course, IEEE Innovation 5G, 6G Testbed. So I think we are basically progressing on the lines that we had set out at the beginning of the year. We have also kind of aligned industry and academia work towards what are the INGR objectives. Um, so just a sneak peek, I think Dr. Naveen already spoke about this. So we have been doing a lot of 5G summit workshops and webinars, but now we are going to 6G, and today is kind of one of the highlights of one of the events that we are doing this year, starting with 6G. We have been doing some more activities like research methodology workshops, which is very well attended by mainly researchers as well as industry people. Then we have PhD edits and grade, which is basic grade 7, which is basically graduate congress. I think these are also very well attended. It is basically for evaluation of thesis for most of the PhD researchers and even masters program. So this is one of the very flagship events that ComSoc is very proud of, and it is really well attended and well participated. I think the good thing about this is we not only do it here in Bangalore section, but we also associate the other chapters in India, like the Kerala section, Hyderabad and Kolkata. And I want to thank Dr. Naveen because he has been championing this year over year. We had a very good turnout of excellent papers to last weekend in IEEE Connect. We had about 14 papers, and they were really well attended. Uh, and some of the other initiatives that we do, open source conference in partnership with Samsung. This year, the a lot of emerging trends on generative AI, IoT, digital transformation, blockchains. So all the important keywords. So this was very well attended. This happened just on 20th, 2 days back. Um, Protsahan, this is one of the important things that we do. This is basically recognizing the research publication. So in terms of research, we put a lot of emphasis on, the people who do the publication, and just to, felicitate them or encourage them. This is one of the important things. So I just want to highlight that. And I would say this is Ignite is one of the premier, I would say, internship programs that ComSoc runs, mainly to make sure a lot of students, in terms of the student branch and student chapters, they benefit from this. So this year we have about 40 plus groups, and there is a mentor and mentee assigned. So I just wanted to highlight the flagship things that IEEE ComSoc does. So if you look at the major events, we kind of divide it into student events, research focused events, and industry focused events. So I think today is a combination of, you can say, industry and academia, and that's why Bharat 6G Summit. I think I would just, before handing over, I would say the reason why we are doing this is kind of inspired by the Bharat 6G Vision program, which has been launched by the Honorable Prime Minister. And, I think if you look at the statement there, the vision statement to design, develop, and deploy 6G network technology. So I will not speak too much about it. I think we have a very esteemed lineup of speakers and distinguished guests who are going to speak on this. And I'm going to stop here because if I speak about this, that will become too much. And I'll just stop here and we'll go to the next event program. Thank you. And welcome everyone. And hope you take the fullest benefit of all the speakers. I think we have a very packed event today, but you should make use of the the breaks to network with the industry members so that you can benefit from this. Thank you. Thank you. Yeah, yeah. But you want to speak about?
Okay, thank you, Anindya, for introducing about ComSoc Bangalore. And I think a lot of work that goes on behind. And thank you to all Exicom and participants who appreciate and attend well these events. So next we start with the keynote, and I'm proud and I'm privileged to introduce Dr. Kumar V. Sivarajan. So he is a co-founder and CTO Tejas Network, and he has a lot of achievement to his credit. He has nearly 3 decades of experience in the field of telecommunication. He is a fellow of Indian National Academy of Engineering. In 2000, he received the Swarn Jayanti Fellowship from the Department of Science and Technology, Government of India, which is awarded to outstanding young scientist. He is IEEE fellow, and yeah, he has also received and selected for IEEE Charles Liggett Forensic Scholarship as an annual award given to only first year graduate student in electrical engineering studying in USA. So Kumar received the Distinguished Alumni Award of IIT Madras in 2013. So let us welcome Dr. Kumar for his speech.
Thank you. Am I audible through the microphone? I prefer to use this rather than not yet. Yes, through the mic. Okay, good. Okay, thank you. It's a real pleasure to be here. I don't have to stand in front of this, right? No. Okay, so good. Okay, it's a pleasure to be here. It's my alma mater. I used to teach here, and IISc is very nice. They can study you an alma mater if you are a faculty member. So we are on the threshold of launching 6G, and 6G got defined last month. Okay, so IMT 2030 got defined last month at ITU. So if you know the process, every 10 years we would have a new G. Okay, if you don't have a new G, people can't sell more phones, can't sell more equipment. So IMT 2010 was LTE of 4G, and 2020 was 5G, and there is 6G. Okay, so let's see first what 6G is supposed to be. Okay. Okay, this is the first slide is the market. Okay, so the market is important. The global market, sometimes it's helpful to know these numbers. So the global market is about $740 billion for 5G and 6G infrastructure. Okay, this doesn't include cell phones. And the Indian market, out of that, I don't have a number, but I think it's about 10%. Oh, sorry, yeah, it is there. So 70 billion is the Indian market. This is our 5-year market. This is not an annual market. So the good news here is that telecom infrastructure will be a growing market. So that means all of us ComSoc engineers have jobs for the next 10 years. Okay. And this 6G, which is also called IMT 2030, will play a key role in this telecom and economic growth. And for those of us in India, India will continue to be a significant market, about 10% of the world market. Okay. Now let's say what is 6G. 6G got defined last month at ITU, and this is what are the usage scenarios for 6G or IMT 2030. Okay. There's a chart like this defined every 10 years, and you'll see sometimes there is a carryover. If you fail an exam, you have to carry forward to the next semester. So that's really what happened here. A lot of these came from 5G because we couldn't pass the test. Okay. So the ones that got carried forward are low latency communication. We used to call it, if you are in this 5G seminar, URLLC, ultra reliable low latency communication. The reality is we could do anything about figuring out how to achieve it or what are the applications. So we just made it hyper reliable and low latency and kicked the can down the road for 6G. Okay. Massive communication used to be called MMTC, massive machine type communication, commonly known as IoT, and then we changed it so that nobody could recognize, and now it's called massive communication. Again, we couldn't do anything about it in 6G, in 5G, so it's for us to do something in 6G. Immersive communication, actually people in 5G talked about, wearing goggles, virtual reality, and all that, but it's 3 years into 5G, and we're still streaming only YouTube videos. So we have to figure out what to do in 6G. Okay. Three more things got added, and they're interesting. So one is AI. Now, after ChatGPT, if you don't add AI in whatever you're doing, it's like it won't go anywhere. Okay, so you have to figure out what AI is and what to do about it in 6G. There are a couple of things which are, I think, sensing. So what is this integrated sensing and communication? So you can find the location if you choose to share your location, and every app will force you to share your location. But what about location of things, buildings, cars, which don't share location with you, right? So the goal is that you'll be able to sense like a radar, and you want to integrate it in communication. Okay. But the bottom one, I think, is the most interesting from an India perspective. And this was very hard fought. So India had a team in ITU, Geneva, who spent 2 weeks last month. From Tejas also had Jishnu from my team there. And we fought very hard to get ubiquitous connectivity. It's part of our vision that we want everyone in India to have connectivity, high-speed connectivity. We got broadband through mobile. We're probably the only country which has mobile broadband, but no fixed broadband or broadband to the home. And that's barely enough. And we realized that during COVID, when kids can't study and so on. And you really need proper broadband. So we now want to have ubiquitous connectivity, and we think 6G will play a role, and we want that to be part of it. We tried a little bit in 5G. We said we want better coverage. 5G, it was a good, like a toehold to get some experience doing something worldwide. But I think here we want to drive this need for ubiquitous connectivity so the whole country is connected. And this struck a chord not only with India, but also with teams from many other countries who have the same kind of need. Okay. I have really elaborating on this, so I will zip through this and then tell you a few other things. Okay. So immersive communication is all the XR, virtual reality, artificial reality, mixed reality, whatever it is, where, basically it's like you're wearing goggles in a room. And what this has to do with mobile and 6G is a good question to ask. Okay. So it's probably that in this room, if instead of watching on video, you should be able to experience in 3D. So it's hardly defined. And it's for us, I think, not to get carried away by the hype and figure out what exactly we will do with this kind of technology. I think there are more examples I'll come to. Okay. Integrated sensing and communication. The broad goal here is that you will sense objects, moving objects, of course, buildings and so on, you could always sense. Maybe you will sense cars, drones. One of the other thing is that you'll be able to sense drones, things that don't share location with you. And knowing this environment turns out to be important for many applications. I mean, drone is what people have in mind, that you should be able to sense drones, and you can't have too many infra, right? So you have already a mobile tower infra which covers everything. So if you are going to have a sensing infrastructure, so you better reuse that and integrate sensing. I mean, this is a broad thinking. At this stage, it's so early that you just basically take these broad thoughts and put them in and hope that somebody will be able to do something to achieve it. And some of that is realized, some of that is not realized, as you can see from the 5G example. Okay. AI, again, let me tell you, the broad thinking is self-driving cars is sort of like a panacea, right? I mean, that's sort of a holy grail. So everybody wants a self-driving car. It's maybe easier in Bay Area, maybe harder in Bangalore, but you want a self-driving car. Now, if you have a self-driving car, you need a 6G network, because 5G tried to do it and couldn't. A 6G network to control the car, right? Now, of course, if you stay in the communications domain, that's not adequate, because to control this car, you will need artificial intelligence in some form. We haven't figured out what. So the goal is that your 6G base station will not only control the cars, help them drive themselves, but also have artificial intelligence, because we expect that something like that will be needed, right? And that's sort of the thinking here. I'll give you an example of an immersive city. So here is in Boston, they're trying to get a digital twin of Boston, okay, of the whole city. Now, what is this digital twin? So currently they have a wooden replica of Boston. You can actually go and see they have a replica of all the buildings in Boston. The wooden replica earlier started for some other purpose. There's a park in the center of Boston. And the rule in Boston is your building cannot obstruct the sunlight into the park in summer because people have to enjoy the sun. So that was the original thinking. And all the high-rise restrictions in Boston had to be modeled. So they put a wooden replica. So now, of course, we can do much more. Can create a digital twin of the city. A static one is not so interesting. Okay, because if you have a static representation, you really want to know if there's traffic, if there's cars, if new things come up. So you want a dynamic, up-to-date digital copy of Boston, right? Or Bangalore for that matter. And that's the digital twin concept. So you can do what if on that. You can have a real-time vision of that. So this is the digital twin. I couldn't quite understand what the digital twin is. And Jishnu, who makes all my slide, I asked him, like, give me a concrete example. And this is what he came up with. Now you can do simulations here. You can figure out traffic. Maybe if you had a Bangalore model like this, you can play around with changing things and see how the traffic would flow. But traffic is a big problem in Bangalore. That's the biggest problem. We all talk about if you're from outside of Bangalore. Ubiquitous connectivity. This is an India requirement. Okay, so we said we want finally to solve this problem of every citizen, every home having very good broadband connectivity wherever they are. Okay, so you and I think we have a lot of broadband connectivity, but that's because you're in Bangalore, Bombay, and so on, right? If you go to Chhattisgarh, you have nothing. And we want this in every part of the country and for every citizen. And 4G didn't quite solve the problem. And even if it did, it gives you very poor connectivity. So we want to do it in 6G. And 6G, we should also think not necessarily wireless. It is just the next generation of communication. And we should think, see, the wireless part of it is becoming less and less significant in a way, because the fiber or wire, fiber, tomorrow I'm going to talk on IIT Madras on fiber, is going a long way. So the wireless part is just the last 100, 200 meters. In fact, in millimeter wave, which was supposed to be the new band in 5G, it was 100 meters, okay? And if you do hundreds of gigahertz, which some speakers will talk about, because that's what you think is the next spectrum available, it'll be even shorter. So most of the network is really fiber. So you need to also think that fiber will be a big part of 6G, and that will be part of getting ubiquitous connectivity as well. But we want wireless because nobody likes to be attached to a wire, but that's getting increasingly shorter, right? So this is more or less how, let's say for ubiquitous connectivity, I think one of the key things is to sort of really get everywhere is to think that communication media or fiber should be like electricity wires, right? So you really need to exploit the electricity poles. And nobody has been able to do that for regulatory reasons or whatever. But if you could get fiber into your home, wherever into every home that had electricity, then ubiquitous connectivity would be more or less be a solved problem. I think that's one way to think. Then there are a lot of coverage issues with mobile signals today. You can't keep adding towers everywhere. You could add a tower at the lamppost, perhaps a small cell. So I think there's technology in 6G, I'm sure many other speakers will talk about, where you have these intelligent reflective surfaces that are passive in their operation. You may need to power it up to design how it reflects, but then that can solve a lot of the coverage gap. So these are some of the technologies, and I'm sure I don't want to dwell on it because I'm not the expert and there are many other speakers, to realize ubiquitous connectivity. Low latency, as I said, this is a carryover from 5G. We couldn't get any ultra low latency. And broadly, the thinking is for machinery, robots to be operated with 5G or 6G. Sorry, it's not 5G, it's 6G. And that the assumption is you need much lower latency because the latencies today of tens of milliseconds are designed for humans, right? Now, these applications are not here yet. They were supposed to be here already, but they're not here yet. So hopefully in 6G, we'll have them, and then we'll need to have a low way to communicate with low latency. One of the things that's also happening, and this will be relevant, I'll say more about it, is this merger of, let's say, Wi-Fi and 5G or 6G. Okay, so Wi-Fi tried for a long time to get into the carrier spaces, but was never successful. Now, sort of it's the 5G getting into the Wi-Fi space with private 5G. So that's coming up. And the argument there is reliability. You want to operate machinery, you really want reserved spectrum and low latency and everything. So it's a good, I think, say competition brewing up between the 3GPP way of doing things and the IEEE way of doing things. Okay. So all of this stuff is old. Okay. This is all there from 4G, 5G. We just carry it forward. We just keep increasing and are decreasing the latency, increasing the reliability, and so on. So it's just rehash because things have to get better. But really, the new capabilities we are looking for are here in blue. Okay. So coverage I talked about. So we have to figure out how everybody gets coverage. Okay. And I think that's important. We can't leave anybody behind. Sensing, again, we want to know where things are, especially things like drones or inanimate objects which don't have a communication capability, right? And we need to integrate that into the communication infrastructure. Yeah, I talked about self-driving cars need to be controlled with the 6G network. Sustainability, when 4G was being defined, the word green wasn't there. Okay. When 5G was defined, it was there, but nobody paid any attention. 5G is no more green, either in terms of the infra or in terms of the phone than 4G is. It consumes as much power. Anecdotally, I've heard it consumes more power because than a 4G phone. Okay. Interoperability is fine. Positioning. See, this is again an aspect that 5G couldn't really solve. Unless you are outside and have GPS and are willing to share your location, the network cannot locate you well. It cannot locate you in this room. It can just locate you somewhere, nearby in this campus. It cannot locate you in your apartment. So if you want positioning for people and for things, that is another area that has to be given a lot of attention in 6G. In terms of interoperability, the biggest thing is satellites, right? So we have now towers, and earlier people had sat phones with satellites, and we want to integrate the thing. So the holy grail here is the satellite is like a cell tower. If you're not near a tower, you should be able to communicate with the satellite. Apple made some foray into this, but that's cheating because all they did was at $1,500 you can do anything for the phone. So they put a sat phone into the cell phone. So you really have two phones. And then if you're outside, you can send a message to a satellite. But that's cheating. Okay. So we want in this phone, which costs $200, the ability to communicate with the satellite so that it's ubiquitous. That's one way or one step of this ubiquitous communication goal. Okay. I'll say this is my last slide, and then I have some concluding remarks. Okay. So, there are a bunch of us in India, companies, operators, academia, who have come together. This was last month. We formed a Bharat 6G Alliance. Okay. We want to do a better job of, driving 6G standards. So there are, of course, engineers and scientists here, but this alliance is meant to drive 6G requirements so that we have something that meets all our requirements and it's affordable, right? And this is not a standards body. We want to work with standards bodies like IEEE and 3GPP to drive the 6G standards. Okay. Now, this is my end of my slides, but let me tell you a few things which sort of came to my mind after I sent the slides to Anindya. Okay. I think we should face up to the fact that 5G is a failure. Okay. So 5G has not done anything in terms of improving communications beyond 4G. Okay. So 2G was very good. It brought reliable voice, digital voice. 3G brought us email, BlackBerry. Most of you are very young, but those of you who are old enough know that first time you got email on your mobile was with BlackBerry. 4G was a revolution. It's a misnomer to call it an evolution. 4G is called long-term evolution. But what evolution of what? Okay, I'll tell you it's evolution of what. It's not an evolution of 2G or 3G. Okay, and 4G revolutionized what we are doing. We got smartphones, we got video, it was IP and so on. LTE is really an evolution of WiMAX. Okay, and WiMAX was defined by IEEE. But somewhere, IEEE lost the political battle. I will conclude in 5 minutes. Okay. But remind me. So in 5G, there was no, so ITU, the way the standards work is ITU defines the requirements. So ITU defined the requirements for 4G, which was IMT 2010, right? And there were two radio interface technologies for IMT 2010. One is what you call LTE, the other was WiMAX. Actually, WiMAX was earlier, okay? And somehow business success eluded WiMAX to the point in 5G, there is only one writ for IMT 2020, which came from 3GPP. Since I'm talking in IEEE and IEEE ComSoc, I want you to rise up and do WiMAX 6G, okay, from IEEE, which defines brand new communication technology. So please cut the tether to 4G. We don't want, I mean, if OFDM is the best you can come up with, keep it, but think completely afresh, because that never happened in 5G. 5G was take this OFDM, 15 kilohertz of carrier spacing, okay, make it 30, 60, change the error correcting code, turbo code to LTPC, stick it in, give it a new name. I think we should change that, and I understand that 350 of you from ComSoc here. So please think afresh, come up with a brand new communications technology, define a writ for IMT 2030, make sure we really address at least 4 or 5 out of those 6 things, because we practically address nothing in 5G, nothing, because there's no URLLC, there was no massive IoT. We just did better broadband, and better why? Not from a communication technology, because you just got more spectrum. Okay, so if you have 100 megahertz instead of 20 megahertz, of course you expect to do 5 times better. There is no increase in spectral efficiency. So I think the challenge, that the vision I would like to set for ComSoc is develop a global standard, a writ for IMT 2030, which is way better than what we have for 4G, nothing to speak of 5G. Thank you.
Thank you for capability of 6G, and also highlighting the Indian perspective of ubiquitous connectivity in the standardization. Thank you very much. And also motivating us, IEEE, to go for WiMAX 6. Thank you very much. I would like to call Dr. Asutosh to hand over a appreciation token to Dr. Kumar. Thank you. Thank you. Speaker. Thank you. Thank you very much, Dr. Asutosh. And next we have Professor Chandramurthy. So Chandramurthy is a professor in Department of ECE here in IISc. And in past, he has worked on WCDMA baseband transceiver design 802.1b baseband receiver with Qualcomm in USA in 2006 and 7. And he is expert, I think, in WiMAX he has contributed to. So I hope the Dr. Kumar, what he mentioned, sir is going to follow that. And he is also IEEE fellow, elevated last year. And he has over 100 publications to his credit. And he has contributed, and he is organizing a lot of conferences, including SPCOM and ICAS, ISIIT, and IEEE SPAWC 2022. So I welcome Dr. Professor Murthy for the next keynote. Thank you, sir.
Yeah, thank you for the kind introduction, and it's a great pleasure to be here. Happy to see a lot of familiar faces and some new ones. So let me start right away. This is a talk on the perspectives of 6G communications. So this is the mandatory first slide. I think Kumar did a wonderful job of introducing this slide. As he said, 5G in many ways is a failure, and people sat down and said, why is it a failure? And then they realized it's 5G, but they made the capabilities a triangle. That won't work. So 6G, now we have a hexagon sitting around it. Okay, so that hopefully now we got it right and now things will work better. So, but on a more serious note, this is basically the three, as he mentioned, these three immersive communications, hyper reliable and low latency and massive communications are extensions of what 5G wanted to do, but maybe didn't achieve, only partially achieved. And in addition, there is integrated sensing and communications, integrated AI and communications, ubiquitous connectivity as three additional usage scenarios with the overarching goals, which is all around in this circle here, like a halo, of sustainability, connecting the unconnected, security, privacy, resilience, and ubiquitous intelligence. In terms of capabilities, you have all these 5G capabilities just further enhanced, starting from security, privacy, and resilience to peak data rate, all of them just extended versions or enhanced versions of 5G capabilities. But there are new capabilities, coverage, sensing related capabilities, AI, sustainability, interoperability, and positioning, which are introduced in for 6G. And as Kumar mentioned, basically in this, among these new capabilities, coverage, sustainability are actually two new capabilities that got introduced into IMT 2030, thanks to the very strong efforts of Jishnu and the team from Tejas and from many others. I was fortunate also to heavily contribute towards inclusion of these two keywords into the 6G capabilities. So let's actually give us a round of applause to Jishnu and the team from Tejas from pushing these into the standard. It's actually not an easy task to do. So the flavor of this talk is actually going to be very different from the rest of the talks you will see today. And what I'm going to do is to basically talk about a few technologies that I think that perhaps these will play a role in in 6G. And these are cell-free massive MIMO and channel estimation and tracking in massive and gigamassive MIMO systems, low resolution ADCs, energy efficient massive machine types communications, new waveforms, intelligent reflecting surfaces. And then there are many other topics that I don't have the time to talk about, but I'll just sort of indicate at least some of them to you. Okay, so we'll start with cell-free massive MIMO. And this is what I'm going to talk to you a little bit about is really the work of my student Anubhav Chaudhary, who's actually here. So what is cell-free? The idea is basically that when a user in the current cellular systems, a user basically starts by attaching itself to a base station. And all of its communications happen through this base station. In the cell-free concept, basically all the access points or base stations in the vicinity process the data to or from all the UEs. Another technology that's actually already there in 5G is something called dynamic time division duplex, in which each access point can independently choose to operate in the uplink or downlink mode in every slot. So for example, here there are 3 cells, and these 3 cells in each slot, they're choosing to operate in the uplink or downlink directions independently of each other. And so now if you see that if I combine these two ideas, that cell-free technology as well as dynamic TDD, what I can have is that if there are users, for example, this blue user who has uplink data requirement, then there are some base stations in the vicinity that are serving users in the uplink direction. The same slot, if there are different users that are demanding downlink data, then there are a complementary set of base stations that are serving users in the downlink direction. And therefore, in the same frequency band, collectively the users, all the users, whether they are demanding uplink or downlink, they can be served simultaneously. Of course, this brings in new sources of interferences, which are the interference from the downlink uplink user to the downlink user, and from the downlink base station to the uplink base stations, and so on. But these need to be handled appropriately. So with this, basically, if you consider these two technologies together, it can potentially function like a virtual full duplex system. So some questions that you can ask are, how does this system compare against a cellular technology, or even a cellular full duplex technology, or perhaps even a cell-free full duplex technology? And another thing that's also important in this context, and I'll come back to this point again and again, because wireless channels are inherently time varying. And it's important to be able to estimate and track these channels. And that is actually really crucial for the whole system to work. And so how do you design training sequences or pilot sequences for these kind of systems? And the twist here compared to a cellular system is that in a cellular system, only the base station that a user is attached to cares to estimate the wireless channel from the user to the base station. Whereas in a cell-free system, basically all the access points are required to estimate the channels from all the users. So it makes the problem considerably harder. So what we found is basically that this half duplex APs enabled cell-free communication with many distributed antennas and fewer antennas per AP is actually better than a full duplex massive MIMO cellular system and even a full duplex cell-free system. This thing about having many distributed APs with fewer antennas per AP is like cell densification. You reduce the cell sizes and the path loss actually decreases, and so you can actually achieve better performance. But in addition, if you can process the data jointly from among these APs and have the cell-free architecture, you can actually do much, much better. And overall, it can lead to much better rate regions. That the rate region basically tells you what are the joint rates that multiple users can achieve together. It has better resilience to interference, better 90th percentile rate, better fairness, and in particular, cell edge users' performance improves. And so you can have a much more uniform quality of service across the entire cell. And furthermore, these Z-off-2 sequence type of sequences, which are more generally called mutually unbiased orthogonal basis pilots, they can far outperform orthogonal pilot reuse or other types of pilots that you can use in these kind of systems. There are many plots here which basically illustrate this point numerically, but maybe we'll just focus on one plot here which plots the 90th percentile sum spectral efficiency. Think of it as the data rate as a function of the signal to noise ratio. What you see here is that this performance here, the lowest curve, which is the worst performing, is that of a cellular full duplex system, which has 16 access points over a given area, with each access point equipped with 8 transmit and 8 receive antennas. So this has a total of 16 times 16 or 256 transceiving antennas in over that area. In contrast, if I take this cell-free dynamic time division duplex system with 16 access points and only 8 antennas, so it has half the antenna density, that actually gives you this performance up here. So you can see that at least as the SNR increases, it can far outperform a cellular full duplex system. The next topic is massive MIMO channel estimation and tracking. The reason why we thought about this topic is basically because as you know, massive MIMO or increasing the number of antennas at the base station and possibly at the user side is actually one of the key technologies for 5G, as well as it's likely to be an important technology in 6G, very likely to be that. And the line of thought was as follows, that if you have any pair of antennas, there is a time varying channel in between them. And now if you have a massive number of antennas, you have a massive number of channels. And as you increase the number of antennas, because you need to keep the total radiated power fixed, the per antenna transmit power will reduce. On the other hand, because you have many more channel parameters to estimate, the number of training signals you need to use to estimate the channel will increase. So what the upshot of all of this is that you are going to have to track the channel much more frequently because there are so many more moving parts in the channel. And so at some point, the benefits of having a large number of antennas may break down. And so that's basically the line of thought and what we wanted to explore here. But to our surprise, what we found is that if you design the system well, you can actually continue to track such channels and estimate them and reap the benefits of massive MIMO systems in spite of the fact that your number of antennas is increasing as the number of antennas keep increasing. So, but in a sort of at a higher level, basically, when you look at massive MIMO, there are many challenges to make it work, including this aspect of channel aging, which basically refers to the fact that your channel estimates get outdated over time. And then there is also calibration imperfections, pilot contamination, intercarrier interference, intercell interference, and self-interference in the context of full duplex communications. So the overall goal could be to understand the effects of all these imperfections and develop techniques to mitigate them. So just one simple result to kind of illustrate the utility of being able to track these channels. What is plotted here is the mean squared error in channel estimation as a function of the sample index. So think of this as a front-loaded PDSCH or downlink data channel with the pilot signals at the start of a frame, and then you have the symbols in the frame following it. And the yellow curve corresponds to a very fast varying channel, the red for a moderate varying channel, and the blue for a slowly varying channel. And what you see is basically that as long as if you use some techniques like Kalman filtering to track the channel, you can actually achieve much lower mean squared error compared to using the channel estimate at the start of the frame and continuing to hold on to that. The next topic that I want to talk about is that of low resolution ADCs. Basically, if you have a very large number of antennas, and sitting behind every antenna is an RF chain and an analog to digital converter. And these ADCs are basically power hungry, and therefore, in order to, if you continue to use high resolution ADCs as you increase the size of your antenna system, you will have to consume a lot of power at the transmitter and receiver in order to have these large number of antennas. And this is one of the reasons perhaps why 5G is not as energy efficient as it ought to be. And one solution to this is to use low resolution analog to digital converters. For example, a 1-bit or a 2 or 3-bit ADC instead of a 12 or 14-bit ADC. It also reduces the data rate that is incoming into your baseband unit and therefore makes the processing much simpler. Now, what this kind of a low resolution ADC does is that it introduces a significant nonlinearity due to quantization in the time domain when the signal before the signal can enter the receiver front end or the baseband unit. And so you need to develop new algorithms for channel estimation and data detection. One other thing is when we started looking at this topic, what we found in the literature is that a lot of papers talk about the use of low resolution ADCs, but they focus on the problem of data detection. However, they assume that the receiver somehow has knowledge of the channel state information. But if you're using low resolution ADCs, not just your data signals, but also the training signals you're using to estimate the channel has to go through these low resolution ADCs. And therefore, this nonlinearity will affect your channel estimation capability. And so if you assume perfect channel state information at the receiver, then you may be significantly overestimating the performance that the system can offer. So what we did is to basically develop a suite of algorithms from the simplest case where you have unquantized observations and you have perfect channel state information at the receiver, all the way to the case where you have low resolution ADC observations and no channel state information at the receiver, which basically take the received samples and not only estimate the channel, but also perform soft symbol detection, because after the data detection step, you always have a channel decoding step, and the input to the channel decoder is these soft symbols or the bit log likelihood ratios. So it's not enough to detect the data symbols, for example, the QAM symbol or 16 QAM symbol, but you also have to calculate the bit log likelihood ratios. That's what is input to the channel decoder. And so there's a series of algorithms that we've developed, and these perform combined soft symbol detection and channel decoding. And you can even combine all of this with the channel decoding step, and we can extend these to MIMO OFDM systems. And one extra twist that comes when you look at OFDM systems is that in the time domain, you're passing the signal through this low resolution ADC nonlinearity, which can in turn destroy the the orthogonality of subcarriers. And that can affect how you can do the receiver processing. You need new techniques that do time domain channel estimation in this case. So to just give you one simple numerical example, here is the bit error rate in a coded system versus the signal to noise ratio. And this bunch of curves here correspond to the case where you assume that you have channel state information at the receiver. And you can see that these perform, so the lower the better, so these perform much better than these curves, which don't assume the knowledge of channel state information, which illustrates the point that if you assume perfect channel state information at the receiver, you may be significantly overestimating the actual performance the system can offer. Then this pair of curves here correspond to this variational Bayesian algorithm that we developed with quantized measurements and unquantized measurements. So these algorithms are pretty high performing. You have only about a half a dB loss of performance because you're using quantized measurements. And these are the conventional receivers when with under quantized and unquantized measurements. So overall, basically, there are better algorithms you can come up with which can handle the presence of a low resolution quantization and still achieve good performance. The next topic is on massive machine type communications. The idea here is that in IoT, you have a large number of devices that are basically sending sporadically sending short packets to the base station. In 5G, the goal was 10 power 6 devices per square kilometer. In 6G, this is being enhanced to 10 power 8 devices per square kilometer. The biggest challenge in this kind of systems is how to manage the multiple access when you have such a large number of devices that are occasionally sending a packet to the base station. And in this context, it's helpful to look at grant-free protocols, in particular distributed protocols, where there is low control overhead, so the users can decide autonomously when they will transmit to the base station. And non-orthogonal protocols, which don't require users to access resources in an orthogonal fashion, that is on separate time frequency resources, can be more spectrally efficient. So we have looked at some of these multiple access protocols that are appropriate for massive machine type communications. And one particular protocol that looks very promising is that of irregular repetition slotted aloha. This protocol works very much like slotted aloha, meaning that a user, when it has a packet to send, basically picks one slot at random and transmits its packet, except that you transmit multiple copies. In fact, you randomly select the number of copies, and then you randomly select some subset of slots and transmit copies of your packets in those slots. In this cartoon example here, you have 4 users and 3 slots. User 1 has chosen to transmit in slots 1 and 2. User 2 has chosen to transmit in slots 1 and 3, and so on. Now, for this to work, basically at the base station, what you do is you look at the signal you received across all of these slots, and you notice that in slot 3, there's only one packet that's transmitted. So you can decode that packet, and perhaps in the header of the packet, there's an indication of the other slot where the same packet was transmitted. And so you can actually go back, and in the slot 1, you can remove the interference caused by user 2 in slot 1. And this is called successive interference cancellation. And once you remove this interference, now you see that in slot 1, there's user 1 and 4, and in slot 2, there's users 1 and 3 that have transmitted. Now, suppose user 3 happens to be much closer to the base station than user 1, then possibly you can actually capture the packet of user 3 in slot 2, even though it is seeing interference from user 1. In that case, you can decode user 3 and then do an intra-slot interference cancellation, remove the interference from user 3, and then decode user 1 in slot 2. Then you can cancel interference here. Then in slot 1, only user 4 remains, and you've decoded all 4 users. So in this setup, in 3 slots, you've decoded 4 users. Even if you could perfectly coordinate transmissions, you would allot user 1 in slot 1, user 2 in slot 2, user 3 in slot 3, and you would transmit 3 packets in 3 slots, or that corresponds to a throughput of 1 packet per slot. So you can see that if you have potentially, if you can have packet captures and using such non-orthogonal, fully distributed random access protocol, you can even exceed 1 packet per slot in terms of your throughput. This is, of course, a cartoon example. One needs to examine in a practical system with various non-idealities that appear in a real system, whether such a thing is possible. So the challenges include how do you synchronize these devices so that they all have the same notion of the start of a slot. How do you detect which users are active and trying to transmit out of those 10 power 6 or 10 power 8 devices? In any given frame, only a very small subset of them would be trying to transmit. How would you estimate their channels? And related is how do you design training signals? How do you exploit multiple antennas at the base station, account for fading and path loss, and optimize these distributions from which these users are drawing when they are going to transmit? This is called repetition distribution. So related to this, you can do a variety of performance analysis, including the throughput, energy efficiency, fairness, and a new metric which is popular among some people these days called age of information. So what we've developed is basically user activity detection schemes and analyze the impact of channel estimation errors, accounting for user activity detection errors, multiple antennas, non-orthogonal training, fading, path loss, etc. And we've analyzed the throughput of such systems. And to basically summarize, what you can see here is what is shown as the throughput as a function of load. So the load is basically the number of users trying to transmit per slot, and the throughput is the number of users decoded per slot on average. And so what you can see basically is that you can actually achieve throughputs that are much better than 1 packet per slot, which is what you would achieve if you could simply perfectly coordinate transmissions and assign orthogonal resources to all the users. And you can actually do this in spite of different imperfections in, for example, the user activity detection, the having finite pilot length. So for example, it goes into more detail, but basically what I want to say is that if you have 10 power 6 or 10 power 8 devices, if you want to estimate the channel and you assign training sequences to these users, these training sequences, you would be repeating these training sequences heavily across all these users. And so there's a pilot contamination is bound to occur, and you need to be able to account for that. The main message is basically that if you design these systems well, you can actually get much better than 1 packet per slot of throughput, in spite of accounting for all the non-idealities that happen in real systems. The next topic is new waveforms. So as Kumar mentioned, again, OFDM has been the dominant waveform in both 4G and 5G. But since we're talking about 6G, we have an opportunity to revisit this and ask if there are better waveforms. Now, one waveform that has received a lot of attention in the literature is called OTFS, orthogonal time frequency space modulation. I won't talk about that here, except to maybe show you a little comparison. But what I want to talk about is maybe one specific use case, which is, let's say you're interested in providing broadband communications in rural settings. And because it's rural, you don't want to deploy a lot of base stations, so you will use lower center frequencies because signal propagates better. And so you use, let's say, a sub-gigahertz center frequency for wide coverage, but at the same time you want high bandwidth. Plus there are, let's say, high-speed trains or a highway going through these areas, and therefore you also have vehicles that are moving at high speeds. So in this case, if you want to provide coverage, rural broadband coverage, then one of the things that is actually a cornerstone for the design of wireless communication systems is the fact that you can approximate the effect of Doppler, which arises due to the relative movement of the transmitter and receiver, by a frequency shift. Now, this approximation is valid only if the bandwidth to center frequency ratio is much less than 1, and the velocity of the mobile is much less than the speed of light divided by 2 times the bandwidth, time bandwidth product of the signal or the waveform. Now, this assumption breaks down if you're looking at these kinds of applications. So in this case, basically you actually have to go back to basics and model the channel as a delay scale spread channel, where what you receive is multiple copies of the transmitted signal S of t, which are delayed by different amounts of time and time scaled by different time scaling factors and multiplied by the corresponding path coefficient. So this is the kind of channel that the receiver will have to contend with and recover what S of t is. And in this context, in these kinds of scenarios, what we can show is that waveforms like OFDM and OTFS actually fail. And so what we've done is to develop another waveform, which is called orthogonal delay scale space modulation, which uses the Mellin transform. So just like the Fourier transform, what it does is a delay in the time domain maps to a frequency shift in the frequency domain. Similarly, a property of the Mellin transform is that a time scaling in the time domain maps to a frequency shift in the Mellin domain. And so using properties of this Mellin transform, you can develop these waveforms. And what we show here is that the bit error rate versus the signal to noise ratio. And again, you can see that these ODSS waveforms actually perform much better than orthogonal time frequency space modulation as well as OFDM in these kinds of channels. What is not shown here is the performance in more benign channels. This is for a channel with 20 taps with a maximum delay spread of 10 milliseconds and a maximum scale spread of 1.001, some parameters here. But what is not shown here is the performance under more benign channels, in which case the answer is basically that all of these waveforms perform similarly in more benign channels. But when you encounter harsh channel conditions, then these waveforms can actually offer much better performance. The next topic is intelligent reflecting surfaces. Again, Kumar alluded to this. And the idea here is basically to use a reflective surface which has programmable reflection coefficients. And then you choose the reflection coefficients in the surface in such a way that the signals reflected off of each of these elements coherently add at the receiver. And so that leads to better SNR at the receiver, and therefore you have better performance. However, this is more or less a passive device. and it's only the reflection coefficients are being controlled by using some channel estimation technique. In order to control this passive device, what you need to do is basically to estimate the channel between the base station and the user through every single IRS element, compute the optimal reflection coefficients, and then feed that to this IRS surface so that it can actually coherently, it can reflect the signal so that it coherently adds up at the user's location. That is very challenging. So what we've done is to basically explore an alternative where instead of trying to program this IRS, what we'll do is to simply randomly configure the IRS in every slot. Now, if there are multiple users in the system, then if you've randomly configured the IRS in slot 1, maybe this theta 1, which is a random configuration of the reflection coefficients, is optimal for user 2. So in order to find out that it's user 2 for whom this is optimal, all you need to do is to send one short training signal from the base station. All the users estimate the signal to noise ratio at their respective locations. And you need to be able to identify that user 2 is seeing a good channel at the current configuration. And for that, you can use some very efficient feedback schemes. So for example, if I want to know, let's say, who's the richest among all of you, I don't have to poll every one of you to find out who has the most money. I can start by saying, who is there any crorepati in this room? And if only one person raises his hand, I found the richest person in the room already. If two people raise their hand, I can say, is there any double crorepati? And then if only one person raises, so I can, like this, I can sort of split the room very quickly and very efficiently identify that it is user 2 who needs to be served. And I can repeat this in every slot and therefore find the best user. And what we've shown is basically that this kind of randomly configuring the IRS can achieve performance which is close to the full beamforming based configuration of the IRS, as long as there are sufficiently many users in the system. And in fact, you don't really need that many users. So what is shown here is basically the blue curve here is the average throughput achieved by the beamforming solution, where you've optimally configured the IRS. And the red curve here shows the performance of the randomly configured IRS. And you can see that of the order of 10 users is enough to get almost all the benefits of having an IRS in the system. There are other topics such as joint communication and sensing and the upper mid-band 7 to 24 gigahertz communication. This is a very interesting, very challenging area, starting from channel modeling to how to achieve giga-MIMO. For example, it's not clear that when you use these kind of frequencies, typically you'll have to reduce your cell size. And in those lower cell sizes, what will be the rank of this channel? And if the rank is low, then you really can't achieve a lot of spatial multiplexing gain, nor can you achieve much of a diversity gain in these channels. So this band is likely to be very important for 6G, and there's a lot of work to be done. Quantum communications and learning, non-terrestrial networks, again, Kumar referred to the, alluded to this, and AI/ML, and as Kumar said, there's a lot of talk, a lot of papers, a lot of research around AI/ML, but in practice, for example, a network operator, okay, are they really using AI/ML? Where are they using it? Where is it most effective? These are very interesting questions to look at, and there are, of course, many more topics. So with this, I conclude my talk. Thank you very much for your time.
Thank you, sir. Thank you very much for highlighting and introducing about cell-free and many other topics. So thank you very much. I would like to invite Anindya to hand over token of appreciation to Professor Murthy.
Same protocol. Okay, let's take it. Yeah, that's okay. Yeah. Thank you very much. Yeah. Thank you.
So thank you very much. And I think we have a time, but we have to cut short for the tea break. just behind. You can go through this door also. So in maximum 20 minutes, we should come back. We are delayed. So please join for the tea. So now we arrange this properly.
How are you? चल रहा है ना थोड़ा लेट हो गया ना क्या है अभी
You know the place.
Sridhar was
Looking for a
got later acquired by Rakuten. Sridhar has been involved in discussing commercial deployment requirements of Open RAN with multiple operators and has been involved in end-to-end system engineering efforts of providing solutions, stitching together various pieces of Open RAN puzzle. He is involved in 3GPP standardization, especially 5G core network standards. I would like to invite Sridhar to take his session forward. Over to you.
Thank you. Am I audible? Okay. So this is a slightly different session from the set of sessions you had earlier. I am not a researcher. I am a practitioner. So what I'm going to present is based on the learnings we have had deploying commercial Open RAN networks for 5G. We have a large-scale network deployed in Japan, and we are in the process of deploying in Europe and North America as well. So yeah, so this is broadly the agenda for the presentation. I'll walk you through some of the key learnings from the front-haul integration of integrating a software-based baseband with a radio unit which is compliant to ORAN specifications, front-haul specification. I'll cover what learnings we had with respect to the control user plane and the timing and synchronization plane, the management plane, and application integration. So this is again a big topic in Open RAN, where it allows you to develop third-party applications to control and steer the RAN as per the intelligence gathered from across the network. Then I'll walk you through taking this as the consideration, how we can look at different lower layer split options for 6G if we assume that terahertz frequency is going to be one of the candidate bands and spectrum for 6G, and then part to 6G standardization, right? So what the operators are expecting when we go and deploy Open RAN solution. So operators in the past have been accustomed to getting RAN gears from big vendors like Huawei, Nokia's, and Ericsson's for several decades now. And they have this inherent expectation that as soon as you get an Open RAN product, all the incumbent solutions that were working earlier has to work flawlessly, right? Now, what we get from standards, there is no agreed baseline of minimal viable set of commercial features, right? So 3GPP specifies n number of features. It is practically not feasible for every vendor to have all the features developed. And there is no MVP captured. Even though ORAN works on MVP group, they are primarily targeting the minimum viable product only for the ORAN specified features. Leaving the set of features that are defined in 3GPP, it is not clear what among them has to be prioritized by vendors, right? And then in many of the networks, multi-band, multi-frequency layer is a given, right? You have your solution has to work in a multi-frequency layer, and you have to have solutions to handle radios from different vendors. So some vendors might be specializing in the low band, some vendors might be specializing in TDD band, some vendors might be specializing with massive MIMO radios. So a single baseband has to interoperate with multiple different vendors specializing in different radio categories, right? And then there, when we get into integration, the IoT profile and how we face issues in interoperability based on the differences in the way they implement the frontal becomes a big bottleneck. When you have multi-frequency layers, support for NCC carrier aggregation is again a given. Every operator expects this, right? And here also the baseband capability as well as the radio capabilities in an Open RAN network are expected to come from different vendors. For example, one vendor might be specializing in TDD baseband and the TDD radios, while another vendor might be specializing in FDDs. So typically FDD bands are the low bands which give you the coverage, while the TDD and the CBRS 3.5 gigahertz bands are the one which give you the capacity. Now, if you have to have carrier aggregation working between these two basebands, you need to open out the interface between the two basebands. That is never standardized. So even though the work for this has recently started in ORAN, it's still a long way to go. Energy savings. So Dr. Kumar talked about it in the beginning. So 6G energy savings and sustainability is one of the big talks. Operators are already expecting it now. In Europe, there is a big crunch for energy, and every operator in Europe is expecting energy savings as a given. But here too, work is happening in silos. If you see what 3GPP or ORAN is discussing, they are primarily targeting how do you conserve energy from a baseband perspective, or from a server utilization perspective, or from the frequency utilization perspective. When can you turn off the power amplifiers? When can you turn off slots? So that is the kind of discussion we are having. And then everybody is expecting some AI ML intelligence at the top is going to aid you in taking those decisions. But nobody talks about what is the energy consumed for that AI ML training. That is completely left out. We don't have a comprehensive framework to study how the overall energy utilization is in a network. And when you go to this intelligent solutions, what is the benefit that you are getting, end-to-end benefit, right? So that has to be considered when we go into 6G study, right? Network sharing, it was left out from an open RAN perspective for a long time. Recently, the shared ORU work item completed. Now it is in a stable state. There are umpteen variations in terms of transport network configurations. There's no standardized topology. So you go to different operators, they expect different transport configurations. Zero trust security, it came in late as a realization in ORAN. Work is ongoing. Things like narrowband IoT and LTEM, right? There was an expectation when ORAN was formed that there's nothing to be done on the radio side. Based on the frontal defined, it will seamlessly interoperate. There was a late realization that NB-IoT doesn't work as expected. So there is an ongoing work item. People left out LTEM. Same expectation was there that LTEM will work out of the box. We started actually integrating with a couple of radio vendors for LTEM. There are tons of issues to be considered there, right? Very simple case. In a given slot, if the PRACH occasion for a normal LT user and LTEM user collide, how do you tell the radio unit that in this position of the frequency grid, your LTEM PRACH is going to come, and in this position, LTE PRACH is going to come? And if there is a difference in the preamble formats of these two, how you are going to handle? So there are ways to do it, but no radio vendor has thought about it. So when you go into these details, there is always a constant push and pull between the baseband vendor and the radio vendor. So bottom line, when we go to Open RAN 6G standardization, we have to consider what is the end goal we are targeting, right? Is vendor diversification the target, or is everybody looking to just push their IPRs? Currently, what is happening is everybody tries to push their IPR. Nobody really thinks about the real end goal, vendor diversification. Then how are we going to make RAN easy to deploy, considering the aging telecom workforce? This is something that we have to deal with in reality. The telecommunication workforce across operators is aging. The new entrants fresh out of college are going into the other domains, right? So we have to make the deployment easy to build. So automation has to be first candidate. So learning from Open RAN, so from control and user plane perspective on the frontal, the first thing is ORAN defines these IoT profiles. So I'll talk about what is the importance of this IoT profile in the next slide. So what they say is there is a specific transmit window and there's a specific receive window, transmit window from the DU side and the receive window from the radio unit side, and it is very tightly timed. So people expect that if you take that IoT profile and interoperate, it will work in a commercial network. It doesn't. I'll show you why. I'll show with a real calculation why it doesn't work, right? And you have to practically consider what is applicable as a delay parameter for a given deployment. Then only things will work. Then in the frontal, they define something called different sections in the control plane. Even though ORAN allows you to have multiple sections used in the slot by slot, not many radio vendors support this. And there are specific requirements like LTM, which I talked about, which demands this type of use case. And then there is a specific digital scale calculation mentioned in the ORAN specification. Right? I'll walk you through that, how that is calculated, and no RU vendor is complying to this 0 dBFS. Some vendors comply, but some vendors expect an offset from the 0 dBFS. So when you have to take these into consideration, you have to carefully calculate how your output radiated power is going to be, right? If you assume that the RU vendor is 0 dBFS and you start sending your IQ samples with a specific digital scale, your expected output radiated power might be exceeding the norms or it might be under the norms. So both are problems, right? You have to very carefully work through that. Okay, just an example of how this works, right? So between the DU and RU, we have this strict timing window. The space between the two green lines is the receive window for a radio unit. So every slot, symbol by symbol, the radio unit receives the IQ samples, right? So the time window that the radio unit has to receive the IQ samples for a given symbol is this space between these two green lines, right? And the time window the ODU has to transmit those symbols is the space between the first two red lines. So ODU has to start transmitting ahead of the starting boundary for the ORU, and it has to consider that the minimum delay that will be expected on the frontal, and so considering that, it has to start T12 minimum time ahead to send the IQ samples, and then the last instant it can transmit is this middle red line. So this is the window that ODU has. What ORAN defines as a IoT standard is this ODU transmit window. If you take 30 kilohertz subcarrier spacing for TDD NR bands, it is 51 microseconds, right? So they have taken that number 51 microsecond as a slightly longer number as one symbol duration. One symbol duration is around 32 microseconds. So they have taken that 36 microseconds. So they have taken that number and they have specified 51. But is 51 really enough for RU to transmit the symbols for a carrier, right? So we look at the calculation. What ORAN considers is a single RU, single DU interoperability. So they think that if you interoperate a DU with an RU, you can take it for commercialization. It doesn't work. In a commercial network, a single site has 3 bands, right? I mean, three sectors. So each sector, if you consider 100 megahertz, so I've taken total bandwidth as 300 megahertz. So subcarrier spacing, 30 kilohertz subcarrier spacing. Total number of PRBs, 273 into 3, 819. And if I consider totally 8 layers transmitted across, right? The IQ bits that I will be transmitting in one symbol duration will be that much, considering 10% overhead, right? Now do a calculation of that, whether you can transmit that many bits in the line. So if you take the time taken to transmit one bit on a 25 Gbps link is this much, right? 0.0004 microsecond. Now if you add Ethernet overhead of 66/64 encoding to that many bits, you have to transmit those many bits. The time taken to transmit that is 66.59, whereas ORAN defines 51 microsecond. It doesn't work at all. So you need to tailor the DU transmit window and the RU receive window as per the deployment consideration. One operator might be pooling 3 carriers to one baseband. Another operator might be asking pool 6 carriers to one baseband. So depending on that, you need to tune it, right? The other is this digital scale adaptation. With 9-bit block floating point compression, ORAN specifies that the maximum I value and Q value that you can represent is 2 power 23, while where 8-bit range is given. If you take 2's complement representation, 8-bit range is given for the mantissa part, and a 4-bit exponent. With 4-bit exponent, you can represent up to 15 values. So if you take the max I value as 2 power 23, in power scale you square it, it becomes 2 power 46, and the minimum interface resolution is the log scale of this, which is minus 138.47 dBFS, right? So what ORAN expects is the maximum representable value with a 9-bit block floating point compression has to be considered as 0 dBFS. Or if you are using 14-bit block floating point compression, the maximum representable value is considered as 0 dBFS. And whatever the minimum will be the lowest from that. So my 138.47 dBFS below that is negative. So considering that, ORAN gives you this formula for your output RF power calculation. So there is a gain setting in the radio. There is an input IQ power which is expected to be 0 dBFS scale. And then later they introduce this reference level offset. What this reference level offset means is they realize that not every radio vendor is actually operating at 0 dBFS level. They have a scaled down version, right? So that they want to add. So this came in later, version 4.0 and later of the specification. Not many RU vendors support this, right? So when a baseband has to work with 2-3 different RU vendors, one supporting this reference level, another not supporting it, your RF power calculation has to be very careful. Otherwise, your overall radiated power will exceed the norms. Learning from management plane, there are tons of capabilities exposed in the ORAN management plane through the Yang schema. Not all of them support all the capabilities. very basic thing, IETF RFC 6022, which talks about getting the complete schema dump. There is a get schema mechanism defined in this RFC. That itself many RU vendors don't support. ORAN realized this and they made it mandatory for RU vendors to support from release 9 onwards, version 9 onwards. But still, commercially, if you see the RU vendors, many RU vendors don't support get schema. So if you don't support get schema, the only way the baseband vendor has to know what version of the schema the RU vendor supports is by pre-handshaking with the RU vendor and then putting it somewhere in your profile or hard code it that this RU vendor works with this kind of profile. It doesn't scale if you build a baseband like that. Then if you look at the O1 interface, which was supposed, everybody calls O1 is standardized, but the reality is this, right? The CU and DU Yang models as defined by 3GPP in 2854 specification are very basic. Even things like MIB-SIB configurations are missing in that, right? For operating a network, these basic configurations are a must. ORAN added these MIB-SIB configuration and some additional bare minimal configuration required to bring a network up, but they are missing many of these configurations which practical networks require, right? If you deploy a network, they want different cell selection policies, cell reselection policies, anchoring bands in multi-band networks, large number of transport network configurations, measurement configuration policies. None of this is defined by standard. Everybody has to be do it on their own. And talking with all these vendor-specific implementations, right? Talking about O1 interoperability is a joke. Coming to management plane, one more aspect I want to touch upon on the fronthaul configuration. So this is the schema that ORAN specifies for configuring the radio with different carriers. The right hand side is the read-only part, reading the capabilities of the radio, while the left hand side is the configurable part. So the point I want to touch upon is you have these cardinalities, right? N number of links mapped to a carrier, N number of links mapped to a processing element. What this N differs from vendor to vendor, right? There's no standard configuration. So you interoperate with multiple vendors, you have to deal with different ways of configuring this block in the radio. Learnings from the synchronization plane, timing. Again, vendors have to ensure that the radio vendors measure the time error limits as per the ITU limits specified in G8275.1. The compliance to many of the time error limits, it will vary from vendor to vendor. Then there are a number of configurations provided in ITU spec itself. Not all these configurations are actually taken in the ORAN sync Yang model. Only very subset of that is taken. But in a practical network, you may need to experiment with changing many of these configurations because of the transport topology variance, right? So the timing is tightly coupled with how you engineer and architect your transport network. Frequency holding performance should be complied. From a DU perspective, the incumbent baseband vendors who are not ORAN compliant, they usually have the timing grandmaster or the boundary clock in the baseband itself, and from that they drive the radio. But whereas in ORAN type of system where the baseband is expected to be running on a CARTS hardware, we don't have this capability. So we had to struggle a lot getting this capability. So I'll touch upon this part and then I'll just directly go to 6G for maybe last 5 minutes. Again, there was expectation that with RIC and application integration, we get a very intelligent network. I'll give you an analogy. I don't want to go into these problems. I have detailed those problems in this link. So if you consider Lego, right, they give you building blocks with buttons at the top. So you can stack layers of Lego by putting blocks one over the other. So that is a typical 3GPP vertical interfacing. You have the layer 1, you have the MAC, you have the RLC, you have RRC. It is stacked one over the other. You have F1 interface, everything. What ORAN wanted to do with the E2 interface is to have a split like this and expected application to plug in from the sides. If you go and talk to Lego, they don't have the side buttons. So how do you get this, right? You have to cut it open and then pull it out and then insert. That's how the E2 interface is currently defined. And with that, it is not at all debuggable. Every message and every IE that is defined in 3GPP is transposed as a octet string in the E2SMs. You take Wireshark trace of it, you don't understand what is going on over the wire. It is such a non-debuggable interface. So what it is forcing vendors to do is implement their own E2SMs, which is then again killing interoperability. It becomes custom. So path to 6G, if you consider terahertz frequency as one of the candidate bands, you will also require anchor bands in the FR1 and FR2 ranges. So which means for terahertz frequency, the 7.2 split may not work. We may have to consider option 6 kind of deployment. So today, even for FR2 millimeter wave, option 2 split is more common. There too, again, if you take the small cell forum specification that was designed for a single cell interoperability. If you want to have multi-cell interoperability, you need to tweak with the timing, the slot indication timings, and the buffering capabilities in the L1. I don't have time to go into details of this, but I can talk about it offline if you have. Again, you cannot afford to miss the carrier aggregation DC considerations. If you consider that the FR1 DU and the terahertz DU are coming from different vendors, then this inter-vendor interface, that blue line that I have shown, is important. So you need to think about standardizing it from day one. Key questions to consider before we go for 6G Open RAN standardization. Extreme flexibility is fine. 5G started with flexibility for everything, right? Lean physical layer. You have lean frame structure, very extendable physical layer design. But that also brought in an unrealistic expectation that everything is available day one. It is not going to happen. That's why we don't see things like URLLC or massive IoT not yet commercially deployed. On top of it, people already talk about this multicast broadcast, which has been legacy carry forward from 3G days. Still, we haven't seen any commercial implementation of this in a cellular network, even though this ATC kind of networks have deployed multicast. But it's just waste of time discussing this in standards when you are clear that it is not going to be deployed. Time sensitive networking. I already talked about issues of ensuring time synchronization and making sure that error boundaries are kept even on a wired network. Now, what expectations we have on having PTP type of time distributed over wireless link, right? So considering all this, we should first aim for a simpler and practically deployable set of features, start from that, and then go for other things, right? If we start pushing IPRs everywhere, then things will never be deployable. So yeah, part to 6G, start with standardized profiling of commercial deployment use cases. And we need to profile commercially deployable topologies and topologies of the transport network. And from that, have a minimal viable set of what is required. Then we have to start thinking about network automation as the first candidate, right? Today, 3GPP never thinks about it. They start adding it after, say, release 16, release 17, some parts of it. But there is no standardized way for doing end-to-end automation of the network. This has to be thought through in 6G. For the reason that the telecom workforce is aging, right? So then define interfaces to meet the use cases and end state goal. So I gave that Lego example. If you want to have the sideways interface, build the interface in 3GPP itself or whichever standard body that is defining the next technology. In there itself, you need to have the sideways interface layer by layer. You can't offload it to some other SDOs and then pull it out and then do. Then the work that happened in E2 is what is going to happen. Yeah, so that's what I covered here. Yeah, that's the last slide. Thank you.
Thank you, Sridhar. Thank you for highlighting this ORAN and challenges behind this ORAN. I request Subhas to hand over the token of appreciation to Sridhar. Once again, please give a big clap to our sponsor, Tejas Network and AMD. Thank you very much for supporting us. Next, we have Ashok Kumar Reddy. So our next speaker is going to talk about AI, ML, and so on. So Ashok Kumar is currently Director of Engineering at Samsung Research. In past, he worked with Weekend Communication, which became part of Broadcom. He was involved in physical layer algorithm, WiMAX, and LTE. And Since 2013, he is with Samsung. So I will not speak much more. It is highlighted. Over to you, Ashok.
Check this. Hello, can you hear me?
Request the speaker to kindly respect the time also. Thank you.
Sure. Thank you. So I had to now try to manage the time because the previous speaker got to move it. The talk is very clear, AI ML for 6G. And I'll briefly cover what we're doing here. To start with, actually, I would like to quickly show you a picture from our recent white paper, a Samsung research white paper, where we try to show how a communication system can use AI in its own components. So here we have shown there are 3 levels of usability. One, when local AI, where you try to use AI within a block with no interdependency with other components in the network. A joint AI is where you try to involve 2 entities in the network and try to use AI across them, or 1 or 2 distributed AI kind of. End-to-end AI is something I don't have exact example right now, but those 2 examples I'll be covering more and more detail in the upcoming slides, what exactly some of the research that we have done in the recent times. So local AI is more like a involving block, and joint involves a procedure because it involves 2 entities there. Okay. So in this talk, I have few examples where we have tried to apply this kind of AI in simple AI physical layer blocks and in procedure level. I'll give you those examples, and that's kind of possibly a starting step for seeing what can be the candidate for 6G. Okay. So let me start with few results and quickly summarize. I'll quickly summarize. It should be seen as what are the possible applications, which of them can really be realized is what is up to you to decide. So I'll give you an example wherever it is relevant and how efficient they are. Okay. So channel estimation is one of the critical blocks in any system that you talk in wireless communications. So we tried replacing one of the channel estimation blocks using AI, especially the DNN networks. Here, we tried to compete with well-known MMSC algorithm with a lot of knowledge. So we understood that at the end of the simulation, MMSC is very good when it has statistics available to it ready-made. But most of the times, channel statistics change over the time; they are not fixed. So in those conditions, LMMSC tend to misbehave and also underperform. So what we have shown using this work is that we can actually outperform over MMSC in the conditions where we don't have perfect knowledge about the channel at any given time. And also we try to show that using the perfect understanding of how the channel manifests in time and frequency, using those properties, we reduce the complexity of the known channel estimation blocks by factor of 1000. That's a part of this work. It's actually kind of a driving way to see how to replace them and make it more robust in the time. Okay, so it's for hopefully future implementations can consider this kind of approximations or robust channel estimation methods. So beam management is one of the blocks that you may see wherever AML for communication comes in. You see beam management is one of the examples there. So we tried this work quite early in time, to 2019, 2020 times. We tried to implement a system where we can how to select a beams for measurements, how to select a beam for data based on the measurements till that point of time. Okay, so using the past measurements, how do we predict for future? Here we try to do that. We have shown here we also used sensors and a device to aid the selections. It turns out that we can outperform the conventional methods by up to 40% in throughput, that we have shown through examples and simulations as well in this work. So in the CSI space, this is actually one of my favorite use cases. Is we tend to believe that channel we actually know that channel changes over the time and channel statistics change over time. Here, what we try to do is we try to predict the channel into the future and see by reporting it if there is any gain in the system. So we have done 2 levels of abstraction here. One trying to predict the channel itself, and other one trying to predict the capacity of the channel. We have shown up to 20% gains, 10 to 20% gains in real networks as well. Part of the solution is kind of deployed in real networks as well. So other important thing, which is very, very critical for most of the wireless researchers, is the channel model. How accurate is channel model for you when you try to use that for your evaluations? In that sense,
as we found that the models that we have in real systems are not so accurate, they don't really represent the realistic channels that you see in the field, we try to model such realistic channels in the simulator so that we can use them to build better systems. That was the intention in trying to use a generative adversarial network-based channel model. Using this, we were able to accurately model the field kind of channels in simulator. That was the intention. There are a lot more extensions possible in this space. It's may not directly go into any of the products, but actually decides what kind of algorithms need to be designed in advance. Okay? That's another critical work that actually fills in one of the puzzle slots for the 6G. So in the decoder space, we didn't try to replace decoder because it's well tuned. What we tried is to fine tune the decoder iterations using AI. We have shown significant gains there as well. If you see any of these implementations of the receiver or transmitter, one of the biggest problem is the RF components and their nonlinearity. Here we try to replace one of the conventional DPD blocks with the AI DPD. We have shown that it is one of the important areas to consider. Wherever there is nonlinearity, it's good to really sometimes apply these AML methods to find out the best possible replacement algorithm for conventional ones. We have shown with no significant change in the complexity, we can gain in the performance metrics corresponding to DPD. So that and handover prediction is one of our first works in 2017 times. This is algorithm. It's once again the prediction time. So most of the times when a call drops, you see here the network is not implemented properly, a kind of assumption we get to see. But many times it actually is possible, up to 1 to 5% possibility of a handoff failure, link failure. So what we try to do here is predict the failure, upcoming failure in advance, and try to see if we can mitigate it. So with that, this algorithm, we were able to predict the future failure in advance by 100 to 200 milliseconds, which help us make difference between a success and a failure. So this is another thing. And this is pilot patterns, as we understood in previous talks. The pilot pattern plays a very important role. Here we show that at a given performance, actually we can reduce the number of pilots that you need to send up to 50% using this selector layer algorithms that we have devised. So this is the summary of selected works that we have recently published and worked. And this just to show a glimpse of what kind of applications are possible at physical layer. It's not to show these are going to be preempted, but I'll show in the future slides how things are going in 3GPP and what will be there for 6G kind of a view as well. So before I go there, one of the important applications that all of us would need to really pay attention is the integrated sensing and communication and application of AI in this space. And this is one of the works which we did in 2022 as part of IDU challenge. Here we try to predict the depth map of a room given the channel impulse responses of a MIMO system. So this work, actually this was a challenge by NIST, National Institute of Standards and Technology USA. Ours is a winning solution for that. This is the solution I'm showing here. Just a quick result, not really too detailed. The input was a MIMO channel impulse response available, and you have to really give me a room, how the room is spaced. This is one of the important use cases of 6G as we believe. And LiDAR equivalent kind of output is what is expected. So what we try to build is a machine learning model, and then from there to voxel. One of the critical point we observed was pre-processing the data was essential to make ML easily understand what we intend to really do out of it. At the end of it, we actually were able to generate the depth map of a room. I'll show you some examples of LiDAR here. In this side being LiDAR output, which is actually very accurate. It uses a lot of advanced techniques there. The predicted output of out of the channel impulse response that we had is what it is. So this actually is very, very close to what we intend to see here. See, observe this and this. You see that it's very close. And this, I believe, I really couldn't find any existing conventional method to do this kind of a job. I felt this is one of the spaces where 6G can use machine learning as well. Just to, before I go to final next steps, so 3GPP right now has spent some time on evaluating and using AI for air interface. So in that, there are 3 RAN groups and various activities. So I'd like to cover the main use cases they tried in release 18 times is concluding now. CSI, beam management, and positioning. And exactly the use cases that I covered and worked previously is what actually is covered. We contributed to both CSI and beam management and towards 3GPP in last 1.5 years. So I would like to give you a quick overview of what are the upcoming AI additional use cases. This is a consensus or kind of understanding across multiple companies. Right now, people believe that we should actually try using AI for resource management, communication sensing, and channel estimation and nonlinearity correction. So I have shown you kind of a glimpse of how they would look like based on my previous work. All of them actually match very closely with the use cases I have shown already. Okay. So this is a slide I would like to spend some time on. Here, I have tried to visualize how AI-based or AI-influenced system would look like. We hear a lot about AI native, end-to-end AI kind of stuff. So I was trying to think about what can be a practical AI native system, or what can be end-to-end AI kind of a system. So this is the visualization of that. Just for you to explain, I'll just run you through. So this side is a conventional system transmitting, starting from a transport protocol, the transmitter ending at RF antenna, and the receiver going taking the RF to transport protocols. Each of the layer has its own specific functions. If you see, there are exchanging data. They actually have a lot of control functions, data transmissions, and nonlinearities. All of them are handled in conventional methods right now. So if you were to be, if you were to use AI-based mechanisms here, what all can really be replaced? To visualize that, I really didn't want to change the functionality place. The actually functionality of this continues to stay there. There is no real requirement to have that exactly at same place. But I try to keep them for our understanding here for discussion. If you see the application, the functionality remains same as these places. So let me start from here, how AI can influence. So AI can influence on baseband learning based transmit scheme selection. It could actually be a waveform or the MCS scheme that you would like to transmit. The nonlinearities are like PA nonlinearities that actually can have significant impact that we have shown in a working model for that. Similarly, at the receiver, AI based baseband, AI influence baseband is very, very possible, given that each block can take advantage of some of these small nitty-gritties. Choosing the parameters is actually, it's going to enable. Many a times we create a lot of parameters, we don't know how to choose these parameters appropriately. There is a chance where we can use AI for choosing some set of right parameters as well. So baseband decoding can actually be there, but I doubt it might take a lot more time for the replacing existing channel decoders there. Further, if you see the channel state reporting, right now we actually have CSI reported from based on the measurements right now. In future, I think is one of the use cases that we are right now evaluating release 18 also is that how do we replace human understandable feedback with a machine understandable feedback? It turns out that we can actually do something more interesting in this space. How do we exchange the states between modules, between one entity to an entity without spoiling the efficiency, but trying to make it more and more machine dependable, machine native kind of a thing is possible in future. And see, this work in these areas are reasonably evident, and some of the examples that we have seen here, there is some also literature existing in this space. How do we represent the channel or represent a channel in such a way that the other entity only can understand, but other guys without the understanding of decoding ability, you can't really understand what goes on here. So this can also be used in maybe the security or security aspects as well based on the availability. There's a quick view. On this slide, I'd like to show, as no set of slide can go without this right now with IMT 2020. So I would like to quickly summarize some of the things I believe can be part of the 6G using AI. So there are ways where people believe we can completely replace AI. I do believe there is a huge chance for that, but there are cases where you can use AI to offline search some nice waveforms, nice constellations, which are not already available with the existing methods that we tried to come up with till now. So there are ways to really search. There is some literature as well. This, I believe, is one of the use cases where you should keep in mind when you want to come up with intelligent waveform. Maybe there's a way to really use waveform AI here. So, and another application I see is whenever complexity is significantly high, you want an approximation algorithm, maybe AI is the right place to really start off some cases to reduce the complexity. That's another observation that I have based on the last few years of work here. System parameter adaptation, as I told you, we create a hell lot of parameters in the system. You look at network, thousands of parameters. We don't know, each block owner tells me this is the right parameter for me to use in this condition, but no one tells me what is the group of parameters to be used in a single shot. So that's another area where there should be smarter algorithms that should come in there. And I see a problem is in the explainability and debuggability of the AI algorithms that we are coming up with is going to play a big hindrance in making them practical. So I don't see them in right matured state to really go and put some of these algorithms and then end up in looking for data, say that data point was wrong, so my algorithm is wrong now. That will be the future if you don't have nice debuggability there. So sensing and AI native, see there are see AI integration with communication is definitely a use case. I also strongly believe that integrated sensing and communication will be one of the important place where AI will play a much stronger role in the full communication system in 6Gs. So with that, I'm ready to take a couple of questions. Thank you.
Thank you, Ashok, for keeping time. And we understand the 15 minutes is not sufficient. So we will give you another time. Sometimes we will call you for tutorial or workshop. So thank you very much. But we can take one question if necessary. Any one question? No, so you are okay. So I request Ravikant sir to kindly hand over the token of appreciation to Ashok. The next speaker we have is Professor Prathajit Mahapatra. So he is assistant professor at Department of Electrical Engineering in IIT Tirupati. He was a postdoctoral research fellow at ITRUST Center of Research in Cybersecurity at Singapore. And he also worked as assistant professor in GS Sanyal School of Telecommunication, IIT Kharagpur. And his research interest primarily in the area of physical layer, secrecy, dot packet communication, and so on. So please give a big hand to Prajit. Over to you.
Yeah, so thanks. So it is a nice opportunity to be here and speak. So some years back, I used to sit there and listen many talks. So now I have the opportunity to stand here and speak. So I'll go into this physical layer secrecy, the role of physical layer secrecy. So in this talk, I'm going to advocate why physical layer secrecy need to be integrated with 6G system. And this is an orthodox approach. Generally, people don't accept it. So we'll discuss some of the associated challenges with it. And with your permission, I'll kind of, okay, so I have some, I don't have that mandatory picture here. So I have some different picture, but more or the less, it conveys the same information, I believe. So any kind of technology deployment happens, we have some kind of a cost efficient sustainable solutions. And there are some basic parameters we look like. We human beings are always hungry. We are never satisfied with the data rates. We are not satisfied with 1 gigabits per second. We want more than that. So that is where like we always want high data rates, network efficiency, then precision. Then the other aspects that I think slowly getting more importance is latency. As we are discussing, I think many speakers have pointed out, 5G is really not able to give you that latency requirement which was expected. So is there any fundamental bottleneck? So that also a little bit highlight. And particularly my talk will be kind of mainly focused on security. I'm not talking about privacy. So what I believe privacy is another different kind of issue than security. So without wasting much on this, don't worry, I'm taking you back to around 1950s era. Just have 2 slides so that I can assume that all are on the same page. So sorry for taking you to 1950. So around 1950, something very interesting was happening. Shannon come up with the Shannon cipher system. So for the very first time, he defined mathematically how to measure secrecy. So he has a very simple model, that is a Ellis, Bob, and eavesdropper who are communicating over a noiseless channel. So there is no noise in it. But the assumption is that Ellis and Bob have some shared key. So then he come up with some condition when you can have perfect secrecy. So he come up with that model and definitions. And many people believe that once Shannon proposed that model and with his result, it gives birth to modern cryptography. Because if you see in this model, they are already having access to some key. The question comes how the users will have some access to the key. If I suppose have a channel, secure channel by which I can share the key, I can use that channel for sending my message user. Correct. So that is where a lot of research started, how I can come up with shared key, and that is where public key cryptography got a lot of attention. But for around 25 years, nothing was happening much from physical layer point of view. So around 1975, Weiner come up with a model which is famously known as Vertep channel. That is how literature call it. So here, what is the fundamental difference between these two models? In this case, there is no key is shared. You can see there is no key is shared, and the communication is happening over a noisy channel. Now you have a very fundamental question. The noise generally considered to be harmful for a communication system. Can it be useful for secure communication? And interestingly, the answer is yes. So there is a very strong theoretical foundation for this. So I'll not go into all the details. I'll quickly go like, basically we talk about these days like cashless communication. Similarly, what I'm advocating is, can you have a keyless secure communication? Without using key, can I have? When Weiner introduced this model, people are very skeptical about practical realism. Like, is it practically relevant? Because there are certain conditions under which only this result exists, which practically may not be possible. Now, with some more changes, particularly with advancement in MIMO, IRS, it may be possible to realize such kind of channel, because I may be able to control the channel to some extent, which was not possible earlier. So again, like as I'm talking about short packet communication, so I'm going to also keep my talk short. So now another aspect I want to talk. So in this case, you see that like there is a communication happening from Alice to Bob. But if you look into many communication scenario, the devices have both transmitting as well as receiving ability. Now, suppose two devices talk to each other, can they agree on a secret key? And all the communication eavesdropper can listen. So eavesdropper can listen whatever they are talking. Even eavesdropper can know what is their encoding scheme. So it has all the knowledge. We are giving a lot of advantages to the eavesdropper. Can they agree on a key? And that is also theoretical. It was proven through a public discussion, one can agree on a key. And this is one of the work which kind of integrated a lot of work practically. And I'll show some. This is just to give some idea. This I have taken from 2016, which still there are a lot of implementation after this also, just to show how many works have been carried out in academics. So there have been many testbeds developed, which kind of shows it is possible to generate a secret key. And one of the thing they use is the channel estimation, which is there in most of the existing communication system. Now integrating this secret key generation with the communication system, we may not have to do a lot of fundamental changes in the architecture. That is one of the advantage comes, because so there are many other steps involved. I'm not going to all the details in interest of time, but channel estimation is one of the steps which is there in many communication system, and we can try to leverage that and also use it for secret key generation. Now, okay, so I'll just give some idea like how physical layer secrecy has now a matured research area. It's not a soft field. It's kind of a own area. There have been a lot of work in information theoretic, because academician works from all permutation combination. So all the easier permutation combinations are over. Now, whatever is left, they are very hard to solve. The other part is channel code development. There are results developed which can achieve capacity for the WhatsApp channel. So like for example, polar code, LDPC codes. So there have been a lot of development happening. Then also algorithm also there are a lot of developments, particularly in the key generation from the wireless channel. Can I use wireless channel for my secret key generation? And yes, the answer is affirmative. Then that is where like testbed development is going on. We are also looking into some of the testbed development. Then the other thing, like from the application point of view, one of the application I've mentioned is authentication. Because once we are moving into 5G or 6G, when devices want to authenticate each other, how I can have a seamless authentication? There are no users. There won't be any OTP coming you and you have to authenticate. They have to seamlessly authenticate. So that is where physical layer secrecy can play a role. Already there are practical implementation of it. But anyway, they have to make it more efficient. Then there are some other applications I'm not discussing here. Now, what next? So what next to be done so that it can, because unfortunately, physical air secrecy is still not part of any standard. Although in recent year, there have been some startup in abroad. I know some of the 2 to 3 startups who are using physical air secrecy as a part of their products. So that is a good thing that already there are startups coming up. And some of the areas that I think need to be looked is how secrecy has an impact on the latency aspect of communication, because that is what we generally ignore. Because once you have a latency constraint, suppose a jamming attack is happening, or you're having a very heavy protection mechanism for the security, then the latency may get affected. So this is kind of very less understood. Then the energy performance, generally people advocate physical air secrecy can be very energy efficient because it can be implemented even on a sensor devices. And but there are not much systematic study in this regard. So these are some of the areas that need to be looked. So currently our group is mainly focusing on these 2 aspects. The other aspects which I believe are more important from industry point of view or standardization point of view, having more systematic study in use cases. That is where a lot of efforts need to be done. And this is another thing. Many cases we say that, okay, we have a crypto system or we have a physical air system. But suppose I combine them together, can I build a much better secure system? So that is another direction people are already working. I know some of the group, they're already working, but this need to be done in a more systematic way. Okay, I have this slide. So this slide I did not deliberately change because the reason is still we are yet to achieve this. And so I'll talk about a little bit about it. Then I'll advocate something else. Now these are the 3 metrics that generally we worry some of the time is latency, then reliability, then this spectral efficiency, different metrics are there. Then secrecy, we generally have a different kind of approach in cryptography, but in physical air secrecy, we can quantify it. And some of the, I've just mentioned some metric here, like information leakage and some of the other metric, but there is some kind of an interconnection among them. And this is something not well known. And that is what I think need to be focused to come up with a framework which can actually try to give us a big insight into it. And that may actually tell us how to design a communication system. So this is where like one of the thing that I'm kind of going to advocate is time is going to be very critical for future wireless network. And what I mean is for every application may not need a very strong security mechanism. Like for financial transaction, definitely you need a very strong security mechanism. But where an IoT device sensing some sensitive data, you may not need a very strong protection mechanism. But then the question comes, how do I come up with that scheme? Correct? How I can actually ensure it is within that prescribed limit. So that is where now people have started advocating quality of security. Like we must convenient with quality of service. But can I have some parameter which quantify quality of security? Then how do I integrate it? So that is where I think this integration of physical network layer basically can play a role in achieving this. We have some work in this direction, but due to lack of time, I'm not presenting. And I'm quickly going into some part of it. Then I'll conclude. So because now, once you look into URLs and other applications, one of the major assumption we have in most of the existing system, I have the like freedom to use a long packet. But the moment I restrict to use a short packet, can I use the existing result? So that is where I have 2-3 equations, but nothing to worry here. So I think this is a very simple equation that I think at least all the communication people know it, like the 0.5 log of SNR. And this equation, the underlying assumption is that the code word length has to be very long. Then only I can achieve this, otherwise I cannot. But suppose I am using a short packet, then what is happening? So that is where like there there have been progress made in the finite block length information theory, which kinds of tell how to trade off between this block length error and the rate, and which was not possible earlier. And so let's not worry about what this equation comes or what does it exactly mean. But one side you can see this is a rate, and this is your SNR, and this is the block length, this is the error. And these equations allows you to trade off between all these parameters. So this is what is captured in this block. So what I'm saying, okay, I can trade off between rate, block length, and error, but there is a fundamental limit behind it. I cannot, if I'm using a packet too short, then I may not be able to achieve some reliability. So some constraint is there. So that I think we should not forget. The other question come is, I want to have a secure short packet communication. It's not just about reliability. Then I have a least information leakage at eavesdropper. So again, there are theoretical development, and in this equation, if you see, there is a rate here, there is an error, and there is information leakage. So what I'm saying, already finite block length information theory kinds of give some way to trade off between all these parameters. So what I'm advocating is, let's not worry about the equation. The point is the physical layer secrecy kind of give you the framework for quality of secrecy inherently. So that is the one advantage you get from the physical layer secrecy. So I'm almost towards the end of my talk. I have some AIML word in my slide. So I thought I should have. So there have been, like, we are talking about AI and ML. But with that adaptation, we are also bringing in new security threats. And that is where, like, the attack surface is going to increase. Like jamming is a very conventional attack, but is there a foolproof solution yet? To my knowledge, there is no still foolproof solution. Now, first time I saw some of the white paper from Nokia, they are talking about jamming attack in the commercial domain. Particularly the concern is if when the deployment for 5G devices are happening, particularly M2M or mission critical application, there a jamming attack can destroy everything. So then this pilot contamination attack, then entry phases of the node in the network. Similarly, like 3GPP, I think talks about false base station attack. So there are many attacks which are there, and this, I think in 1G it will come, I think, more focused. Currently, I don't see 6G focusing much about quantum resistant protocol, but already I think NIST has started like how to come up with quantum resistant security protocols. The good thing about physical layer secrecy, it has a root from information theory, and it proves that it has quantum resistance. So these are some other advantage it has. What we need is the security controls need to be adaptive and context aware. And that is where what I believe. So I'll not go into much details, but that is where what I believe is like this. So let me say. Yeah. Okay. So what I believe is like this PLS is inherently adaptive. So because physical layer technique, if you see, they're generally adaptive to the environment. Now, once you have joint communication sensing in place, can I adopt my security mechanism accordingly? Or based on the context, can I keep the security? And that is where, when I'm talking about this context, that is where AI/ML can play a major role to know the context. So I think already the time is up. So I'll just conclude with few words. So basically, like how to ensure this is not known. There are very limited works, and I think we are one of them to contribute there at the early stage. And the other thing is, already people are talking about attacks on the modem. So generally, we are not talking about attacks on the modem, but already people are talking in academics where they are worried if there is a circuit elements which is placed in the fabrication phase itself. For example, it controls the oscillator frequency by a small drift. That may not be easy to detect, but it may hamper the communication. So these are the new challenges coming up. So I think there are a lot of opportunity to contribute, and there are a lot of scope. So with this, I conclude.
Thank you, Prajit. Thank you for highlighting this physical layer security. Any question? Yeah.
Yeah. Yes, CDMA is a very close example of this color sequence that I agree. But the other problem is when you are using that pseudo random sequence, they have to be fixed. And there are algorithms exist which can actually predict it. But there is a solution to overcome it. We can discuss offline. Okay, so I request Dr. Saptarshi to kindly hand over the token of appreciation. In fact, AI and ML in the previous talk, Ashok tried to overcome the criticism about that. So thank you very, very much for that. So our next speaker is Satish. Satish is a part of Nokia Strategic and Technology Division and heads the standardization and industry engagement in APAC region, focusing on India, Japan, and Korea. In his earlier role, he was the part of robotic system research at the Nokia lab and contributing to the wireless research standardization. The current research interest is 6G communication system focused on sustainable and secure networking. So let us welcome Satish for his talk. What do you?
Okay, Namaste, can you hear me? Actually, sitting there and listening to all these talks makes you feel hungrier, even if it is second last talk before the lunch, but I'll try to do justice to the opportunity given here. So, Parthajit, thanks for referring a very fine paper. Please refer it, make it famous, because I also have 25% of that there. Yeah. But indeed, as in like security certainly is one of the key aspects as we go into 6G, because the connectivity is going to permeate more and more into all aspects of the life. So therefore, it better be safe for us to use that. So today, what I am going to talk about is slightly a bit more conservative. So while we are all talking about different features that you can expect you get from the new generation network, for example, sensing, for example, so something very sophisticated techniques that you can use at the level of physical layer, the use of machine learning, security, etc. But then what I also wanted to get your attention towards was the cost of implementing these features. So there is no doubt on the benefit of the use cases, etc., that would be supported, but then at what cost? And then in particular, with the current situation that we have in terms of the global energy situation, it is becoming an imperative that you look at not only the conventional KPIs of capacity, reliability, scalability, but also sustainability as one of the key things. And today, when I say sustainability, I'll be mostly focusing on energy efficiency, although it has a more broader connotation, including fairness, inclusivity, etc. Okay, but I thought if I don't talk about metaverse, people won't appreciate that I'm in the 6G era. So I'll still start with this. So when we talk about metaverse, typically people think about entering into a virtual world, which is actually set up to their conveniences, and they do some activities there. But for Nokia, it is a bit more practical in the sense that we are looking at metaverse from two angles. One is digital physical fusion, where we have the representation of a practical physical world in the digital domain, which can be manipulated to achieve certain goals. And to manipulate that, we need to have access to this distributed artificial intelligence, which will actually enhance ability of humans to work in this physical world. So that certainly requires, features like, for example, continuous exchange of data between the physical world to create the digital image, continuous exchange of data between the human or the machine that is going to actuate the physical world via the digital world. So because of that, what we see is that there is going to be traffic growth that will be much more than what you would have seen when we shifted generations from the past 4G into 5G. So already we are seeing that there is a significant growth in terms of AR/VR traffic. 12 times increase in traffic is actually anticipated as we get into 2030. And then if you look at also, I mean, this is from an external source, but even our own research, our own research indicates that if you look at, conservative to aggressive estimates, there is going to be a big increase in the traffic demand of the future use cases. Okay, and these use cases are not just gaming, but also practical use cases where we are trying to improve productivity of different industries, like, for example, manufacturing sector, logistics. So for those, this is the requirement. Okay, and these use cases will not be happening inside a house or in a constrained location where you have, say, for example, physical connectivity, but these use cases will have to be enabled for a mobile workforce. That is where wireless networks come into picture, and we have to figure out, I mean, although these are really needed, but can we really sustain this in terms of the energy requirements? Okay, so I'll stay here a little bit. So as you see, so what are the requirements of 6G as we build on the use cases that are supported by 5G? So first part I want to see is from the reverse. I'll go from 4. So there is a need to support 10x to 20x more data rates as we go from 5G to 6G. Okay, and that should probably be done at almost, I mean, and then this energy consumption will not be compared with what 5G supports, say, for example, 100 Mbps or 1 Gbps in 5G. How does it compare with 100 Mbps, 1 Gbps in terms of 6G? Because that is a no-brainer. I mean, we have to expect newer technology to be energy efficient. But what we are talking is that there are going to be different use cases that need to be supported in 6G. So what is the energy consumption of at even the peak load between the two systems? So that also should not really scale linearly, but it has to, in fact, go in the reverse direction. Okay, so the target is to provide 20x more capacity, but at 50% lower power usage, because the energy situation is not in the positive direction, but it is going to be more and more difficult. The other thing here is that at lower, so now we all know, what are the use cases that actually need these peak data rates, and I just took an example of metaverse to illustrate that. But what we have seen from our existing deployments is that 80% of the time the base stations are not running at peak data rates, but they are running at only 20% of the capacity that is needed. So therefore, if your technology is optimized for the peak data rates and to scale up the capacity, sometimes we do not have the same kind of, say, for example, efficiencies when we are talking about lower data rates. This thing is pretty stark if you try to compare 5G versus 4G. At low data rates, we find that 4G is approximately 2 times more energy efficient as compared to 5G. But of course, at peak data rates, 5G in fact is like 90% more energy efficient as compared to 4G. But when we talk about lower data rates, because of the need to actually scale to higher data rates, I mean, the use of heavy processing in the digital domain. So there is a need to keep some of the circuitry on, which makes, at very low data rates, earlier technology more efficient. So what is the expectation from 6G? So with 6G, when we already know from the field that, this is the case that we have to support lower data rates, it is very important to actually gracefully reduce energy consumption as we go for lower data rates. And at zero load, the target should be that you should be able to consume zero energy. Of course, zero as in like near zero. Okay. So this is the motivation for us as we develop 6G networks. And what we will do in the coming few minutes is to talk about different technological directions, I would say, not solutions, and the kind of trade-offs that are there as we try to achieve this. In 5G systems, I mean, as we go to lower data rates, we have technologies like, for example, MIMO muting, so that lower data rates consume lesser energy. And then if you go even to lower data rates, you can start using this discontinuous transmission, which is where you get the maximum benefit. But even beyond a particular set of data rates, say for example, those that are needed for these IoT devices, 5G still consumes more energy as compared to a 4G base station. So what can we do in that region is something that we have to see. Okay. So as I said, I mean, this theme and the focus of this topic is not only looking at the conventional KPIs, but to look at sustainability as a key KPI that would be at least in our interaction with the different potential adopters of the technology to be a key gating factor, irrespective of whatever feature you support, whether the system is going to be more energy consuming or less. Okay. So just to see, what should be our focus? Where should we start attacking in terms of trying to reduce energy consumption? So this is a view of energy consumption from a CSP perspective. So if you look at it, the mobile networks of all the components, the radio access contributes to around 73% of energy consumed. So this is where our focus is going to be. So if I take example of a RAN, and this is an example of a 5G RAN, you see we have this CUDU and then RU. If you look at the split of energy consumption within the RAN itself, we see that 90% of the consumption happens in the radio unit. And here we have taken example of a 5G massive MIMO system where we are looking at 100 megahertz of bandwidth that is being used. So even inside this radio unit, if you again break it down into different components, for example, the power amplifier, digital front end, L1 processing, etc., what we see is that power amplifier takes about 60% of this 90% energy that is consumed by the radio unit. And then digital front end, which is crest factor reduction, FFTs, and all those things, they actually consume 15% of the energy. So the focus of some of the technology directions that we will discuss will be in the domain of how do we try to create solutions that will try to reduce the energy consumed in this component as well as in the digital front end component, how we can really shut it down to zero. Okay. So with that, so there are different tuning forks, if you may, that we have for that. So one essentially is the waveform. So what kind of waveform has an impact on the PA efficiency, because that directly is dependent on peak to average power ratio. So as you know, when we started with GSM, we had a very nice continuous phase modulation GMSK that could support lower data rates, but then had very good PAPR characteristics. Then we had to support larger data rates, but at the same time address the aspect of this multipath and also this intercell interference. So we went to CDMA. And finally, for supporting large bandwidths, we went to OFDM. So while it supported large bandwidths, the problem happened is that it actually has a very bad PAPR characteristics from the perspective of higher PAPR leading to lower efficiency of the power amplifier, and hence the amount of power that you would need to support a particular data rate would also go high for similar data rates between a single carrier waveform to this. So with that in mind, I mean, there are different levers, and I'm not proposing any solutions here. What we're trying is that, I mean, we have considered different waveforms, and what we have finally concluded is that there can be no single waveform that could potentially address the wide range of the use cases that would need to be supported. So say, for example, for supporting higher loads, certainly we would need to go with OFDM waveform or whatever variants of that, and in that case, higher PAPR would be necessary. But then, as we know that 80% of time lower loads are there, so then for the lower loads, we could probably look at other waveforms for better PA efficiency, and from extremely low loads, probably we should look at our good old continuous phase modulation. And then one of the aspects is also that if you have to have flexibility, how can we use machine learning techniques to actually determine the best waveform that you would need for a particular load that is currently on the base station. So this is there. So another lever that we have is that, I mean, if you look at lower data rates again, I mean, and we are trying to attack that part. So you could actually find ways to actually clip the portions of the data where you are looking, so in the frequency domain, wherever you are looking at higher powers, you can actually clip that. But then that would introduce errors. And if the data rate is lower, potentially you will be using lesser resource blocks. So there is a opportunity that you can use guard band signals to actually compensate for the errors that are introduced. So this flexible playing around with the guard band signals, depending on how you want to trade off data rates with the error that is introduced because of clipping, is another way. The other tunable parameter that we have is that, trying to push the operation of the power amplifier to more towards this non-linear region. But then, that leads to the issue of two things. One is this error would increase. So that potentially could be handled by the use of machine learning in the receiver, so that it can overcome that error that it introduced. And then, second aspect, if you push towards non-linear region, is that it would increase out-of-band transmissions. So there also, with advent of technologies like, for example, sensing of usage of adjacent spectrum, like we have for this CBRS systems, what we could potentially do is that if we find that in these adjacent bands, if the usage is less, then we can, potentially go for this more relaxed out-of-band transmission requirements. So, that would be another lever for us to trade off between higher energy efficiency versus this out-of-band emissions, because anyway there are no other users to be interfered with. So then very quickly, so not only on the radio layer, we also have to look at flexibility in terms of architecture. So the trade-off between latency, which is this distributed architecture, with the centralized architecture, is that this overall energy that you have is that power usage effectiveness of the data center is greater than the cell site. So there's a cell site and there's a data center, plus you get the pooling gain, and the trade-off is with whatever transport is available and the consumption. I'll need 2 minutes. Thank you. So yeah, and then while we focus on, I know there is a lot of research going on in the domain of what we do with the radio, because that is a tough problem to solve. But then one of the things that we have also seen is that more innovations in the domain of engineering itself. Say, for example, what is the kind of hardware that would be suitable for doing this physical layer processing thing, is something that actually provides very sizable advantages in terms of energy efficiency. We have found that use of an advanced SOC, where you have this inline acceleration, allows you to gain around 10 times lesser power as compared to the use of a regular CPU GPU for L1 processing. And then since this is specialized hardware, we also need some kind of an AI ML based mechanism to actually switch off these functions whenever the requirement of such functionality is less. The other aspect is AI computing. I mean, AI is a great tool, but then it consumes a lot of energy. So one of the things that we have observed is that, I mean, in terms of AI, most of the operation that are there are actually multiply and accumulate. So you have the weights, you have the input, you then multiply, accumulate, and then you go to the next layer. So this multiply and accumulate operation actually consumes a lot of energy because of the access of memory that you have to do in terms of getting the weights plus getting the results to put into the next stage. So what we have analyzed is that analog AI, which allows you to combine multiply and accumulate operation actually allows you to avoid these costly accesses to the memory and can lead to 10x power reduction. So this is another tool in our hand to actually look at reduction of energy consumption as we start getting into more and more usage of AI. Then finally, what we are also looking at is in terms of data center architectures. So there is a trend towards extreme disaggregation. So typically CPU, memory are all connected via the same bus, but even that in some data center architectures, there is a discussion that they should happen over the transport network. So what advantage this allows is that it allows you to be more flexible. So you can actually tune your data center to different use cases easily as compared to more fixed architectures like we have today. But then in that case, the use of silicon or this electronic switching does not really scale up in terms of energy, because the amount of data rates that you would need for a CPU to access memory would be much higher as compared to two applications communicating over the transport network. So in that case, optical transport is a great option that has to be analyzed. How far can we get into the chip with optical network? And that is where silicon photonics research is a very promising direction to ensure that we have an energy scaled data center. IP optical integration, another, as I said, there is nothing more energy efficient than optical transport as of now. So therefore, smart use of routing mechanism where we say, for example, lower rate traffic flows, where we can take advantage of like statistical multiplexing, combining the flows, those can be directed towards more electronic switching, as in the routers, whereas larger traffic flows can be identified and they can be switched directly over the optical layer by the use of ROADMs. So if we avoid this like optical electronic switching, that itself we have realized can lead to large benefits in terms of energy usage. Then of course, silicon innovations certainly have a big role to play in terms of energy efficiency. I mean, that is again an area that has to be looked at. I'm just showing some examples where we have realized that, you know, working on optimizing silicon has led to great benefits as part of our products. Then, you know, not everything is research. There is a lot of engineering going on. So the use of liquid cooled base station, how we can use the heat, reuse it for other purposes, have actually shown us very surprising results in terms of very practical ways of reducing overall energy consumption in the system. Then we know that it's not only about the network, but also what it supports. So there is a big role that the network can play in terms of ensuring that we have a more sustainable operations, whether it is in the domain of manufacturing, logistics, mines, drone operations, etc. So one example is that by just avoiding drive testing, we have found that 16 tons of CO2 emissions are saved per 1,000 sites. So this is just one example. And if you look at more broader research that we have done, we see that 80% of carbon emissions come from the physical industries, and only 30% of them are digitized. So digitalization from a study that we have done can deliver around 40% savings of this global greenhouse gas emissions. So this is a big opportunity, and you know, that is why we have to really go beyond the flexibility that is provided by 5G. But to be honest, this like adoption of 5G inside the different industries is still kind of slow to take. So therefore 6G should actually start from beginning in terms of what are the kind of APIs that will allow digitalization to go on the fast track. Plus these APIs not only provide features in terms of you know, satisfying the different connectivity requirements, but also provide APIs that allow these industries to be more energy efficient. So for example, if there is a way for the network to indicate when it is most efficient to transfer data in terms of energy, if there is a way to say, for example, tell that, you know, what is the carbon footprint of the game that I just played. I mean, those small things, developing APIs from sustainability in mind is a very key aspect as we go ahead. And then finally, just a little bit of advertisement. I mean, we are engaged with the ecosystem, whether it is research, industries, or regulators all over the world. and we would be happy to certainly hear your views and thoughts on, on the ideas, because we consider sustainability as one of the key drivers for our 6G plan. Then of course this requires us to work with the academia, with different operators, as the people who have the real field experience as you develop these solutions. And as our CEO said, there is no green without digital, and the digital also has to become darker green. And that would end my presentation. Thanks a lot.
Thank you, Satish, for highlighting and showing the possibility of making the greener. So I would request Dr. Chandramurthy to kindly hand over the token of appreciation to Satish. So our next speaker is Devorsi. So thank you, sir. Thank you very much. So next to Devorsi, now he is a PhD interns. He is doing PhD at IIT Kharagpur and interns at this Samsung R&D Institute. So he is doing the PhD jointly at Mehari School of Applied Computation Science, USA. Over to you, Devarsu. And just a warning.
Yeah, fine. So yeah, I'll keep it very simple and short for mainly two reasons, as because I'm standing in between just the lunch and you, and also like I'm presenting in today I'm presenting mostly in front of my teachers and mentors, like whom I used to follow during my research journey. So like there is nothing too much to note down or something. Just sit back, relax, and just enjoy the presentation for the next 10-15 minutes. Yeah, so my topic is like erasing digital divide leveraging software as 6G. So whether 6G will be soft or hard, we don't know. So like that we need to know throughout this journey, and let's find out that what it is. But just to like to play with what the technology perspective is giving us. So that's why I just just trim it like this soft 6. So this will be a very brief outline of my today's talk. So if time permits, I'll quickly go upon, we'll touch upon some of the findings and the results that we have achieved in our lab simulations. So yeah, motivation is like, I'll start with one of the famous quote of Kate Gilmore that regarding the thing that the internet had the ability to dismantle the divide. Now internet failed miserably, the divide is bigger than ever. So almost like 3.2 billions are yet to be connected, right? And sitting inside this AC room and having these all technological aspects at hand, like it's very difficult for us to realize that what is actually going on beyond the knowledge of our limit. So the thing is that like it's pretty obvious to understand that it is not the thing that we all are here and the entire other globes are enjoying the same facilities what we are enjoying here. So that is the main perspective and motivation that we look into this field of digital divide and how we can contribute to erase it as early as possible. So like if you want to know more, you can just go through this book of The Price of Inequality by Joseph E. Stiglitz to know more about what impact the digital divide could have made in our society and the future perspective. Yeah, so obviously we know that what it is and why it is actually in the picture. So we have like highly progressive metro cities and low progressive rural areas, right? So and this scene is pretty much clear in the perspective of of developing countries, maybe like India or many other countries, whether the developed countries is having mostly on the town or on the areas with advanced architectures and infrastructure. So that actually drives the term this digital divide. So we have the cluster of people who are enjoying some certain of services, whether others are surviving and depriving from the latest technologies. So the connectivity challenges that is actually raised from this digital divide can be seen from this Ericsson mobility report in just last month published. So you see that this thing, like in past coming 6 years, like what the transformation of the existing 5G and also like the other what other like countries in mostly in African regions, they will be still at majority will be using the existing 4G, 3G, and in fact a very little bit will be using 5G, and the developed countries like mostly in Northern America will be privileged enough to have mostly on the 5G line, or maybe some of them will be moving into 6G as well. So we need to close this gap. Like we don't want to see this sort of graph like this. So we want a similarity, symmetry, and uniformity in between these two. So that's why we need to understand that why this digital device is still sustaining. So it is pretty obvious that we all know that sometimes I used to recharge my phone. I am a bit confused that which recharge plan is fitting my budget and it will be most suitable for me. Because we are not using whatever the internet or something that we have been subscribing for. So sitting in this room, if I have to think like that, just think about those people who are not having these technologies and services, like how they will be how well they can use this kind of technologies to gain the services. So that is why this digital device is still sustaining, and this is a major concern in which we want to contribute to eradicate this thing. So I'll see some of these key terms which will help us to reduce this thing, like in software-defined networking, network function virtualization, that will drive the network slicing perspective, and all of this entire thing will collaboratively contribute to the programmable networking. So we'll see that how these key technical terminologies are going to help us. So it's a very brief slide of SDN and NFA, so I'm just skipping it part. So coming into the softwareized network slicing. So what then the perspective of network slicing, we all know that we will no longer will be having the dedicated network infrastructure. It will be mostly on the generic network infrastructure based on that. We can virtualize the network instances so that we can provide the services on a more generic way to the subscribers and the user whoever will be needing that. So that's why each network slice will be dedicated for particular network services, even though we have a same baseline physical infrastructure common in between all of them. And the SDN, the server or the centralized controller will be required that can dynamically change and give the instruction to those infrastructure that in which way they need to behave. And some of the key technology enablers of beyond 5G network slicing are like SDN, NFV, container, edge cloud for computing, and the virtual machines will play a very major role. These are not all of the things, but majority will be covered by this only. So moving to the programmable 6G, so we are talking about 6G. So now we need to look at in which way these all technologies are impacting or will impact our coming 6G. So the 6G transformation will be no longer in a direct way. So it should be from the 5G to 6G. So if you look into this, some of the main building blocks in the open source programmable 5G, we see that how different entities and the blocks are collaborating with each other. So we have the virtualization technologies, the automation, management, and management block here, the core network like in EPC and 5G, we have radio units, RANs, and also the control learning optimization slicings are here. So different technologies and the industries who are contributing in these technologies are collaborating to each other to contribute towards the 5G networks. Similarly, when we want to move this towards the 6G, so we cannot jump in a straight away. So we need to, it will be a learning process through 5G advanced to 6G. So whatever the bottlenecks will face in the 6G network, so in the 5G network, so that will help us to reduce the complexity and the make it more effective for the 6G network. Yeah, so 6G, some people are also saying that it will be a sixth sense of our network. That's because some of the revolutionary technologies on which this 6G will make its contribution, like some sort of like simultaneous image mapping and localization, augmented human senses, gesture activity and recognition, and high accuracy. So how 6G will make its impact into these all technologies that we're going to see in coming future. But yeah, this is the future that we are heading towards. So now coming to the deployment network instances. So if you remember that the initial talk of Kumar sir and also the Murthy sir regarding the 6G vision, and it also talks about the deployment perspective and also some of the key challenges that this deployment perspective can bring into in the Indian perspective, and as also the other developing countries perspective. So that we're going to see here, and this will mostly involve some of the research findings like whatever we have done in our work. So like just to make this understanding very easier, so we need to transform the network whatever it exists in today's scenario. So obviously if we have a 6G core, we want the concept of 6G network softwareization and virtualization with the addition of these two SDN and FE technology. So we are moving from non-SDN to SDN and also is non-VSDN to VSDN. That is virtualization of SDN. Similarly, the hardware entity should be transformed from proprietary to more generic, because to adopt new technologies, it's not feasible to stick into old concepts of proprietary hardware, which actually are very costly and it's not easily upgradable. So yeah, so that's the very brief timeline of the network transformations that we will see, and that mostly involves the research contribution. So we'll consider some of the networks as our graph. This network's specifications as simulator parameters has been taken based on various literature survey and the existing technologies. So we'll optimize it based on 4 well-defined latency objectives. So this term latency we all have come across for almost all of the slices, that how effective and how important this term is. So we'll see the deployment perspective with the help of this as well. So in SDN, we'll see the controller placement problem localization. So obviously introduction of a SDN controller is required to make a non-SDN network a SDN. Similarly, for the virtualization perspective, we'll see that how the virtualization can be done with the perspective of transforming to non-VSDN to VSDN network. So this is a very generic flow, and to understand it more easily, so this is one slide. Like we'll start with very generic network, which is non-SDN, which is a traditional network. So introduction of a SDN controller will make it SDN enabled. So similarly, introduction of a hypervisor will make it virtualized. So we'll see the multi-point placements as well, then the analysis of the characteristics. So once these two entities are deployed, so we now need to flow the network services within that. So that's why the VNA placements within the defined network controllers and the hypervisors unit. So that will also give the notion of service function chaining and the concept of hybrid network as well, where the existence of SDN and non-SDN networks coexist. And finally, the notion of network slicing, like how this all transformation is going and coming into something which will play an important role in the 6G transformation. So yeah, so this is one test case scenario that we have taken in our in Indian's topology. So this is a 16 nodes, 18 edges network. So this has been divided in different clusters and regions. So like I have escaped the mathematical calculations, like where we have calculated these 4 different latency objectives to find out the potential locations of this controller and hypervisor unit. You can see here we have found out the dominating controller and hypervisor location in case of latency. So latency means like latency can be in terms of the deployment cost or the propagation path delay, something like that. So the main finding is that, like, in which way we can transform a network from the very base end or very generic way to the the more advanced or the programmable network. So that is what it is shown in the figure. So this is some of the results that we have achieved. So some more results that we have done similarly on the AT&T North America topology. So here we have also, it is given that in 4 latency objectives, what are the best pairs of the C and H plane units that we should choose so that the latency objectives has been minimized. So this is another test case that has been done in AT&T North America. Yeah, moving into the cost aware deployment in this OPJCP, that is the open joint hypervisor and controller placement. So what we have done is that, like once the placement of these things are done, so we need to look into the characteristics of what the entities we have been used. So here we have considered it on the H plane only, hypervisor plane, as because lots of research have already been done which focuses on the C deployments. So here we take different capacity and the cost of the hypervisor units, so that once they had been placed, so what the overall network cost like the results, that is our major point of observation. And another thing that is shown here to minimize the latency is that, like, is it possible that we can bypass the hypervisor for some sort of for few network functions and directly come to the network controller from the source node, so that it can help in reducing the latency perspective. So the same baseline topology has been used for this, and yeah, so these are different test cases on which it is done, and these are the controller C and H plane pairs on which we have selected the hypervisor types. So the type of hypervisor means, obviously, like this, you can see the cost like in different types of the hypervisor is shown here, and the fantastic results that we have achieved is here. So we see that in type 1, which is comparatively low cost thing, is can cover the northern and eastern part of India, but in western and in southern part of the India needs more costly deployment, as because right now we are standing in some of the cities in the western region which is industry dominant area. So this is one of the very interesting finding that we have achieved from this result. So yeah, so this is an impact of H-plane analysis, and the cost analysis is given, whatever I have explained. So finally, like some sort of 6G driven softwareized network slicing for better connectivity. This is our ongoing research that we are doing. So I will quickly tell about what exactly is happening here. So yeah, so this is a slide we can talk about. So we have different telecom service providers, a group of here. So obviously it is difficult to encourage the service providers to invite them and and make them and encourage them to deploy the services in the rural or the village areas, as because they want to make some sort of profit out of their deployments of or the service giving. So in which intelligent way we can allocate this to some sort of remote area? So in our test case, we are so far investigating the Andaman, Nicobar and Lakshadweep Islands. So that can be any parts in India or any other countries, to encourage them and to make them give them certain solutions, so that then they come into and encouragely and more actively participate in providing the services in the remote area. So this is one flow. Like if we have these baseline village areas and we have the TSP, so how we can allocate them the services to different network slices, so that the slices can be served to mitigate different use cases of various users at the remote areas. Yeah, so yeah, it's like I'm concluding it with this thing. So yeah, so this 6G will play a very major role, and we hope that 6G can kill this concept of digital divide in this coming future. So that's it. So yeah, so future is all about AI. So as many speakers like Partho sir, Satish and Ashok said regarding the artificial intelligence. So I also feel like that this coming next generation AI will play a very huge role in 6G development. So this is it. So yeah, these are my references, and yeah, so this I can skip. So I'll start. Thank you, and thank you for your patience.
Thank you, Devarshi. Any question for him? He programmed complete network.
Devarshi, thank you very much for the talk. What exactly do you mean by the SDN controller? I mean, what is it actually here in this network?
Yes. Right.
Hello. So SDN control, like it is a hardware unit. So yeah, hello. Yeah, so in this work, SDN controller means the hardware unit that is more generic, and that is not a proprietary hardware that has been used for the existing network controller that were there, where there is no the C and H plane separations. So here the SDN controller is specifically designed to act as a it's a hardware unit, obviously, so act as a more generic perspective, so that it can it can be programmed on the go. So this is the vision of network SDN controller here.
I have a question. Ashutosh, I know you have been participating in the CTU
Yes.
as well, right? So how do you see 6G can help decrease the digital divide?
Yes. So, sir, actually, the last part that I have explained regarding the network slicing part, and how, in which way network slicing is going to help this eradicating the remote areas connectivity. So what I feel is that the software-based network slicing in 6G will play a major role, because like if we can encourage the service providers who are initially reluctant to come and invest in the deployment of the infrastructure in rural areas. So we are actually, I have not shown the results. So we are trying to find out the break-even points and the year-wise deployment, that in if suppose they are coming and deploying in 5 years or 10 years of a window. So how much benefit they can get from that, and also like the service of the users who are residing in that area should be served. So this way, I feel that combining the perspective of 6G and the software as network slicing can eradicate this problem of connectivity. That's it.
What do you mean by software network slicing? So that's why I understand even 5G time.
Yes.
More on the software.
Yes.
What do you mean by software network slicing?
Yes. So here the meaning of this software as network slicing means that obviously we have multiple network slices that can be controlled by multiple TSPs there, and we need to deploy some sort of network slice like in which way the slice would be created and would be allocated. So we need one centralized control on that. So yes. It is already there. It is already. Yes. It is already there. So what we are thinking that in 6G also it can help, because it will be upgraded to with some latest technologies, as because it is programmable and it can adapt on the go. So that is our feeling that it can achieve. So even though this work is not completed yet, so we are. Yes. No, nothing beyond that. Yes. Yeah, this is some sort of hypothetical assumptions. Like we are yet to compare the results, what actually we get and what theory will give us.
Needed to bridge that gap, digital divide, what we were calling.
Yes.
You were saying that it has kind of increased the digital divide. We are trying to sort out this. So any areas what we're targeting for that?
So like throughout this thing, my only aim is to to go for a faster deployments, so that we can have the better connectivity in those areas, and hence we are thinking that we can eradicate this digital divide.
That's already there, right?
No, I am trying to make the speed more faster.
Mobile network where there are money.
Yes.
Doing it and going to the rural area.
Yes.
That deployment is the only way of going to happen in 6G.
Yes, but we need to take care of the other networking entities, like the latency and the cost and the service of deployment. So those perspectives are yet to open for research. Yeah, thank you.
Okay, thank you. Next session is networking lunch, not lunch. So kindly use that. Networking lunch. So thank you, Devar sir. Thank you very much. And I request Anand to kindly hand over the token of appreciation to Devarsi.
Thanks.
So we have lunch now. It is just behind, and we will start restore back 1350. 1350. Please come back. Thank you.
50.
Good afternoon. Please settle down. We'll be starting this session soon. So we'll just give audience a few seconds to settle down. Yeah. Good afternoon. Welcome to this post-lunch session. We have two main talks which are going to continue now. So the first talk is going to be given by Ravi Pasumarthy from Capgemini. So his entire credentials are here. So I'll just go through it quickly. Ravi is a technology leader and system architect with 24 years plus of experience in developing wireless and satellite-based systems in 4G, 5G, NTN, and driving O-RAN related architecture and solution initiatives at Capgemini engineering. So he has several other credentials under his belt. So these things are given here. So in the interest of time, I would like to hand over the stage to Ravi to start his talk. So one request to all the speakers in this and also the lightning talk session. We have, where is the volunteer sitting? We have the diligent set of volunteers sitting there. So they'll be showing the placards. They'll be keeping time. So please pay attention to them as well whenever you're speaking. So thank you very much. Yeah. So over to you, Ravi. Thank you. So let's give him a warm welcome.
Sorry. So why it's important and how do you realize it? What are the key challenges to address that? That's something which I'll cover. So I've taken a different picture, right? I've taken a Bharat 60, so Bharat 60. Rather nativity. So my focus is going to be on the HAPS, LEO, MEO, GEO part, which is defined as a part of 60 vision, which is right how what is important of NTN in the context of overall 60 vision, as we call it. Just to a context, right? Because we have been talking all about wireless, now we're talking about base station up in the air. So different set of problems, entirely different set of problems. Whatever we're talking, everything is applicable, but the challenges are very, very different. So to give a context, right, when we talk about NTN, there are multiple things we talk about. Right, you have the labs, A2G, HAPS. Now ATG is for communication, right? And then the HAPS is actually about 20 kilometers, is the stratosphere. But moment you go into higher altitudes, outer space, the challenges vary, right, from GEO to the LEO. So when you talk about NTN, right, there's a debate in the NTN world that HAPS is a separate right entity in itself, not to be mixed with NTN per se. But broadly, if you can talk about HAPS is one category, and then LEO, MEO, GEO is second category. Now there are multiple advantages of it, of this NTN related concept. Now what is more important to understand is there are multiple ways how to realize. One, you have the base station on the ground, which is the traditional one. And then, right, the challenges are like what are the delay latencies, propagation, etc. Now, the second aspect is you are moving up the base station to the space, right? Now, that's where challenges start to come because the satellites are not actually stationary objects, they are moving. You have mobility, and then you have multiple factors. For example, right, different conditions, you look at the LEO part, the latencies vary based on LEO, MEO, GEO. Footprint varies, how much you want to cover. Orbital period varies. And then the handovers, right? In LEO case, it could be as frequent as maybe every 10 minutes. So the problem statements, what I talk about in terrestrial world becomes entirely different when you get this one, the NTN. Second problem is when you try to push the base station up, becomes another secondary problem statement which has to be solved as well. And there are different challenges which need to be addressed to be able to realize this solution as called the NTN in the context of overall architecture. Now, one good part is, right, is currently what our satellite deployments are all, they are based on proprietary technologies, right? So primarily S2, S2X, RCS2. So mix of all of this and then trying to integrate the MEF for the transport part. But that's one piece of it. But the NTN is trying to visualize how we build a 3GPP based network architecture into our specifications into evolving into the NTN part. But problem is that's just a spec part, right? It talks about maybe some part of physical layer, the MAC, the solutioning is open. Resource management is open. Bigger problem in these networks is not about those aspects which are kind of getting defined, but the overall bigger piece. And then my talk tries to cover about what are those challenges which we'll have to cover and how does an architecture consider, right, in the context of the overall architecture. Now, when you talk about NTN, it's a singular term. There are multiple factors which come into picture. Now, first is what is the use case, right? NB-IoT, currently most of the launches which you see are deployments which are primarily focused on NB-IoT, which is low bandwidth, few kbps, few mbps max. But the objective of the NTN is also to be able to get higher broadband, if not actually in gigabits, at least in megabits, right? So how do you achieve it, right? There are multiple ways to do, right? Based on, once again, the geo, but the problem statements differ when you get into each of these modes. The latency, handovers, mobility, interference. I'll talk a little about in subsequent slides. These are another problems that we'll address. The third is the bandwidth, the frequency and bandwidth. Currently, standardization talks about FR1, which is about 30 megahertz, 25-30 megahertz bandwidth max. People are trying to build solutions which are about 5 to 20 or 30, and that falls into the probably a geo range addressing the NB-IoT problem. But the benefit of what NTN is expected to carry out as you go forward is when you start trying to address the FR2 band, which is Kaku band. There, the frequencies can actually go up to 10 megahertz plus range to 26 based on the bandwidth. But then the bandwidth is going to be huge, right? But then if your bandwidth is going to as big as 1 gigahertz the bandwidth, right? You could have multiple beams into bandwidth and then the polarization into kind of, right? That's what the problem is going to address. You will get higher throughput going up to gigabits per second from a satellite. One satellite is able to provide you in FR2 satellite, few 10 to 50s to 60s gigabits of throughput. So that is the benefit you get, that you have one satellite able to operate, provide you a huge bandwidth, pipe available with a wide coverage area, right? That is a benefit you can get when you go to FR2, and then that's going to address the problem of ubiquity. NB-IoT anyway is going to be FR1, which is a lower bandwidth, etc. So that's another problem addressed to state. But the benefit is going to come when you have this FR2 as a bandwidth. But that has multiple challenges which will come into picture, discuss later. Second is a kind of terminal connectivity. Even though everything is kind of what you call standard mobiles, right? So the problem is, even though you talk about NTN, still there are two kinds of problems which comes into picture. Everything is spec defined, that's still fine. Satellite to terminal connectivity only addresses certain market. I don't know the broadband market is going to be addressed using the standard mobiles. That could come into as a custom CPU or custom device. So even though you call about actually, what you call standardization based NTN specification, still this is another problem that has to be addressed. Can your mobile, actually an NTN mobile, once they are compliant to 3GP specs, really solve the problem of a broadband, or they can still be problem only solve a narrow band? If that is not the case, you'll have to get into a custom CPU which has to be built. Then deployment options. There's multiple deployment options which are possible. Currently, specs talks about just a very transparent case wherein the CUD on the ground or base station on the ground and the satellite is actually a pipe and then taking care of those delays. But that's not the way it's supposed to be or it's going to be. Most of the satellite launches or operations going to happen is that you have the base station going up. Now, which part of the game base station is going to be on the satellite is actually once again a problem statement. And see how that in place. Now, how do you can just scalability? Because once you build a satellite in the payload, unlike on the ground, you cannot keep on adding blades. But satellite, you can't keep on launching satellites. Once it's launched, lifespan is actually a few years. So what is the scalability problem? How do you address? How do you dimension? How do you build? How do you take care of these new algorithms which are going to be placed? So that becomes another problem statement in an NTN kind of a network. It's not like I can put in a blade and then launch or increase the capacity. These two are very important factors, is the beam and the beam management. Now, if you get to the FR2 bands, typically analog beamforming is what could be used, and you have huge bandwidth, very high bandwidth, right, which is there. Number of channels could also be high. Number of cells which you typically want to support could be in thousands, 100 to thousands. So one satellite supporting each cell actually having, say, gigabits of bandwidth and multiple thousands of cells to be supported. It doesn't mean it's impossible problem statement to actually able to simultaneously beam all the cells to the ground. So a smart and efficient way of doing a beam allocation, beam management to be able to address the users and the cell coverage is very, very important. So unlike the traditional terrestrial network of beam management, here the problem statement slightly varies of what you call as the beams and how do you allocate the beams And then how do you do beam management? That becomes a very important problem statement to be addressed. Okay. And the last part is the capacity and resource allocation. So resources are fixed, and then they have different kind of service qualities which need to be met. How do you make sure of the resource allocation? Second, there are a lot of issues in the sense of there could be interference because of the delays, once again based on the LEO or MEO, etc. Geo, the delays could be there, interference could be handled, needs to be handled. And then you have this the losses which are going to be varying across each of these, and there could be an outage which could happen in the way of the satellite network. So how do you take care of the capacity performance and meeting the SLAs, and the resource allocation and the interface mitigation is a problem statement in itself, which has to be addressed. So in summary, when you try to transpose, right, the specs doesn't probably talk about any of these things. It talks about, okay, you have the delay latencies, etc. What is the timing advance changes required, right? What is the, how do you take care of the Doppler? So it talks about some of these aspects. How do you take care of the ARC? How the number of ARC processors are required? So the standard terms of how do you build up the, modify the interfaces is what it talks about. But system solutioning of a NTN network is much more beyond than a typical, right, layer 1, layer 2, layer 3 or the RF related processing. You need to consider all of these considerations, and especially as you go to the higher bands, more bandwidth, higher beams, and then the beam management and the impairments and characteristics, right, and the satellite mode of operation. The problem statement multiplies. Now, when you want to build a solution, right, now we have this problem statement, so you have to build a solution. So the way you could have is, one is in architecture design deployment is one part of it. The third part is actually standardization, which talks about what are the changes required in the signaling layer procedures, air interface procedures, etc., to be able to address, right? But then the bottom part is where the solution aspect comes into picture, right? When you have this on the ground, having a cloud native architecture becomes important. Currently, all the satellite networks are mostly, even in fact, the traditional networks. I think the people do benefit the value of cloud native architecture in the program network, etc. So having this virtualized network is actually a way to enhance, right, when you have the NTN solution built on the ground. But as I said, when you get to the satellite, payload running on the satellite, then how do you build a solution becomes very, very critical. What is the solution to be taken care on that kind of a platform where the capacity is confined, and then be able to address these aspects. So that's another problem just to be considered as part of solutioning. Now I'm trying to correlate all to the NTN architecture, ORAN architecture, if you realize, and then you have the SMO, right? So typically in a satellite network, like OSS, BSS, etc., you also have a command center, and there are multiple gateways. Each gateway can support multiple satellites. So the gateway gateway mechanism, selection allocation mechanism is one important part. The control command center of the satellite network is also very important. That drives the overall management of satellites. So we are talking about satellite launch, and then the command center is going to be there. Now that command center, and then provisioning that information towards the network, the RAN network as you call it, or NTN RAN network you call it, is an important part. So what one of the ways to do that is the SMO is something which you need to be built, enhanced as a part of the ORAN network architecture. So you have the SMO, and then you can leverage that to do the specific satellite provision data, and then interface back to a control center. And the resource management is the most important part. Now people talk about machine learning, etc., everything, right? But most of these allocation problems and problems could be solved, right? This is where the ML could probably come into picture in the concept of NTN. But the resource management aspect is the most critical piece. And as I said, all the problem statements are there. You can do in your scheduler, you could do in a physical layer, but at the end of the day, those are just kind of entities which are trying to follow some decisions based on inputs. And the inputs vary across, right from your center to the SMO, to the network conditions, and the way the satellites are deployed, satellite network is deployed, mobility of satellite, number of satellites, and then interference, where it's deployed, band. So multiple access do come into picture. That information is important. So you can't force everything into a right your RAN per se, and that's where, right, the approach what we think is probably appropriate is having this resource management as a component of the RIC, where you have the flexibility of doing all those challenges which are there. And then some of the algorithms which have to build, these are actually the right functionalities aspects which need to be considered. So I quickly posted, I think I got a reminder. So these actually so this is a recap of the 5G network. I'm not going to talk about it. So we all know the benefits, right? Multi-vendor, interoperable, programmable, inline, right? And you have the machine learning for for application of the RAN, improve the network efficiency, energy, etc. Now, idea is how do we superimpose that to an NTN network? Okay, so this is what I try to there are three types of modes. One is a transparent mode, which is currently what is designed. So here you can see CP, but it could be normal mobile also, right? So you could have the CUDU, and then you have this problem statement of the RU could be actually either it could be frontal front end or it could be proprietary front end. There are multiple ways which are there, right? You can have that RU interconnect, and then you have a feeder link station going up. There could be multiple gate stations which are there, gateways which are there, gateways interconnect, and the handover between the gateways is also important problem statement. But end of the day, what is important is this is aligned with the runner architecture. In this case, fully aligned, where you could have the RIC, CU, and the SMO. And biggest play of the overall network of resource management allocation, interface the ground station is handled via the, could be handled via the RIC and SMO concept. So while the CUDU problem is one part of it, the RIC and SMO and the resource management problem is where it could help in the building the NTN solutions. Now take another case of a region network where the whole thing could be on the satellite, right? And in that case also, the whole of the resource management could be part of the ground network, which will be controlling these satellites, right? I'm not going to talk about how part could be in a separate session. And the third part is a regenerative, semi-regenerative, as you call it, wherein you could have the CUs on the ground and the DUs on the top. Now, these were people try to do because you have a solution which is right. As I said, the capacity in the satellite is fixed. If you have the capacity in the satellite which is fixed, one way to do is I can maybe have everything on the satellite, but then you realize that okay, that's not sufficient. Then you realize okay, the DU and RU could be on the satellite, and the CU could be on the ground, and you could do this allocation. So once again, what happens is this is an F1 link. There's a delay which is getting introduced. Now this F1 link delay is also another problem which has to be addressed as a part of this kind of deployments, which is not there in these two cases. Okay, so there are multiple problems and statements which are to be addressed based on the deployment option. This is the way the networks are going to evolve. NTN networks are going to evolve in the future are going to be based on one of these three factors, these architectures. Okay, now very broadly, right? Yeah. So what are the benefits, right? So I try to depict this very high level. Okay, so you have these slices which could be there even in the terrestrial network, non-terrestrial network. You have the typical architecture. You have the control center as I said in the satellite case. And then you have this, all these critical items, for example, ability to scale the capacity, scheduling for smart beam allocation, which is very, very important. It's not static beam allocation, smart beam allocation, management of interference between the satellites beams, mitigation of the inter-beam satellite interference, right? Optimizing, meeting 5Q parameters. End of the day, all this is fine, but there are also certain 5Q requirements that is met. Even the latency is high, there is a latency, the 5Q which is defined in the spec, but those requirements have to be met across the slices. So all of that could potentially be done as a part of a RIC, which are an not a RIC, which would be there, and then driving the whole network down below. Now, when you get into the ubiquitous network, actually, as you call it, right, you could have a this architecture once it's evolved could actually support HAPS because they're the only in the HAPS once again there are multiple architectures. I'll not delve into it. Assume that you have the payload on the top. NGC controlling the HAPS is what it is important. You have a network, terrestrial network, you have actually satellite network which is all controlled. And this becomes important when the TN, NTN kind of a problem statement comes to the picture, which is going to be defined future, that how do you do an interoperability between our function sharing between terrestrial network and NTN network. So this kind of an architecture does help in achieving those kind of objectives. Thanks.
So maybe we can check. Maybe we can pull up the slides for the next speaker. So in the meantime, we have time for maybe one question.
What is going to happen? There's no payloads planned as such for CU sitting on onto the payload.
That's a trend. In fact, there's a plan specification. UPF is also going to be satellite. So that's a trend. So I'm saying that's going to happen. In which case, the CU also has to be satellite. UPF also going to be satellite. That's a particular use case. Those are use cases given. That's going to happen. This would be part of satellite. That's part of the current use case.
And even just edge computing kind of.
That is precisely the case of the edge space is what we call it.
You are going to build some applications. Yes,
that case will be the
So I was trying to think in my mind an analogy between, broadcast convergence with the broadcast network. So there seems to be a certain motivation for it because the cellular system is getting clogged. Now, in this case of convergence with satellite, from a use case or application perspective, how do you think things are going to get distributed on what gets put on the satellite versus what stays on the cellular Do you have any kind of high level?
Can benefit. Traditional community thinks the same thing would happen. It's going to be converged.
So you're just saying that we are going to make it possible for the
Future
solution providers to decide which
Yes.
of these to use. These are becoming interworkable.
It's possible when you have a
interwork.
common core, common functionalities. That's when the decision becomes easier for the operator also to be able to decide what is the basis on which the allocation would happen. That becomes a problem statement of resource.
So then there's the other angle of spectrum utilization.
Absolutely.
So how does that get? How are we? So spectrum is a common resource.
Yes.
Now, how to most effectively use it? What are the pros and cons? Satellite using it versus,
Satellite has two
broadcast
different
versus
bands in the
cellular.
current specification, 255 and 256. So those are two bands which are dedicated for satellite, L and S band. Problem is not about the frequency usage. Problem is the interference which could happen because of actually the satellite operating the network and adjacent of LTR 5G networks which are actually going to be operating there. Problem set is one is what is the frequency you are going to allocate because that's a fixed band. And for this fixed band, you have mobile and the coverage which is to be there. Part one. Part two, more important problem statement is with the satellite and the delays and Doppler which is going to happen with the traditional network, how do you take care of the channel interference happening between those two? That is a bigger problem to start. But I think from a frequency band, it's fixed, at least for an FR1. FR2 is kind of going to be out 25, 26, 26, 28 gigahertz. So there, I don't think that could be a problem statement to handle. But in the FR1 band and 80, that could be a problem statement. Frequencies are defined, but still the interference is a problem to be solved with the satellite actually launching or having a payload on the same frequency band, similar frequency band of the existing terrestrial networks. And this is why the the interface management is a very important aspect which need to be considered in the satellite, probably not necessarily in a terrestrial network.
Thank you. Thank you, Ravi. So the title of the next talk is AI powered telco network. Oh, I'm sorry. Yeah. So can I request Dr. Naveen to please hand over a token of appreciation from ComSoc side to Ravi? Okay, so the title of the next talk is AI-powered telco network cloud automation in the journey towards connected intelligent things, which will be delivered by Gnanapriya Chidambaranathan from Infosys. So let's welcome Gnanapriya.
Hello. I'm audible? So thanks everyone. So far we had been seeing so much of 5G and 6G core kind of solutions, specifically the radio. In the keynote, you would have also heard about, right, the software cloud native scenario and also the network automation. So my talk is more on the network automation and how AI powers that network automation. So I'm not going to have any 6G vision slide or anything. So I'll directly go to, I'll start with the softwareization of networks. Why that is important. While 5G might not have provided till now the promise for low latency or massive IoT kind of communications, but still this entire decade is for that to improvise when we reach 6G. But the idea here is, right, how this is setting the stage for 6G to be deployed or even 6G to be envisioned further. So softwareization is the first part I'll be talking about, and what are the guardrails to be taken and how the end-to-end orchestration and automation is going to happen. So the first part I've just put a simple 5G network architecture, but the key part I wanted to look upon is the softwareization of networks. We are doing disaggregation. Earlier, like it was all coming in a box, right? Now we are disaggregating everything, right? When we do that, it becomes more and more owners and responsibility to make it work seamlessly, right? When we disaggregate, are the components like a real Lego block? Can it actually talk together? Whether we are doing vertical integration or horizontal integration or whatever, is it going to talk to each other seamlessly? That becomes a key challenge. And of course, virtualization, it also provides more opportunity for automation and complete programmability, right? And why this is becoming important in the last few years, lot of, is it not audible? Okay, thanks. So when we talk about this last few years, a lot of digital transformation has happened, right? And COVID has actually helped in IT to become more and more digital enabled, right? Every enterprise has taken that. Now this is coming to the network also, right? So we are talking about environment, how we can go beyond the proprietary, have a general purpose hardware kind of stuff. Hardware is also improving a lot. And how you can get on-demand services today, right? Like you have a lot of plans available from operators, right? But at a particular instance, right, can I actually get that higher bandwidth? So today 5G summit is happening. So everybody maybe in this campus, can they get a real high bandwidth so that they can see a HD streaming of this session happening, right? So is that available today? No, right? So can we do those kind of on-demand services? And of course, when you go to adopt cloud native technologies, right, all this scaling, elastic nature, everything will be available. Network as a service, NAS, connectivity as a service, right? So these two are other topics that is coming into picture. And of course, because of this embracing of digital, a lot of IT technologies are coming in here as well, right? New ways of working, adopting CI/CD, DevSecOps, NetOps, all combinations are happening. And of course, this is going to help in monetization as well. So now, breaking the previous diagram, right, the network architecture diagram, which was like more of blocks, right? Each component is going to be a box that is coming in. Now consider that, okay, like this is all splitted as either a virtualized network function or a containerized network function. And in this complete decade, right, it's going to be combination, right? All PNF, VNF, CNF, everything is going to be there. It can be deployed on operators network or it can be deployed on hyperscalers network, right? So all this, how it is going to work together. So the more and more we are disaggregating, we have to chain all these things together for the service what you want to do, right? Whether it is going to be the network slice for EMBB or URLC or MIOT or whatever it is. So how are you going to bridge all these together? So some examples on how the VNFs can be placed or the network capabilities can be placed is provided here, right? Cell site, what are the components can be placed? And similarly, right, whether it is a edge facility or a telco data center, how things can be placed compared to like the national data center, etc. Right? So with this as the base, what needs to be taken care? More flexibility given, there should be some governance and control also, right? So these are some guardrails that we need to consider when we are taking network to more digital, right? From because we are going to build a seamless kind of interactive network components. So vendor agnostic platform approach needs to be there. Software architecture principle needs to be followed. How are you going to handle the network management itself, right? And how are you going to bring in like AI for more automation? And how are you going to handle the operations, right? Because it's not just only like day zero, day one. How are you going to do day two and beyond? And how this automation is going to happen? And finally, of course, the security. Data is very critical because with this 5G, huge volumes of data is getting generated, right? So how you are going to derive insights out of it? So these are just a few inputs I wanted to talk in the journey towards connected things, right? I have taken this example of V2X. All right. So if you take V2X, there are multiple possibilities, right? It's not just only automated driving or assisted driving. It can also be, right, like how vehicles can coordinately travel, right? Or how you can help in the traffic management, etc. Right? So all these different categories of use cases are leveraging either one of these slices, right? Whether it is high bandwidth or like low latency or massive IoT kind of slices, right? So what we are talking about is how you can actually provide the V2X bundle, right? If I want to do an assisted driving kind of story, right? What kind of facilities I should take from the network, right? Or if you want to do, right, like combined with insurance, pay as you drive, right? If you are driving rashly, then the sensor data will actually be passed and that will be taken as an input for your premium payment, right? So these are different kinds of use cases that we are talking about. So now overlaying the previous picture with the network components, right? So if you see here, like I had given the specifics for 5G network functions, where all it can be placed, right? And since all these things are becoming like more software oriented, it is also important for doing more of automation, right? Because you need to do like data configuration, you need to handle like regular updates of the software that will get into these boxes, right? So all those things needs to be taken care, right? So if you see here, like in the data center, so where more and more of edge specific scenarios are to be considered here. And you can see the red is mostly the radio side components, right? And if you see the green is the 5G core component, right? And infra itself can be of different categories, right? Whether it is virtualized or containerized, etc. All right. So now like overlaying the network slice concept, right? So if you want an EMBB slice, right? So how are you going to place that? If you are going to do an URLC slice, how are you going to place that? So URLC slice, you need this capability like more in the edge itself, right? I will be doing more of edge computing. For example, if I want to take care of some surveillance or I want to do more of video analytics, right? So then I need to have that capability in the edge itself, right? So I'm going to deploy this capability on real time, right? In that premise so that I am able to actually get the low latency service. Now, how this is going to happen, right, as an end-to-end, as a user or as an enterprise customer. So any service that I am going to ask for, okay, I'm actually like want to do high definition video streaming this entire day for this event, right? To this many people who have subscribed for this event, right? So how am I going to do that, right? Or if as an end consumer, I want to actually watch certain application or certain video, how am I going to do that, right? So this is a view to talk about how this end-to-end orchestration happens from the customer side down to all these individual IT systems and the network systems, etc. Right? So this all has to happen in real-time fashion. So with this background set, right, orchestration view is set now. Now let us go to the AI/ML driven scenarios. I want to take like say 3 examples to quickly highlight how AI/ML is helping in those kind of use cases. This is another view I wanted to share from an adoption of AI/ML, right? In the 5G or beyond, right? Because this entire decade we are going to call it as beyond 5G and then 6G, right? Huge volumes of data are going to be generated, right? And it is going to be cross-domain. As I mentioned in the V2X example, right? Whether it is for an insurance or whether it is for a traffic management. So it is all different domains altogether, right? But the data that is generated is going to be leveraged for that, right? So how am I going to build that systems, right? It's not going to be a single big data lake kind of story. There will be a lot of platform of platforms. You will have like feature store where already models are being built, and with the new data, it is going to be enhanced further. Multiple capabilities are going to be there, right? And there are new techniques are also evolving in the AI/ML side, right? So because normally when we say AI, we say huge data, huge set of algorithms, right? Like with multiple parameter analysis needs to be there. But there are also technologies, right? Like a tiny ML, tiny AI kind of story where with the limited data sets, you can still derive insights, right? So we need to choose which kind of combinations is better, right? So this is one example how you can do adaptive service orchestration to effectively manage the service degradation. So assume that there is some degradation happening. How you can help in the auto healing, right? So can I actually like monitor real time? And based on the levels of the signal degradation, can I actually, right, like do a feedback loop so that I can assure that I am providing the right SLAs, right, what I had signed up for, whether it is for an enterprise customers or a normal consumer, right? So if I want to do that, then look at the technologies here. So we will have a lot of technologies, right? Like whether SNMP, CLI, Netconf, Yang, Tosca, every vendor will have different set of such interfaces. And for day 0, day 1, day 2 configurations, you have variety of templates that are available. So how all these can be automated, right? So that is what becomes a very key scenario, right? So there you can leverage all this AI ML. But of course, right, like a lot of standardization needs to happen. Even everybody says that, okay, like they follow 3GPP spec or the other specs. Definitely in the real implementations, there will be challenges. It's not a real plug and play kind of story. The next use case I want to highlight is the energy scenario, right? There were some talks on the energy efficiency stories, etc. Here I'm talking about this energy saving in RAN sharing, right? So if you see here, the TS 28310, right? So they have defined on how energy parameters needs to be like looked at and monitored, etc. Right? And they're also right, like you can leverage AI ML. So this is mostly from the demand supply kind of story. So constraint solver kind of algorithms can be used. And if you look at the TR 28813 and 28913, so there has been clear focus on if the network is going to be virtualized or if network is going to be containerized, how are you going to look at the energy efficiency? How are you going to even capture those kind of parameters and then, okay, leveraged for monitoring, right? So this is something that is being like taken up. So in release 18, like CNF is also like included, but it is a long way to go, right? Not everything is being adopted. But if you see specifically in Europe, right, because of this energy regulations and other stuff, right? So they are actually like looking at how you can handle energy efficiency on one part, energy storage, how you can use the right storage mechanisms, and the other one is right, like how you can handle the green energy combination, right? So this is the next use case. Since we talked about the V2X scenario, like I have taken one example as connected cars. Specifically here, we are talking about vehicle platooning. So what it means is, right, like if all vehicles, if huge trucks are actually like carrying payloads between cities, right? If they go in an coordinated travel, then efficiency will be better. Also, the carbon dioxide emission will be less, right? So how you can achieve that, right? So leveraging the URLLC slice, right, and capturing the kind of camera and other sensor feeds, etc., with computer vision and other AI ML techniques. So you will be able to achieve that coordinated travel. These are other variety of use cases that can be picked up from customer experience to the operations. So how this is all setting the stage for 6G, right? So if you look at 6G, so this is the high level architecture, right, from a 6G perspective, right? How multiple technologies are being brought together, right? Like earlier also, right, satellite was highlighted, right? So there are multiple wireless, terrestrial, satellite, all communications are going to work together, right? And there is a clear view on how AI and ML is going to be like leveraged across all the layers, right? So these are possible scenarios from the adoption of AI ML, specifically in the MNO stage, right? So orchestration and management. So it can be like intelligent end-to-end orchestration and management, AI for network performance specifically, sustainable 6G. Right, the green 6G kind of story. How 6G can itself be an efficient AI platform, and how this is leveraged for secure and private and trusted AI adoption, right? So these are the generic 6G architecture guiding principle, and you can see here AI is leveraged for full automation. And this is the blown up picture for the earlier I highlighted about how the orchestration happens, right? For 5G and beyond. This is an example for how in 6G it is going to be leveraged. So you can see here in the network layer, you have radio transport, all functions. If you see here, AI is there, right? And infrastructure layer everywhere, right? So, but it is also looking about like how you do local AI. The second speaker today talked about, right, like AI adoption across, right? So you will have the local loop kind of scenario, and you will have cross loop scenarios as well, right? So across layers also how AI is getting leveraged. So with this, right, like I just wanted to highlight today 5G and beyond is setting the stage for adoption of AI in your network automation and how it is envisioned for 6G as well. I'll pause here.
Can we take up
Thank
some
you.
questions?
Maybe we can take one question while the next speaker is getting ready.
Can we take up the question from the online mode?
Okay, yeah, maybe we can do one question. Can I request Vinay Srivastava? Okay.
Can we take up the question from the online mode?
And we are looking at patients not as a separate this is part and parcel of how compute is there across.
Are we audible?
Under the duration of the talk,
We'll try to go over the nitty-gritties of spectrum identification, right, for the next generation technology, 6G in this case, which is the marketing name of IMT 2030. So spectrum, when we talk about spectrum, what is spectrum? Of course, right, it's the set of frequencies which are used for the electromagnetic waves to transfer information from one point to other. It's a very unique resource. It is owned by the governments of a particular region, and the regulators they divide these spectrum into, or they segregate these spectrum frequencies into bands for allocation of these spectrum to certain services, right? And services are the use cases which use these frequencies. For example, mobile communication. One subset of mobile communication is IMT, which is touted as 6G now, IMT 2030. right? Every 10 years cycle, you get a new generation defined by ITU IMT group, and which then multiple SDOs try to come up with their specifications, try to match the key performance requirements of these KPRs, and the ones which qualify are then delegated or as designated as 3G, 4G, or 5G respectively, as the case may be, right? So now one interesting thing is that the spectrum has to be uniquely, the uniqueness is that it's very specific to the geographical needs, to the societal needs, and to the legacy, right? What are the legacy allocations in a particular geography? It that dominates the decision making of the future spectrum allocation to the services as per the requirements, right? And we'll see. So you have all kind of frequency allocations, and regulators have a very tough time deciding whether they want to allocate it for the national issues like defense. Do they want to give it to IMT, the terrestrial services, or do they want to open up or give it to unlicensed services, right? So it's a very delicate balance which they have to take. Now we come to the first question: why does 6G need spectrum or more spectrum, or why are we even talking about it, right? So IMT 2020 or 5G already had some spectrum allocation. India has seen the auction happening in 2022 itself, right? So we'll come to that. Let's see the reason, the technical reason behind the ask for more or different spectrum from what we already have at hand, right? So very recently in June 23, we had the draft recommendation of IMT 2030 finalized, and it was approved in the last meeting of IITR WP5D. This is the framework for IMT 2030. It's a very important milestone, and the kind and the famous diagram, I know you all were waiting for this, right? Is this one. But what I want to look this time around is more closely towards the pillars, the 6 pillars which have come up, right? From the three, the mobile broadband, the IoT, and the LLC things. And the new pillars include integrated sensing and communication, ubiquitous connectivity, as well as integrated AI. The ubiquitous sensing and communication, along with these, there are some capabilities which are there to these use cases, either single or a bunch of them, and we'll see which ones, right? So there are some legacy capabilities which the previous IMT generations had, which are shown in green, and then there are new capabilities, right, which have been defined in blue. And if you look closely, right, there are sensing related capabilities for the first time, even though the previous generations were able to provide positioning, very precise positioning as well in indoor scenario, but it was not a capability from ITU perspective, IMT 2030. A positioning has been included as a capability. Now the actual values or the key performance requirements would hence, there would be a process, and these would be discussed and deliberated and freezed upon in the coming years. However, because these new use cases have come, it gives rise to the requirements in terms of the spectrum, the throughput, and the spectrum needs which they would require, right? So now this is the list of the user scenarios and some of the representative capabilities which you can are there with them, right? Now so if you look at only the holographic communication, integrated communication, sensing here, and the indoor and outdoor use cases, you see that for indoor use cases, which are more industrial use cases, for which you have very tight requirements in terms of positioning, the amount of contiguous bandwidth required is huge in terms of gigahertz, while for the even for the outdoor use cases, you see contiguous bandwidth exceeding 1 gigahertz, right? So this is the Y part of it. You need a lot of contiguous spectrum. For 6G, we already have spectrum, given allocated to satellite and IMT services. Now, most of this is non-overlapping, right? And now, so we need more spectrum. We need contiguous spectrum. Where do you get it from, right? There is a physics involved first to see which is the right band for communication, and then we have to see where do you get that spectrum from. So which is the what part of the spectrum, right? What is the right spectrum and what are the challenges? So this is the physics, and this is basically the propagation modeling of the channel. These are the different propagation losses which a communication channel would see, right? Apart from the, and these are apart from the free space propagation losses which we see. So if you see, right, from this point in time, which is around 15 gigahertz of carrier frequency, you start seeing other kind of manifestations, right? And right from the resonance to water, the resonance to oxygen, which deteriorates the signal quality. You have the effect of fog and dry air. So you would like to communicate in the null spaces here, where the propagation losses are low, right? So, but we have this null space already here, and so this becomes another favorite reason to be proposed or to be considered to be studied for possible use in 6G, right? We'll see what are the challenges. And then there are some ducts here in the sub-terahertz or centimeter wave. You know, there are various names, or sorry, the sub-terahertz frequency. This is touted as centimeter wave. So these are the possible places where a contiguous amount of spectrum might be available, right? And this is where the research started a few years back. Now, as you would see, 6G would not use only these two spectrums chunks, but also it would reuse the reformed spaces from 4G, 5G era, and 6G would have probably one essential range where the propagation has lesser losses, which is the essential 6G range, also because this channel has already been modeled already for previous generations, and my time is over. So we'll see that. We'll see what are the challenges quickly. So the only part is that 6G would require all kind of spectrum here, and none of them is indispensable. These are all for different kind of use cases, which we'll see in future. And so this is from the national allocation table. We have mobile service as primary service in these spectrum chunks. So this, which makes it easier for the administration to identify some of the chunks for IMT, right? Looks very promising, isn't it? Then what's the catch? Are there any challenges at all? Right. So, by the way, in the previous APG meeting, Indian administration formally took a contribution and supported IMT 2030 spectrum discussions in 7 to 24 gigahertz as well as 92 to 275 gigahertz chunk, which are both what we discussed just now. However, once you start looking at the challenges, you have to see what are the services which are already using the spectrum. And as some of the previous speakers already told, right? So this is the bread and butter of this band is the bread and butter of the non-terrestrial or satellite communication channel. You have KU and KA band uplink and downlink here, but then at least the satellite uplink bands are very promising, where even the current agenda items in WRC have steady use cases, so that the IMT can reuse the same spectrum for which satellite is using for uplink, right? Mostly for FSS, which is geostationary satellites. So these are some of the chunks of ranges which are being used for terrestrial communication in the sub-terahertz. I'll just run through. And however, sub-terahertz has other kind of challenges, and the challenges are mostly in terms of the technology, right? To enable the communication itself. And if you look at the IC technology here, you would see that beyond a certain point in frequency, the range of communication is 10 meters or less. And that's also, catered to probably a proof of concept of future growth in the technology. So here, I think in sub-terahertz is something which is still a mile away compared to the centimeter wave, right? Unlicensed, probably you guys can go over. And so there are huge unlicensed allocations. So in India, your 5 gigahertz Wi-Fi router uses some of these frequencies. As a work to do, you can go back and check what is the chunk of frequency which your Wi-Fi router does not use from this allocated one in India, and ponder why it happens. So just about the studies before I leave, right? So spectrum sharing, when people talk about, and when you look at all these publications and literatures, you would always see a term called cognitive radio springing up, right? So cognitive radio and such CSMS CD based proposals are mostly restricted or applicable only to the unlicensed bands. But the licensed bands where there are services either giving to IMT, to defense, or to other setups where a particular provider has paid for it and is trying to provide green service in terms of better location, you have to ensure. So probably you guys can go over this. I'm sure the slides will be shared, but I've just tried to make it easy for you to look at the right references in terms of national frequency allocation plan and things. So ITU is the body which basically holds the WRC or World Radio Communication Conferences every 4 years, where the spectrums are harmonized globally. And let's not go through this. The world has been divided into 3 regions: region 1, 2, and 3, and the harmonization happens across globe, the regions. In most of the cases, there are ways in which countries can opt against the harmonization by assigning footnotes. The upcoming WRC 23, these are the agenda items pertaining to IMT, and some of them are very hot. This is the process of WRC. I have to run fast. And so preceding to the WRC, there are some preparatory meetings, conference preparatory meetings, which release a report which goes into WRC. Towards this, the Indian National Preparatory Committee also works, and there are 5 subgroups under which, and NPC is the driving one, and the outcome of these respective items go to APG or ITU. Once more, coming to this, and the last very important point, as you say, that WRC 23 would be first time discussing the possible 6G spectrum, and that should be in the agenda item 10, which will decide the agenda for WRC 27, where all these things will be discussed. So under these, the regions will bring about their proposals on the right frequency spectrum, and some of them will be chosen, and that will decide the agenda for WRC 27. There will be 4 years period during which studies need to be carried out for possible coexistence and reuse of the spectrum. And the reason I'm probably explaining all this is that from India, there is a lack of any forms of inputs and studies towards the spectrum. Spectrum is the Adidev. It's the Ganesha of the Havan, of the communication which you want to do. And if you want to be 6G leaders, well, you start with Ganesha. Otherwise, you're putting your first foot wrong, right? So guys, I know I'm talking to the right community. This is where a lot of research opportunities are required. This is time-bound research, and it results into amicable forms of regulations and appropriate use of resources for your for your geography. So these are some of my suggestions from the centimeter wave band. These are possible studies which could be taken up. And without much ado, thank you very much for your patience with that extra time as well. Thank you.
Thank you. I request the next speaker to get ready. In the interest of time, you can discuss more about Ganesh ji during networking tea break. Thank you. So the title of the next talk is Network Architecture for 6G Systems, Some Early Thoughts. This is going to be by Pranav Jha from IIT Bombay. Mike, would you like that one?
Yeah, okay. Hello, am I audible? Okay, so thank you very much for having me here and giving me the opportunity to talk about some of the work. Though it is not mentioned here, it is mentioned towards the end, but most of the work has been done by Meghna, who is sitting here as part of IIT Bombay. So, yeah. So I'll briefly talk about the architectural aspects of 5G and then some of the issues that we think are there, and then some of the proposals that we have. Obviously, it's a very short talk, so I can't discuss about many proposals. We have done substantial work in this area, but Okay, what is this? Okay, but we'll try to cover two proposals quickly. So here are 2 or 3 limitations that we envisage in 5G system. One of them is that 5G system has a converged core, which actually allows integration of multiple access technologies. So you can have Wi-Fi, you can have 5G new radio, you can have LTE, you can have satellite, all those converging to a single 5G core. But the problem with this unification or convergence in core is that the RAN level information is not available in the core. So if you want to take some intelligent decisions, say if you have traffic splitting, say if you have dual connectivity, a mobile connected to 2 radio access technologies simultaneously, and you want to use one of them to deliver data to the user. So you would like to use the best one available to him. But which RAN or which radio access technology is best for that user at that time is not really known to the core. So when core decides to deliver data through a particular technology, it is not really aware of the radio access information. So so convergence in core is actually, it's a very nice architecture. I mean, that I think is a very nice thing which 5G has come up with, but there are certain limitations. So that is what I wanted to talk about. Then we also think that this coupling between RAN and core is not really required. Now, today, if you look at it, when the 5G system was evolved, so they developed, new radio technologies. Obviously, it's very similar to 4G, but simultaneously, they also developed a 5G core. Now, what happened is that both these things go together. But when we came to deployment, we realized that 5G RAN was supposed to be deployed in non-standalone architecture with 4G core. Now, there is no way to directly connect 5G RAN with 4G core. You need to go take the signaling through 4G RAN. So if your UE has to use 5G RAN for data, and but the core is 4G core, so the signaling will happen through 4G RAN. So this coupling between RAN and core, we think that can be done away with. And you can decouple the two, and you can maybe put an abstraction between the two. So that is the thing. And then we also think that broadly, the mobile network handles everything, in a user and service agnostic way. It doesn't really deal with different types of traffics in different ways. So it has a typical same path, which is tunneled from UE to the core in UPF, and there is no decision based on, say, if the user is not mobile, you don't have to use the tunneling in many cases. So some of those things we think are limitations of the 5G system. So these are some of the issues that we have looked at over the years. So one of the things that I will talk about today is there is a possibility of, so 5G and, is a very scalable architecture in many ways. They have done a lot of disaggregation in user plane and control plane. We will see that, the GNB, we know that GNB has a CU, then CU has a, UP and CP separate, and there is a DU, there is RU. But there is a possibility of further disaggregation. Similarly, the control plane of 5G core has a lot of disaggregated functions, but we think that the disaggregation could have been done slightly differently. So that is what is one of the parts. The second thing is decoupling of RAN from the core. So these we call these two ideas. The decoupling one is actually 5G flow, and 5G serve is what related to this disaggregation. So this is the basic concept of 5G flow. So what we are saying is that we want to decouple the RAN and core. So you put an abstraction in the RAN towards the core, and you put an abstraction between NAS layer on the UE and the radio layer on the UE. Because NAS layer is what is responsible for talking to the core, and the NAS layer is actually tightly coupled with the radio access layers underlying. So if you put an abstraction layer between the NAS and the radio access layer in the UE, and similarly an abstraction on the RAN towards the core, so then you can encapsulate the RAN as a separate thing, and this way you can run the core as an overlay network completely. So it becomes completely decoupled. So what does it give us? I can directly use a 5G RAN without a 4G RAN to connect to 4G core. Because my NAS signaling is independent of RAN signaling. So if I have a UE with 4G NAS, but 5G RAN, I should be able to work without a 4G RAN. So that is the basic. It has other advantages. I can have a simpler edge computing. I don't need a core. I don't need a UPF. Today's edge networks necessarily need UPF. We don't really need it. So those are some of the things that it proposes. The second topic that I will quickly discuss is 5G serve, where, so as I said, 5G already supports level up disaggregation. And there is so we have proposed some additional disaggregations in data plane as part of one of the IEEE standards. But here we are talking about 5G's control plane disaggregation. So the basic idea is that when you look at the control plane, so say GNB, CUCP, it actually manages the DU and CUUP, but it also manages the UE. The RRC signaling is handled by GNB CUCP. So there is a signaling between UE and GNB CUCP, and there is a control functionality residing in the GNB CUCP, which actually manages the underlying user plane functions. What we think is that these two can be separated. So, okay, I'll quickly finish. So, on the right-hand side, we have the existing GNB architecture where you have GNB DU, GNB CU user plane, and GNB CU control plane. Now, in the CU control plane, you have the control of the CU user plane, these two functions. So this is being managed by this. And there is an RRC part, which actually talks to the UE. So what we are proposing is that if you push this RRC out or create it as a separate module and treat this signaling just like another form of data. So the whole of signaling, which actually is handled by the control plane, should not be treated by control plane. It should become part of the data plane or as a service. It can be just like any other data flowing through the network through its own cost requirements. In a way, it is actually done like that today also, if you look at it, because RRCs also use the signaling radio bearers, which are not very different from data radio bearers. So that is the idea. So I'll just quickly wind up. Give me 1 minute, please. So this is, the overall architecture. So if you apply this, so you apply the control plane disaggregation, where you push the signaling functionality out of the control plane. So authentication and all that can become more like data. So authentication server goes out of the control plane. So it basically makes the control plane simpler and, in a way, disaggregated. We also think, apart from many other things, one of the aspects that we are right now investigating is, does it really have an advantage in terms of access security? In the sense that right now, when the UE is connected to the network, so the signaling, it takes it to the GNB CUCP control plane. But if I push the RRC out, then the UE is not actually talking to control plane function at all. So does it help in improving the access security aspect? So that's a question that we are actually trying to investigate. So these are, this is an overall view of this architecture where you have user plane or data plane functions. You have control plane, which manages these functions, but they are not talking to the users. Users are talking to these RRC functions or NAS functions or so on. And then there are services like mobility orchestrators and so on. So that's about it. And thank you very much. And these are some of the references. And, Megan and Akshita, they were part of our team who did a lot of work. So thank you very much. Yeah.
Thank you. So maybe in the interest of time, we can take all the questions pertaining to the lightning talks in the tea break because we are schedule. So the next talk is titled AI Powered RAN, and that's going to be delivered by Ramkumar Sharma from Ericsson Global Services. Some online participants are are audible, so I request them to mute themselves.
There is no audio. There is no audio.
Organizers, the online participants cannot hear. There is no audio coming through the channel.
We are not able to hear.
Thank you. So in LT, a node can itself determine what is the best neighbor to itself. And that is a progression. And then we are talking about SON, where rules are defined, and it is human supervised, where one is defining all the rules. When this is happening, then what has to be done? And now when we are talking and standing here, so we are talking about machine learning. So there are several use cases where, for example, we talk about traffic steering, load balancing, handover optimizations. So these are the need of the hour, because as the network is going to be very complex, the management is going to be very hard. And nowadays, one thing which is gaining a lot of traction, that is machine reasoning. So in machine reasoning, what is happening? Intents are defined. That is in network, what has to be achieved. And we are not defining how it is going to be achieved. But machine has to learn itself. It has to determine, for example, I need to have 70 Mbps throughput for 90% of my subscriber. That is my need. And I'm not defining how it has to be achieved. So machine has to learn, and that's where industry is moving. Now, combining all the things, we have numerous use cases. We have huge data demand. Security is very much needed. And to have that, intelligent automations are required. Networks need to be green. If I combine them and put them into a bundle, what does that mean in terms of my RAN? So when I talk about radio access network, and especially I talk about protocol stack, which starts from layer 1, that is my physical layer. Then I have layer 2, 3, and so on. So in terms of time scale, I can define 3 closed loop, layer 1 and layer 2. These are at the microsecond to millisecond. while my layer 3, it has a little bit lenient requirement, and the other two loops, which are bigger circles. So these two loops are related to network optimization and network design. So mostly I would say the network design and optimization. So these are happening manually. So there is a lot of scope to be optimized there. But if I talk about my control loops, which are layer 1 and layer 2, these are already autonomous. But if I'm bringing machine learning into that, that means I need to learn what would be my optimal internal state, which can trigger these RAN algorithms. Now, I'll quickly talk about lifecycle management of AI-powered RAN. So if in industry term, if we say that something is everybody's responsibility, then it becomes somebody's, and finally it becomes nobody's. Then in this scenario, we have to determine who owns what. For example, if some vendor, it is not necessarily network equipment provider, it could be third party. For example, in Open RAN, where we are talking about disaggregation. So in SMO and other, for example, some machine learning models are coming from third party vendor. So who would be designing, who would be training, and once it is accepted by the operators, what is the responsibility of the operator? So these are different responsibility. I will not dwell much into that. And I have taken one example, which is the intent-based network management. So CSP is defining what do they want. Then the intent definitions are coming. And then further, whoever is the equipment provider, they need to pass on to different network slice management functions. So it's a close net of integration of different functions, which has to be explored. Further, it is a simple view where we are standing, where do we want to go, and what is the long-term vision. For example, in radio access network, there are multiple problems which are handled with different kind of models. Because these are trained locally for each cells for different kind of radio environment, these are called a specialized model. So the objective is, rather than having a specialized model, generalize them, and in long term, have that layer with the AI ML enabled capability. And to achieve that, these are two enablers, which are model generation and scalable and learning scalable platforms. So in model generation, generalize a single model for all kind of different radio environments. There could be conflicting intents. So the model should be trained how to maximize those conflicts, and a single model should be sufficient to perform different kind of actions. And in terms of platform, for example, in 3GPP and Open RAN, SMO, which is a service management and orchestration platform. So most of the learning and data collection is happening there, and there is a disaggregation in terms of CU and DU. So whatever the model is learned, the learning has been transferred to those CU and DU. So I'll wrap up in one. So I'll quickly talk about AI native RAN. So AI native, when we talk about, it's an intrinsic capability. It is not sitting outside and learning something, but it is built inside the whatever the product or whatever the network function is there. And when we are saying that something is AI native, so these pointers has to be looked upon. For example, what is the purpose of that product to be AI native? For what environment it would be interacting, whether it is learning from those new findings, and what kind of interactions it would be doing to other network functions, or what kind of different environment is there, and whether those network AI nativeness, whether it is producing some value addition. And I'll quickly touch upon this specific model which Ericsson has come up. So when we say that we have some AI native capabilities, then how to evaluate that? So from Ericsson, there are 6 models or 6 levels which has been defined, which are level 0 to level 5. So level 0 means it is not AI native. We have some AI ML capability, but it is not complying with other functionalities. To have the AI nativeness, the minimum level is required level 1. And these are some, these shouldn't be treated as the target, but these are some of the guidelines. So some functionality or some product, they may require that level 2 or level 3 is fine, but some may require level 5. So as per the need and as per the use case, this level has to be looked upon. And this is one of the use case which I'll quickly cover. So we have already witnessed about sustainable networks. So if we talk about interaction from a network and a single subscriber, so the CO2, a greenhouse gas, which is generated, it is this much amount, 9 kg and 2.6 kg. Embodied energy, we cannot talk about much how we can mitigate, but in real networks, we can definitely control the operations. And as per one study, the most of the expenditures, 25%, goes of service provider goes into operation cost, out of which 90% goes to energy bills, and in those energy bills 70% it's contributed by the radio access side. 3GPP has already proposed so many features, but those are basic features. How we can tweak those features to our need, that depends to us. And that brings to one of the interesting use cases, which is energy efficiency. So in Ericsson, what we did, we tried to tweak the cell sleep mode, and we utilized the AIML, and we were able to gain the 10% energy reduction, and that is significant in terms of total billing amount. And this is a quick look how 3GPP is looking. Ashoka has already talked about release 18 and different use cases where CSI enhancement, beamforming, and positioning is looked upon. But this journey has not been started just now, but with the NWDEP, which was in 2017, and the platform which was defined in release 17, which was in 2021. And these are several use cases which one can explore, but these are not limited, but depending on what is the requirement of service provider. So with that, I would conclude and
Thank you, Ram. So the next talk is titled Envision of Compute Platforms and Cloud Computing for 6G Networks. This is by Mahantesh Kotiwale from Samsung Research Institute.
Hello, am I audible? Am I audible? Okay, good afternoon, everyone. We are all communication society, right? So I would say being very ambitious here, rather greedy. I will say why. We are hearing today, right? The 6G has to be AI native, 6G has to be secure, 6G has to be high speed, 6G has to be low latency, and at the same time 6G has to be low power. So there is another community, like compute platform community, deeply concerned, like what these guys wants everything, and then how to do it. So you're just talking that, so you have to think about them also. So can there be a platform? You need high speed, secure, accelerators, and low power. So yeah, this is the one consideration, important consideration, which I want to cover as part of the 6G technology. So yeah, we have seen these requirements, right? Or rather the use cases. So that's going to be the fantastic world we are going to live. Altogether, it will bring the requirements of data rate and latency 50x more than 5G, 10 times lesser latency than 5G. And then at the same time, the 6G has to be open. It has to be virtual. It should be there on the cloud. And then there need to be need for split computing. Yeah, I'm audible. Hello? 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 Yeah? Okay. Yeah, so what I mean to say is there are different requirements coming together, putting challenge on the compute platforms. The different kind of requirements like performance, architecture, and trustworthiness are well covered in our 6G vision book. You can have a look online about it. So let me cover how were the deployments in terms of compute platforms. So we know 4G was custom hardware, like there were different SoC vendors who gave the modem solution as a whole. The carriers took those SoC solutions and gave it to the carriers, and then That's how the deployment was. So at the same time, it was non-virtualized, vendor specific and less flexible. It will be there at a base station and then just remain there. And then the cost of operation, the cost of deployment was in the control of the vendors and the infra companies who were providing the solutions. So coming to 5G, which we are living now, what I would say is it is in the transition phase. I mean, there are flavors of the custom hardware deployments as well still going on. The carriers and infra companies are still wondering and figuring it out what would be the exact benefit of virtualization and this kind of disaggregation. But still it is in a right path. I would say the era now is towards virtual RAN and open RAN. And at the same time, the need for AI in wireless is well sensed now. And that is giving good sense that 6G need to embed the AI from the beginning. So let's come to the 6G, how it is going to be deployed in 2030. As shown there, the compute power is needed everywhere, starting from core, base station, even we don't know how the devices will look like, but we can easily envision that device also need good amount of compute platforms or compute capability. So overall, I would say 6G is going to be virtual RAN, open RAN, AI native. It has to be secure. It should be supporting the split computing and it should be energy efficient. So let's dissect what kind of different kind of platforms are needed at each layer. So 6G, for 6G speeds and latency, every layer is going to matter. Unlike for 5G, until 5G, you can take one unique or one category of platform and then apply it for all the layers. Maybe it was possible because of the speed and latency requirements required at 5G. So let's dissect and look one by one quickly. So layer 2 and layer 3, which are like stateful packet processing and preparation, which can be still satisfied by the CPUs, RISC and CISC based, even for 6G. The major thing comes in the type 2 of processing, which is like stateless packet processing, where you need the very, very high speed packet processing and packet forming. So what we can think now is the efficient packet accelerators are needed. So type 3 is very important for the layer 1, the vector processing is needed. And then the heavy forward error correction like LDPC needs still the accelerators. And then AIML, if you want to make the AIML as part of the 6G, then GPUs and maybe FPGAs are also needed. For security between any disaggregated services, the security accelerators are needed. So overall, it is looking like heterogeneous set of computations are needed when we think of 6G deployment. Another consideration I want to bring here is the trade-off. So we have a lot of COTS services, COTS compute platforms available. GPUs are there. Low power RISC CPUs are also coming on the cloud. GPUs are also there. DPUs are there. Smart NICs. So all are getting available on the cloud. It gives a lot of challenge to the telco architects, which one to choose. And putting everything together, can it be power efficient or is it secure? And then is there enough of AI compute capability there? So what I would say is overall, the 6G, particularly the RAN, 6G virtual RAN, need to be scalable, secure, low power, high speed, heterogeneous, and AI capable. So I don't have the solution, sorry, but that's the work to do. So quickly, before going to my conclusion and way forward, let me cover quickly on the 6G device also. Device may not have big challenges for 6G because one thing we can consider is it can offload its compute requirements to the network. Just that it is bringing a requirement of split computing architecture need to be defined for 6G. So, however, even if somebody want to rig up a SoC for the high computation, it's not possible because the limitation of computing power and the battery life is going to be the limitation for hologram kind of applications. So with that, I would like to conclude way forward, the compute platform and communication technology have to join hands together and make a right solution for that which we don't have now. So with that, I would like to call this a starting of era of communication and computing convergence. So that's, I conclude my talk.
Thank you so much. So our next speaker is Neha Sharma from Samsung Research India. And the title of her talk is 6G Network Architecture and Security, Enabling Future Connectivity and Trustworthiness.
Hi, good afternoon, everyone. I'm Neha, working with Samsung Research India, Bangalore in the 6C lab. So today my topic is network architecture and security. So we have heard a lot about the 6C, what are the 6C use cases and all. So in this talk, I'm going to cover more about the 5G journey, the Samsung 5G journey, how the 5G evolution is in the 3GPP, and what the need for 6G, a bit mega trends related to that, and the requirements for the same. So to begin with, sorry. Okay, so the Samsung 5G journey has started almost a decade back, and where in 2012 we have our own internal 5G testbed for the terminals as well as for the base station, followed by the prototype demonstration in 2016 in mobile communication on the first millimeter wave. And then the early trials have happened along with the various network vendors and in other infra vendors. And we have done the first 5G deployment in US in 2019. And today, in 2019, there was the first 5G device was commercialized with various network operators. So today, the 5G devices as well as the network, they are supporting all the non-standalone, standalone architecture, all FR1, FR2 bands, voice, and other kind of stuff. So the Samsung has the way it is like in 2019 when the 5G devices were launched. So that time itself it was thought, what is the next thing? What is beyond 5G? How the 6G will look like? In terms of 3GPP, for the 5G evolution, it started in release 15, where it's mainly introduced the 5G framework, the basic architecture. In release 16 and 17, it's more about introducing the vertical use cases related to V2X or NTN or this public safety. So release 18 is the one which actually where the 3GPP has also taken a more bolder steps where they have introduced some AI ML kind of applications. And also there was a lot of enhancements have been introduced related to energy saving. So in release 19 is also recently the workshop has happened, and there the main goal is to cover the gaps of release 18 and also pave the path for the 6G, which is likely to be the release 20. So we have all good in 5G, we have 5G networks, we have 5G devices, and 3GPP is also progressing well. So why do we need 6G? A lot of fellow speakers have already talked about some of the, the use cases for the 6G here. So where we have XR, VR being it's a hologram or digital replica, they all required high data rates, very low latency requirements will be there. You need a high bandwidth, and you also need a the being it's a network architecture or the security should be scalable to satisfy these requirements, which is not possible in the 5G. So as is it quite detailed, I've been talk about this. I'll not go into details of this. So in terms of the mega trends for the 6G, how like it is different from the 5G. The one thing is till now, whatever the wireless have been designed, there humans were the main consumers. But when we goes to the 6G, the machines will be the main consumer. So this means that virtually there'll be no limit. I mean, in humans still you have a perception limits, but in machines there'll be no such limits. So this means that the network or the other things also need to be designed in such a way that there should not be limits apart from your computing power. So it is expected that by 2030, almost 500 billion devices will be there, which will be there in the 6G. Then AI in case of 5G was designed when it is already, the 5G system was designed first and later the AI was introduced. That's why maybe many cases were there, which let's say can be solved by AI, but still there are some gaps. But in 6G, it will be a native AI where AI will be introduced from the scratch itself. So that is another trend. Then the cloudification of networks. 6G need to be fully cloud native. It's not like that you have someone the virtual RAN and all those things where it means the network architecture need to be redesigned and it should be very flexible and scalable. Metaverse, which is a kind of XR thing where we are talking about all these metaverse town, metaverse societies. So that is another trend which will be in the 6G. And one of the main goal is clean tech for sustainability, which is like a greener networks. So basically we need to have a good 6G, need to have all these things. And apart from that, we need to take care of the energy things also. So based on this thing, the Samsung has mainly three 6G requirements. One is the performance requirements, where you need a high data rates and low latencies. There are trustworthiness requirements where, we are talking about a lot of openness, usage of a lot of AI and all. So this means that your hardwares and other things need to be trustworthy. So the security requirement will be more strict as compared to what we have in the 5G today. In terms of architecture requirements, some of these aspects Mahantesh has already covered. In the 6G, we'll have a more like a split computing kind of mechanism is also there apart from the edge computing and all. The network design should be like that. It should be very, very simplified because, linear and energy saving is another goal for the 6G megatrend. We need to have a fully cloud native kind of system, and these should be very flexible and scalable. I'll touch upon something on the service-based architecture in the next slide. And the network should be like that. It should be like a plug and play where it is able to support diverse set of devices. And we'll need to have new kind of network topologies, which is like cell-free or mesh and all those kind of thing. And of course, the NTN, which is a kind of was introduced in the 5G, but it will be fully utilized only in the 6G only. It's a rare realization will come into 6G where you have integration between the terrestrial and non-terrestrial network. And these are one of the main thing which will actually, reduce your digital divide, which is also one of the UN goal. So when I start with the service-based architecture, this is what we have. One of the like a possibility can be like today we have like mostly the core is which is a more flexible and scalable because of the service-based architecture. This means that any entity can talk to anyone. But in possibility of 6G could be, we'll have all the network entities, being it's in the RAN or in the core, they can talk to any other entities. So we have more details in this paper, which is published by Samsung. If anybody's interested, they can go to the details of it. So this kind of design helps to have more flexible and to be and more cloud friendly. So in the 6G security trends, there are few of these trends are there, which are main security threats, and these need to be considered before designing the 6G. We're talking about network openness, where we want to open up all the possible interfaces, but this means that there will be a lot of unauthorized access into these open interfaces. And this may lead to the solution like zero trust architecture kind of things are required, which is anyways is already in the cloud network, but we need to have something similar for the 6G network also. Then virtualization and containerization. Again, these terms are something which is known in the 5G, but when 5G security was designed, this was not considered. So we need to consider vRAN and vCode security also in the 6G security. Then we have this network AI. AI, we're talking a lot. This means that a lot of data will be there. So there are two perspectives. One is you need to secure AI data itself because these data will be used for various purposes. This need to be secured. Another thing is the AI also need to be designed for the security. A lot of algorithms can be used which can help to enhance the overall security. Sorry, just one last slide. And another thing is the quantum computing. So typically the current algorithms what we have today, they can be easily be broken by the quantum machines, which are possibly come by 2030. And the existing crypto algorithms, they are not capable of, provide any security against that. So there is a possibility like, data can be harvested today and can be decrypted later when the quantum machines come into existence. So it's important to work on some of the algorithms which provide the secure mechanism against both the quantum and the classical computer. So the post-quantum cryptography is one of the technique algorithms are there which can help us to solve these kind of issues. With this, I guess she's already mentioned the time. I like to conclude this. Thank you.
Thank you. So the last speaker for this session is Vinosh James from Qualcomm, and the title of his talk is AI in RAN.
A lot of familiar faces, so good to be here. Thanks for inviting me. I have some bad news and some good news. Bad news is I have like 50 slides. And good news is they canceled the tea hour, right? So we have all the time needed for it. I'm just kidding, right? Just to ensure that you're in here. So I'm going to talk about AI and how we apply it. So if you know Qualcomm, we are like a technology company focusing on chipsets, which will then power a modem, which has a radio, and then it also talks to a lot of sensors, which is in the device, right? So when I talk about AI in RAN, I come from that perspective that how can you design AI which is power efficient, compute efficient, and can run on a small compute platform, right? So this is like the best case of two. I think you spoke about it nicely, right? That compute is what is actually leveraging AI gains, right? So there was two things happening by itself. Technology was also evolving from 4G, 5G up to 6G, and then the compute platform was also coming up. So this AI in communication is like the perfect marriage, leveraging each other's strength and then trying to find out how to basically leverage one aspect into the other, right? So that's where this thing is about. And if you look into it, it's a broad stream. I'm going to focus on very narrow thought because it's like 10 minutes. So I'm going to talk about radio awareness, right? So what exactly is radio awareness in a device, right? You're talking about a handset which has multiple radios, some of the spectrum being very narrow, some of them being very broad. Some of them can carry multiple MIMO streams. Some of them may be just using a single CISO stream. So if you look at it again from a communication handset perspective, you have your WAN, you have your LAN, and you have also other things like short range radio, several other things. So the AI in a device is actually going to help you optimize a lot of these parameters, right? Let's focus on a very simple case because I have like 2 slides later focusing on some results which I will actually bring in. So let's focus on millimeter wave. Let's focus on parameter estimation or channel estimation for that millimeter wave optimization, right? How do you actually do that today, right? We do it. We solve the problem, right? That's the reason 5G is in there. But then you would have definitely heard feedback that the moment I turn on 5G, power drain ho jata hai. So I keep it on 4G or I try to keep it in sub-6 or things, right? It's natural. It's natural because they solved the problem of first trying to put a millimeter wave into it, and now comes the play of how to actually optimize it, right? And there is always this game, right? So everybody in this room must be familiar with Gini optimization. Meaning, if I know the perfect channel between the source and the destination, I can reciprocate it and then try to do the best to actually match to the channel. But if my battery is like draining in 4 hours, how am I actually going to do it? All that I can do is do samples, right? But then people in this room or people who sat before this in this room wrote hundreds of paper on how can I actually use channel estimation done on the 6 gigahertz band and then try to estimate something for the millimeter wave band. Problems are still the same. Parameters, how do you estimate the parameters? How can you actually estimate the correlation? And how do you actually do that? That is the thing about this millimeter wave optimization problem. You try to figure out how can I actually do it efficiently, and then AI is just a tool, right? I'm actually oversimplifying it. It's not. right? There are researchers in this room, who are actually making a life out of it, right? So let's not oversimplify, right? So that's the context. So you talk about spectrum sensing and access, contextual awareness, environmental sensing, everything, we can actually use that. And why am I actually saying it so confidently? Because in that one device, you have several other things. Very simple stuff, right? If it is millimeter wave, if it is multiple access, but if the device can tell you that, based on this guy's behavior, he is going to the tea table after this, that AI engine is actually helping you estimate the channel which follows you, right? Simple techniques like this will actually ensure that, A, you have better estimates, B, you are able to actually do a lot of other optimizations as well, right? So that's where all these things actually come in. I will have to go a little fast. I'm actually not seeing those ladies because anyway, we are missing tea time, right? So you can rest for now. So we are focusing on the beam management related problem, right? How do we actually use beam management to effectively parameterize some of this stuff and then take it to the next level, right? Since my focus is on something else, let me just try to pass it on a little fast. So this is the same story, right? That the moment a lot of these vectors are available, which can actually give you samples and start doing it, a lot of these things are done, right? And Qualcomm has a few of these tech marketing people, who make fancy slides, right? And I don't want to take to the pitch, but get to the message that, this is what we want to be conveyed, right? What you are dealing with, it's a handset. It has a modem, which has a few set of capabilities. There are sensors in your device, which actually helps in you doing a lot of stuff. Your gyro, your Bluetooth, short range sensor, several all of these things. Try to mix these parameters, and then the idea is to basically match to a Gini estimation, right? You try to map one into the other, you have a problem in there. How can I actually do a better channel estimation, knowing a sub-6 narrowband channel and then trying to fit it to a wideband channel? Or can I actually now use it to actually measure a millimeter wave channel, right? So these are all the things that actually come up, right? But then this particular slide I will emphasize because, if you actually go to the Qualcomm website, you have a lot of these results also listed up. So this is about how AI helps improve AI millimeter wave channel estimation, and gains to the extent of about 80% is possible. Just because you are able to have that best the exact sample of the channel in there at the right time. Of course, it's like a controlled experiment because it's like outdoor, and then the antenna is like 30-40 meter away, and then you're able to track it. This was done outside India where people don't jump into each other. So, but you get the idea, right? That AI is a must. The main thing I wanted to discuss today is about its application in standards, right? So there are two aspects which get into standards. One is like fundamental blocks, which will have to be part of the device, part of the network, and then part of other things that need to be there. And the next key thing is about those information exchanges that need to happen, right? And it's not like 3GPP or some single standard body focuses on all these problems. No, we have multiple bodies that actually work in it, right? And I have listed down 5 of them where we actually participate. There is ITU, which deals exhaustively with use cases, and they create reports on how are these different use cases being used in the AI field, right? Again, I hope that I'm not confusing generative AI with communication or AI, right? Because generative AI is like helping you create artificial data from nowhere, right? That's like that magic Buddha. You have some data samples, you try to actually do something else. Here it is like, how can I actually make my communication equipment effective by doing some optimizations to that part? GSMA, which is, I would say, the operator forum, where they define that, this is the network, this is the sort of optimization that needs to be done. Now, how do we actually parameterize this problem and then try to do something effective on top of it? NGMN and then 3GPP, right? So the list in here to basically summarize what is the work going on, what was the release, and how it is done. The last 2 slides, which actually matter to me, is where Qualcomm is actually focusing on, right? I emphasized a lot on the device. And then speakers before me, they actually told that, a lot of computation actually happens now in the RAN, right? Let's go back to the same problem. If it is a Gini channel I need to mimic, how am I actually going to send it back to the cloud, right? I also told that, AI is like a great tool, right? So it's basically the same thing. I'm hiring a Michelin star cook or a chef to basically cook for me. But at the end of it, that guy is actually going and eating away 80-90% of it, right? So all this fancy thing I put in the device, it's actually consuming 80% of the power. or it is actually taking away 80% of the compute resource or whatever, then what's the point in it? So the consequential research also happens on how to actually simplify some of these elements, right? So our philosophy is, yes, there is cloud, right? So for example, even your Alexa or some other tool you are using today, what happens in there is the moment you speak, it gets sampled, goes to the central server and then come back. What is the fun in that? Right? All the time going to tell us, Alexa, play X. You could have actually sampled it here and do it, right? But today we are not able to do that, right? I'm just again simplifying it and then picking up a very easy problem, but that's the idea. Can I actually offload a lot of these things at the either at the edge or at the device and then try to do stuff out of it, right? So this is on the main functional block, which goes to the RAN, which goes into the device, which goes into something else. Next thing is about the messages. So what it's not like 3GPP hasn't started to do anything on AI. They have done two set of standardization activities on it. The first one is what is called as on 5G, where we did overlay AI/ML, meaning there's a good RAN, there's a good UE, they don't speak to each other. But then if you are able to do some custom proprietary implementations, you try to get that part, right? So it becomes like an afterthought during that time. When they did 5G advanced, they realized, okay, this amount is not good. We should try to basically figure out, how to improve this situation, right? So they introduced handshakes, very simple handshakes. And then, that's now part of what is called as cross-node AI/ML. But there is a catch. You'll be able to leverage that only if the infra changes to 5G advanced, not if you have the old it, or you try to basically mimic it in a proprietary manner. What is changing in 6G is you are trying to make it native, meaning by design, when you start the process of 6G standardization, AI need to be part of it, right? So that's why you saw speakers before me who didn't have AI in the title mentioned that AI is a key thing, because it's part of it, it's fundamental, right? So once you start doing that, then you try to actually mimic a lot of things. So the question is, what sort of messages need to be exchanged? What are the parameters we are talking about? How do those parameters help? Is it like essentially needed, or is it like proprietary information being passed on? So those are the things we are trying to answer in the 6G, right? And that's where some of the research from my team is actually also going on, right? With that, I conclude. There's no 50 slides, so thank you.
Thank you. I request you to just be here. I have 3 announcements. First, if you have any questions, please feel free to talk to the speakers of lightning talks in the tea break. And for the online participants, I request you to leave your questions in the chat box so that we can forward that to the speakers. Second announcement, after the this is where we conclude the first set of lightning talks, and now we have a lightning memento distribution. So I request all the lightning talk speakers to come over to the stage to receive the memento. I request Dr. Naveen to hand over the memento to all the speakers. So since she's already here, maybe we can start with him. Vinay Srivastava. Vinay is here. Yeah, please. Thank you, Vijay, and sorry for the. Thank you. Yeah, okay. Ram Kumar Sharma. Oh, sorry, Pranav Jha, please. Yeah. Thank you. Ram Kumar Sharma. Mahantesh. and Neha Sharma. So and the third and the most important announcement is now we will break for tea. So, so let's gulp the tea and then be back here by in 15 minutes. We'll start 4 o'clock sharp. Thank you.
Hi, can we start off?
Yes.
No, I'm not talking. Okay. Maybe a final call. Okay, so welcome back. I think we have come to the third leg of this day, actually. A lot of interesting talk has happened, actually, and we'll try to conclude with more lightning talks, actually. So first off, this series will be led by Anand, actually. So Anand, from CDOT, he will present his talk. A big round of applause to him.
Thank you. Am I audible? Hope so. Yeah, good. So let me speak from this side. People are speaking from that side. All day I'm sitting there, I can't see properly. So I'll speak from this side. Okay. So first is the motivation of the talk. Okay. PPT will get it anyway. Material will get it anyway. So the motivation of the talk is to introduce you to an IEEE standard, a diamond in the rough, actually. So people who start 6G don't think, okay, there's no any standard existing which I can use or enhance, or this is an existing standard in the sub-terahertz band, something starting from 250 all the way till 320 gigahertz. Okay, so see the range. Okay, no longer milli, no, we are way beyond that. They're talking in the order of 250 giga to 320 giga. That is 70 gigahertz of bandwidth available, and you have to imagine the size of that spectrum. Actually, it's very difficult to imagine also. So I introduce you a diamond in the rough, and let's see if we can enhance this, or can we collaborate together, come up with an IEEE standard in the next 2-3 years, which is a polished version of this, which meets one of those 6G requirements specified by ITU. Okay, so that's a target. Okay, so in your head, you're thinking how to improve this while I speak. Okay, so this is the baby version. Let's go. So there are 3 parts of it: the D, E, and F part of the standards. So I'll introduce the first part, the D part. The D is the file layer, the E is the MAC layer, and F was just a 1-page standard. So the IEEE people wanted, some people wanted to request, say, okay, take this whole standard as it is and bring it to millimeter wave. That was the last. This is the F standard, which is the latest one. It is nothing but moving the band from, I told you, somewhere in the order of 250 giga to 320, all the way down to 57 to 71 gigahertz. So this standard doesn't matter much. It's just a 1-line standard, actually, 1 page. That's it. So the remaining 2 are good, actually. I highly recommend you to read through this, hardly 70 pages. It will take 1 day if you really want to study. So this is a diamond in the rough. Okay. So let me introduce quickly the diamond itself. So this is a diamond. Okay. So the IEEE group has identified 4 use cases for this and made 3 assumptions. Very simple, straightforward assumptions. First part, direction of antennas at both links are known. Very tough if you want to do beamforming and nothing like that. Interface can be mitigated by proper link planning. Gone. All the obstructions are gone now. No fight exists for access. Oh man, no. Everything is straightforward. Okay, you always start from basic principles always. So that's what my professor used to say. Assume something which is very simple for you to do, basic step. Then you remove the assumptions one by one and make it tougher and tougher. So let's start with the basic question which I showed you. This is the basic question. So there are 4 use cases identified. You could identify 100 more things. Front hall, back hall. This is known to us in data centers. This is to remove those. If you go to a data center, I have been to in my office, lot of wires, lot of cables, messy cables. You label them at year 1, 10 years later, you forget what that label means. So this is for that domain. Server-to-server communication without cabling. Intra-device upgrading from I2C, SPI, and can you go to terahertz band in that domain? And chaos downloading, this is again not so much, but from Japanese point of view, it's very useful actually. Okay, so I explain again, diamond in the rough. Please pay attention. So as I told you, the bandwidth is from 250 to 320. This looks like Wi-Fi, no? If I show you a Wi-Fi diagram, if I don't show the access, it looks like, oh, Wi-Fi channels. This looks like Wi-Fi channels, yeah. So you have all the 4 options, starting from multiples of 2.16. So the minimum bandwidth you're starting with is 2.16 gigahertz. So can you imagine the throughput? Okay, so you forget everything in the 6 gigahertz. You're worried about fighting Wi-Fi, but no, forget everything. Go this domain first. Be happy there. You have enough bandwidth, no obstacles, angles are known, everything is known. Now you polish it. Then we will see whether you remove one by one, and can you bring it back to FR1 and FR2. Okay, so think that way. So let's wipe the white rubber and wipe out everything which you know, and think about the free world which you are right now here. Happy world. 2.16 is more than happy. You can watch YouTube. Yeah, I know. I'll finish it off. I have only 5 sites. Okay, so these are the flow graphs, 4 graphs. Yeah, good to know actually. So 4 graphs about throughputs, and we are able to achieve more than 100 Gbps. 2017 standard is achieving 100 Gbps. That is 5 years back. So no challenge. This is a Mac. Very simple Mac. In fact, we should say baby Mac. Hello, hello, hello. Anybody is there? So asking this coordinator. He said, yeah, I want to join with you and chat with you something. Okay, chat with me, talk to me. Okay, enough, done, bye. That's it. The Mac is the simplest Mac ever. RLC Mac, you throw the book away. The 300-page document which you 3GPP you study, I used to study, it used to be a nightmare debugging it in Wireshark. Throw it away. You go to this simple concept. Okay? So what more simple? Diamond in the rough again is a baby, okay? He knows nothing. What does he know about Mac? Baby fellow. So there are people who wanted to solve this problem. So there was a project called Thor. Can you think why they made Thor? Because THR is inside it, okay? And there's a nice cool arrow, hammer, Thor sample. So this is a finished project already. They showed 300 gigahertz of link bandwidth, and they could show POC in 2022. Finished. The project is over. And this demo is available in this EU project. And now you may think, oh, I missed the bus. Oh, I could not contribute it. So this is it. This is where you can contribute now. So Terameta. So you introduce a little bit of meta services, that IRS flavoring a little bit, because okay, you don't want line of sight, you want to have a reflector in the middle. Take away one of the assumptions from that original 3 things which I showed, and that is what this is. This is active right now. People are requesting for participation. You see if you can contribute in this. Even if you can't contribute in this, please join the mailing list of the IEEE 802.15.3, and you will get mails, and I'm one of the members. So we work, yeah. So that's it. Thank you. Please take this diamond in the rough and make it. If you want to collaborate, talk to me later. Thank you. I finished.
On time. Any questions for Anand? Okay, no. Oh, okay.
Hello, am I audible?
Yeah, you're audible. You are to hear us, Rashmi?
Yes, yes, yes. Thank you. Can I share my screen and it start?
There is a slide here.
Is my screen visible?
Yeah, the screen is visible.
Thank you. Hello everyone, I am Rashmi Kamran from IIT Bombay and I will be presenting today our proposal towards Green 6G. Energy aware
We'll
service
start in
delivery.
2 minutes. We are
Rashmi, 2
having
minutes
some.
you give us, yes, just in the logistics.
Okay, that's fine.
Rashmi, are you able to hear?
Yes, I can hear. Am I audible? Hello, am I audible?
Rashmi, are audible to the online participants.
Oh, so I mean, I should wait.
I think you should wait. Some logistic problems going on.
Sure. Thank you.
You can start off, Rashmi.
Okay. Thank you. So hello everyone, this is Rashmi from IIT Bombay and I will be presenting our proposal towards Green 6G, Energy Aware Service Delivery. So before I start, I would like to highlight the motivation behind Green 6G. With increasing demands in communication and computing services for huge number of users, increasing energy consumption for mobile networks has been a concern. As per GSMA report, the total annual emissions of the mobile sector is approximately 0.4% of total global emissions, which may be doubled by 2025. The objectives taglines like breaking energy curve, enabling net zero indicate the efforts of mobile industry in this direction. Additionally, users are now more aware toward environment and are even using apps to evaluate the impact of their actions on emissions. However, motivations like climate change, global energy shortage are not new for 6G. Impacts on energy usage with many new use cases in 6G need to be taken care of while designing 6G to make it green 6G. There are many efforts and approaches have been applied in the existing mobile networks which are intended to satisfy user experience and achieve energy efficiency at the same time. Energy saving modes are implemented in some network elements. For example, cell on-off feature in RAN to save energy. Partial monitoring of energy related parameters is enabled in the network to facilitate AI/ML algorithms to optimize energy efficiency. Even discussions on considering energy efficiency as service criteria started in 3GPP for release 19. A lot of research work is available towards energy saving in mobile networks. Now, let us focus on some of the missing aspects. There is no provision for exposing energy usage information to users and verticals. Energy consumption is not performance criteria. There are no methods implemented and no exposure about energy source related information. Rack selection based on energy consumption is missing. As for multi-rack scenarios and even predicting many types of racks in future, it can be useful to have energy awareness in resource allocation strategies too. So, our way forward is Green 6G, our proposal with our energy awareness built into its design. So, the broad level objective is Green 6G system, a coordinated solution at both user and operator level from the perspective of energy consumption by considering availability of energy saving resources and user awareness. In the direction of achieving this, our proposal is to include energy information exposure and monitoring at service level granularity in Green 6G. In the following slides, we will highlight the required features and challenges for Green 6G design. Now, we move to proposed features for Green 6G, which are categorized into these 4 dimensions, which we will next deep dive into each of them. Energy monitoring with granularity. Green 6G can facilitate energy consumption monitoring at granular level. We try to visualize this idea here in this figure. Energy monitoring per user, energy monitoring per service, energy monitoring at slice level. Energy aware network functions can be aware of energy source type, whether it is conventional or renewable. Battery symbol here shows total energy usage and also energy volume provided by both types of sources. So ability to identify energy source used is also a feature for Green 6G. Exposure of service level energy usage to users and verticals is another feature. For example, as shown here, user is aware of green service. User knows very low energy is needed for this green service and can be made available through renewable energy sources only. But it will give them low QoS. User is also aware of red service, which needs more energy and can be served by non-renewable energy sources with high QoS. Now, in this set of features, there can be service subscription options with multiple energy levels and associated QoS. Example of such services are shown here. For example, partially green service. It needs very low or low energy with very low or low QoS, and this energy can be provided from only renewable sources or both. Yellow services can be combination of red and green services. Idea is green user must be free to choose a green service while knowing about the trade-off in terms of QoS. We can attract more users for such subscriptions by adding a feature of energy-based charging. So, users who are not environmental conscious are also in. As we know, nowadays AI/ML enabled service options are available in the network. For example, for many things, load balancing, positioning, and many more. What about the energy consumption for these AI/ML algorithms? So we propose green optimization as another feature for Green 6G. Energy-aware algorithms can be designed with energy exposure and monitoring available in Green 6G. Now, we present few ideas which can be incorporated in Green 6G design. There can be a dedicated energy management function, EMF, which can coordinate with user regarding its requirements and inform user's choice to resource management function. It also exchanges energy-related information with energy-aware network functions. It can be aware of energy consumption model with joules per bit mapping for energy-aware network functions. As a result of energy-related coordination and exposure in the network, an energy-aware service can be served to the user. We will now look at some of the challenges and benefits of adopting Green 6G. I understand including such features in the network will have many challenges. So intentionally, I have used this picture to convey the same. Some of the challenges will be consent for coordination between all stakeholders, users, operators, energy providers. Coordination and interaction between network elements within the network. Discovery and selection of network elements for end-to-end service based on energy-related criteria. Real-time exposure of type of energy sources can be a challenge because of dynamic change in availability of energy sources. Can we get the support from energy providers regarding exposure of energy source type? That is another issue. Overcoming these will not be easy. Seems not to be feasible also. But we have to start including energy awareness into initial stage of 6G design. So after discussing challenges, it's important to look at benefits as well to encourage ourselves in this direction. Green 6G can be a big technical tool to handle energy-related constraints in mobile networks. It may help us in achieving our goal, connectivity for all and everywhere, as few places are still unconnected globally due to limited availability of energy sources. It is a revolutionary step towards controlling carbon footprint of the user while considering their choice. In conclusion, we should take energy exposure and monitoring related requirement into consideration while working on 6G design so that 6G eventually evolves into Green 6G. Thank you. Sorry, I was not able to physically present, and my thanks to the organizers for giving me this opportunity to present virtually. And my colleague, Mr. Pranav Jha, is physically present at the summit, and we are open for any further discussions and suggestions. Thanks again.
Thank you, Rashmi, for this talk.
Can we have one question from the online participants?
Yeah, one question we can go through.
Yeah. So hi, Rashmi. Can you hear me?
Yes, I can hear you.
Yeah. So Rashmi, the idea looks very appealing and great, but since morning we are hearing up so many talks, and it talks about AI, ML, intent-based networking, service orchestration. So it appears to me like it's very, very complex, things or services or system, running behind. How the price mechanism and, you can say the price and the resource, constraint you can apply for the network aware function, because I don't know if I'm, using your, you can say this video, how much is the, backend network and the service and the cloud is actually provisioning these services to happen. So how this will be feasible, like your idea? Thank you.
So thank you for your question. So frankly speaking, yes, It's really, really, very tough. But the thing is, what I feel like when we see at a service, we concentrate on the QoS parameters like latency, data rate, and many more. So, like we want somewhere like energy related parameter let into those performance parameter from the small start, and then certainly this really need a big change in the whole network design, because for everything we want now energy should be measured. We should know which source will be there. I mean, certainly it is a seems to be very, very big task, but somewhere we have to now think over it and try to put some techniques at hardware level, software level, everywhere, so that energy awareness is there.
So, I mean, I
Correct.
have two comments to say about it. Like, one is like, even bookkeeping of these things will take energy and services more than whatever we are doing it now, because we are supporting the things. Second thing is, will the market will be ready? You know, the market always look for
No.
profit and all. Yeah, thank you.
Please, due to the
Hello.
Yeah, thank you, Rashmi.
Oh, maybe we can discuss, yeah, because 3GPP is also working a lot in this area. So there are some technical things which I can share with you, maybe in detail later on. Thank you.
Hello. Hope you can hear me. We're getting an echo from the room. Yes. Can I start presenting? Okay, great. I will share my screen and start presenting. Okay, hope you can all see my screen. I'm not able to see any chat box, so if you can't see the screen, please do speak up. Thank you very much for the opportunity to present today. I'm Balaji from Keysight, and I'm presenting, based in the US. So good evening to all of you, and it's morning here. And I'll keep my talk brief since it's towards the end of the day for you. The talk is about the harnessing of digital twins for the 6G life cycle. And this is becoming a very important aspect for design of future generation of communications, including 6G. And this is about the tools and the methodology that will be required as we go about this process for 6G. And one of the main reasons is that the complexity of the system, as we just heard, in the various talks, is increasing exponentially, and the number of interactions between subsystems is also exploding. And in such a world, the design of any one subsystem has to exist in coordination with all of the other systems and has to take into account the real world environment in which it's going to be deployed. And hence this notion of digital twins has become very important. And what is a digital twin? It is really a virtual model designed to accurately reflect a physical object. And one could say that, okay, we are talking about a simulator or an emulator. But one of the key differences I want to point out when we talk about digital twins, there are a few different axes. But the main ones are basically the ability of this solution to coexist with the real world. That is to say, it's not an isolated box, running on its own, but that it is able to interact with the real world environment and also able to have bidirectional communication with this environment. That is, it's able to provide both the input into the environment, but also take input from the environment in order to modify its own behavior, in real time, in order to mimic the outside real environment in some way. These are some of the attributes that make the digital twin somewhat different from a conventional, what we call a simulator or an emulation environment. So, and the goal of a digital twin is to actually exist through the end-to-end process of the design life cycle, all the way from design towards test and evaluation, towards deployment, and ultimately post deployment maintenance analysis, fault detection, and so on and so forth. There are a few core attributes. These include composability from various models. They could be software pieces, they could be hardware pieces, or combinations that are part of the digital twin. The speed of this digital twin should be real time or faster, and it should be scalable to the scale expected in a real world deployment. It should be able to capture the dynamics and the behavior very accurately to the level of accuracy required, and I'll get to that in a future slide. And finally, it should be very heterogeneous, incorporate any different type of network and communication system necessary. Um, and there are different types of digital twins. It is not to say that the digital twin should be a complete clone of the real environment in all possible ways, but there are different types of digital twins that are deployed for different domains. An application digital twin, or a network digital twin, or an RF twin, or an environmental twin. And the reason these are different is that they are able to highlight and accentuate different aspects of the functioning of the network in full fidelity, while abstracting other layers and other aspects that are not essential for that one particular type of testing. This is in order to keep the complexity of that twin to a manageable level, to keep the computing to a manageable level, and also enable scaling to a much larger network size as required by a particular use case. It is possible for that certain use cases, only a few cells is sufficient whereas in other use cases, you need to, model an entire region of the country, perhaps. These are all sort of the various dimensions of the digital twin, and this is becoming a widely, recognized, methodology for the development of 6G systems. There are, discussions about digital twins happening, for example, right now in the ORAN's next generation research group, and in various other forums across the industry and the standards environment. Just to show one example of how a digital twin can work, one of the key applications that are being postulated right now is to enable the study of AI-based optimization, especially RAN optimization techniques like optimized beamforming or multi-user MIMO, or new 3D positioning mechanisms, or energy efficiency that we just heard about, and on, including an AI native air interface. These are very complex features, and it is not advisable to test them in a real environment for the very first time. And most of the initial testing, development, optimization is done in a digital twin environment. But one of the important aspects here is that, in this picture, as you see, the digital twin also includes the hardware in the loop aspect. That is to say that digital twin can consist of many digital or virtual instantiations of modules or subsystems, but there can also connect with real life base stations and UEs or other subsystems, including the corresponding, let's say, an AI ML application living inside, for example, RIC X app or R app, for example. So just to, this is a very large topic, impossible to sort of touch in 10 minutes, but I wanted to give an idea of what it could look like by showing a very brief video of a digital twin. This is a Keysight solution. What we are showing here is just to go back a little bit, a Singapore harbor with an NTN network that includes 3 G-Node Bs, a traditional G-Node B, as well as a high altitude platform and UAV, and 20 UEs, which includes 10 vehicles on roads, but also 5 vehicles that are ships, and 5 pedestrians, and there is network slicing involved across these as well. So this is showing sort of in real time. I hope you can see the video playing. Basically, it shows the movement of the NTN layer, the non-terrestrial layer, the UAV vehicle moving. Correspondingly, there are cars and pedestrians and ships also moving and receiving traffic in real time. And we are actually able to show sort of various application behavior in this scenario. This is just a very small slice of what a digital twin can do. It's not simply to display a certain emulated performance, but in fact have real life feedback from a system back to the digital twin and then back to the real world. When we talk about energy efficiency, for example, we are able to, for example, collect energy consumption profiles from many UE models in real world, and then use that models to create energy consumption models that then we transfer back to a digital twin, and then use that to show or analyze how it would perform when deployed in a, let's say, a real city with hundreds of users. What would the energy consumption profile look like? So these kinds of things are already possible, and these are necessary, I would say, in studying the complex use cases and that are coming up for 6G. With that, I will end my talk, and I thank you very much for the opportunity.
Can I ask one question?
Yes, sure.
Yeah, so I'm Dr. Bhupendra Kumar from IIIT Vadodara. So you talk about mimicking the environment using digital twin, and you talk about some certain component of Open RAN, ORAN actually, the XApps and RApps. So how actually the digital twin is taking the data from these kind of component to actually simulate or emulate kind of behavior, from NTN or from say suppose if I'm taking a GPU from NVIDIA and that's using Siona, they must be doing something, that providing feedback to the digital twin. So how it is happening, like, and where we can find the pointers to actually explore more in this area. Thank you.
Sure, we can certainly talk offline and have further conversation on this. But the way the digital twin, in my opinion, in this particular use cases you brought up, would act is that it would have a legitimate ORAN compatible interface, either an E2 or O1 interface in this case, to an XApp or an RApp. On one side will be the actual sort of this AI optimization, XApp or RApp that is, ready to be deployed in a commercial sense. But then on the other end, there is a digital twin of the entire network that will stand in for the network. So the emulation is happening inside the digital twin environment, but it is talking in a real sense with this XApp and RApp through this E2 or O1 interface. So that's one, very possible and very almost, currently existing mechanism for testing, and we are, already participating in certain plug fests in ORAN that are going down this path.
So it is happening with the same TTI, like it is happening in the real time,
That
or
is correct.
okay.
That is correct. It has to happen in real time. So for certain purposes, you can slow it down by a factor of X, small number. But for the most part, the requirement is that it has to happen in real time for the purposes of that particular application. In a near real time rig, that could be that you have to turn around and provide the corresponding stimulus response within the 10 millisecond window, or whatever, and then in a non-real time, it could be in the order of a second or so on and so forth. So the requirements are specific to those applications, but within those requirements, it should be real time, quote unquote. Yeah.
Thank you very much.
Okay.
I think with this, we will end our lightning talk. And it's a nice, interesting one. So we go back to our last keynote speaker, Dr. Ashutosh. So Dr. Ashutosh is the chief 5G strategist and fellow at Johns Hopkins, actually, and in the applied physics lab. And he also is the founding co-chair of the IEEE Future Connect, who is also a participant for this Bharat 6G. Dr. Ashutosh, please have it for your keynote.
Got that? Yes, good. Right, folks can hear. Right, no, not this, the second one. All right, so let me, when the slides are getting ready. So first of all, I'm so happy I could attend in person. I think there have been a lot of meetings I have been attending virtually. Thank God I was able to do it. And like to thank Anindya, ComSoc chapter, Bangalore section leadership, everybody who made it happen, right? Got it? No. I copied it. Just see. It's got version 2. It says version 2. Didn't you copy it? Somebody copied it.
Yeah, open. It's already open.
No, not that, not that. I had to change that. All right, V2. Just. I think I made sure we copied that. All right. So let me see if I open that. It's called Asutosh. Look for Asutosh V2. Yeah. Got it. V2. There's a V2 because I had to change that. Yeah. Wait. No, not that. I don't know which one. Where did it go? What did you copy? You copied that, right? Yeah. Let's find that. I think we copied that because this is not it. All right. So why don't you figure out? Then I'll just start talking and we'll find the slides. So when we started talking about 6G Summit, just to give you a little background, I'm also a ComSoc Communication Society volunteer, currently serving as member at large. So in 2015, we started the first 5G Summit in Princeton section, 2015. And we had several 5G summits after that. And so far we have done about 90 of those around the world, right? And many of them have taken place, at least 3 or 4, right? And your tutorials, I know Nilesh was here. We had the industry day here as well. And now when you're talking about IEEE 6G Summit, so that was the first one in 2015. So I was talking to Anindo and Alok. I said, let's do the 6G Summit. And if you know IEEE Bangalore section and Princeton section, we were the sister section agreement. When Ramakrishnaji was the chair, I was the chair for Princeton section. And yeah, that's it. So I'm so glad the first IEEE 6G Summit is happening in Bangalore section. So really, let's give a big hand for that. Yeah, because there have been many 6G summits happening around the world. But they're not really open, right? Sometimes, things like that. So in the spirit of bringing the new generation, new technology, I'm so glad it's happening. So what I'll do, I had what is the clicker? So I had prepared a slide deck before, but I realized, is there a clicker somewhere? So I realized that there are some people who are interested to know a little bit of what's happening in INGR, the Future Network, where I'm one of the founding co-chair, and now the technical community. And we also have done something more to that within IEEE. We created an innovation testbed, 5G, 6G testbed. I don't know if Tech Mahindra people are here. They may be coming. So we got their help. We got some funding from IEEE. And now we are building a 5G, 6G innovation testbed. I'll talk a little bit about that. And you'll see how people around the world, from the academics, industry, startups, who do not have their testbed, they do not have the capital to do it, they can log in and they can just do their stuff. So, for example, I teach a class and Johns Hopkins on 5G. My students keep on asking, you are professor, you are teaching all about protocols, arrows, this, that, equations. How do I know how 5G actually looks like? So things like that will be useful, right? So I know I have 30 minutes, but I'll be quick. And the second part of my talk will be a little technical. I wanted to give a big security talk on 5G/6G, whatever, but I reduced that a little bit. So before my job at Johns Hopkins, I used to be at AT&T Chief Security Office for about 6 years. Before that, with Bell Communication Research, I also had a cybersecurity CTO for a company, small company of 200 people. So just to give you an idea, this is an IEEE talk. It's important to acknowledge some of the work people have done in the past, right? So what you're showing here is, many of us have taken data communication class, and it's showing the evolution of the communication, starting from on the old days, people used to send with pigeons or horses, and then came the, telegraph, electrical telegraph, optical telegraph. Then we all have been through the PST and circuit switching. And then 1969, the first packet switching, Professor Kleinrock, Binchoff, and Bob Kahn, they sent the first packet from UCLA to SRI, right? So a lot of interesting things happened. Then we had a lot of things that happened after that, like Ethernet, right? Then cellular started around 1990s. And now we are in the era of next G. We are calling it 6G now. Someday it will be 7G, whatever, right? But there's a convergence network. I think a lot of people talked about convergence. So it is important, not only cellular, there are other things also. So we have to keep in mind how we can take advantage of the convergence networks. In fact, last year, some of you gave a talk. We had an XG summit at Hopkins Applied Physics Lab because we just didn't want to call it 6G. But it's probably good to call it 6G now because we're in the 6G area. So this is just to make sure when we're doing any research or anything, we like to make sure how it's going to help the community. So the slide you are seeing here, how different parts of the society can benefit. It's almost like a smart city type. So people in the home, ITS, like transportation system, medical system, right? They have different type of application they need. Some may need low latency, some may high bandwidth, some may need bursty traffic. So we need to evolve our communication infrastructure so that it can accommodate this kind of application. So it is always driven by the application. Then you have the KPIs. I think there are a lot of interesting talks this morning about how ITU gives the requirement, 3GPP gives up the specification. And every standards body, they have their own contribution. Like IEEE, we are doing on the Mac layer. We also do a lot of optimization algorithm. So it's a kind of an ecosystem. So I wanted to make sure we all understand, because 10 years from now, the application might look different. All right, now you have seen this slide already. I just want to make sure, because you're focusing on 6G, let's talk about cellular a little bit. Again, historically, right? So this is what is happening. Starting in 1980, it was all analog. And every 10 years since then, there has been evolution of the next generation cellular network. And some of you may know, like there used to be something called 3GPP2. I personally was involved there when I was in Bangalore Applied Research. Around 2008 and 9, I think this kind of folded. This was Qualcomm champion technology, pretty good, right? But then LTE picked up. And finally, EHSP was deployed a little bit. We never saw the birth of EMB, or maybe it didn't get deployed. Everything got LTE. I think there was discussion about WiMAX this morning. All those things are still were being deployed. I personally have tried WiMAX when I was in Telco Research to install it. And then we are in the midst of 5G, and 6G is coming, right? So I just wanted to highlight. So while 5G is being deployed, we have to keep on doing research. I remember the ALU 6G summit, they had it like 3 years back. And the person from Nokia came, he said, we still haven't deployed 5G, but we have to look ahead, what's happening 10 years from now. So the research community, the students, people who are doing PhD, they have to start thinking. It doesn't happen overnight. It's not a Y2K type problem, right? So we have to work on it. So this is the right thing we are doing today as an IEEE community or any other community. We are doing the research, trying to figure out what is the new application, what are the new challenges. So it needs everybody's hands, right? Students, startup, companies. So with that spirit, another thing we should not forget, I think we talked about Wi-Fi. There was some IEEE related slides, right? I think today also lightning talk. So this is important that we should not forget that there is always a coexistence. And I was talking to Professor Anurag Kumar the other day. We have this Future Network World Forum coming up, and I requested if we can do something about, here's a lot of Wi-Fi work. So it is important, the research community, while we are doing on 6G, 7G, etc., we should not forget the 802.11, right now it's Wi-Fi 7, 11BE. I'm personally involved a little bit. It has to coexist. So there are a lot of interesting research topics. We are not going to talk about 11BE or Wi-Fi 7 today, but if you are coming to Future Network World Forum in Baltimore or listening remotely, you'll be seeing an interesting panel there. All right, so with that, that's kind of background slides, right? So what is IEEE doing in the area of future networks or 6G, 7G, whatever, right? So there's an 802.11 working group. They are developing the new generation of Wi-Fi. But at the same time, what I'm showing here is the Future Direction Committee. And you might find your own niche interest in any of these, right? Some of them are blockchain, smart city, smart grids, and you might have been involved in many of these, right? So this is a very interesting thing that actually started around in 2009 or so. Roberto DeMarca, he in fact started this. So anytime there is a new area, we start baking up. It's like you bake up, right? A new idea, it runs for 5 and 6 years, and then it graduates and becomes a future technical community. So that's what happened to us. So we started this as a 5G initiative initially, 2016. I still remember Garrett Fetwise from 5G Lab, myself, Rob Fiss. In terms of headquarters, we started talking, hey, 5G is coming, what should IEEE do? So we said, okay, let's call it 5G initiative. Then after 1 year, we said, yeah, no, we should change, because 5G becomes 6G, then should we call it 6G initiative, 7G initiative? So we called it Future Networks Initiative, and we kind of stayed with that. So in the IEEE side, what we look at the actual KPIs, the real, latency, this and that. So 5G, 6G, 7G, these are all commercial things, right? Depending on which release, 16, 17, 18, okay, this 6G is done here, 7G is done there, right? So while we see what's happening in 3GPP elsewhere, IEEE also has to look at the future. So that's why we call it roadmap. And the second one is innovation testbed. So this is, did I lose this? I had an agenda slide. Oh yeah, I lost that. So I wanted to, so I'm just want to make sure we are being structured here. So Future Networks Technical Community, which is part of the future direction. And then INGR, I'll speak a little bit about that, this roadmap. And then 5G, 6G innovation testbed that I spoke about. I'll talk a little bit about that. And the last one will be a little bit technical, right? I wanted to make the whole talk technical, but I thought it's better that you get to see how you can contribute any of these, right? Future Network Technical Community, how can you be an author? Now, all the INGR roadmaps, 14 of those have been published in IEEE Explore. Every year we have a new edition. If you want to contribute to the next edition and be listed as a co-author, you have an opportunity to do that. And I'll talk about some of those briefly. The innovation testbed, that is, I was telling before, I won't repeat that. I'll talk about it, how you can get involved. I'd like to thank Tech Mahindra folks for helping us to integrate, and new initiative committee from IEEE giving us the funding to do that. So this is going in at speed. All right, so let me go back. So that was my agenda slide. I somehow missed it. So we were here. So I'll talk about future networks, then innovation testbed. We just graduated from Future Direction Committee. Now we are the technical community. In a way, we did our job. They think we did a good job, so they promoted us. We graduated. Now we have more responsibility. As when you graduate from colleges, go out and do work, you have more responsibility for the society. So we have to do a better job. Anyway, so this is what we are, a Future Networks Technical Community. Right now, there are 9 societies, paying societies. Communication Society is the primary one, managing society. There are other societies who are listed. And they're the financial sponsor, right? Because we are on our own now. And the other societies, they can be technical, they can, provide funding later on. So there are many things we do along as part of that. We have publication working group, standardization, education, conference. As part of publication, we do tech focus. You can publish your work in progress paper and publish. And we do a lot of events. Future Networks World Forum. In fact, the third 5G World Forum was supposed to take place in Bangalore. But due to COVID, we couldn't do it in person. Otherwise, it would have been a great event. But many of the audience here, they were organizing committee members. We did it virtual. Connecting the unconnected, Dr. Sudhir Dikshit and myself, we started this about 3 years back. This is the 3rd year, talking about digital divide. It has picked up real steam. I know Sandeep and a few other people, Praveen and Naveenji, and they're all part of it. So this is going on. Then first responder tactical networks, many workshops. Most of them are free. We try to make it available to the rest of the world. The research and education side, this international network generation roadmap, I'll briefly go over that. E-learning courses, webinar, tutorials, you might be seeing a lot of those happening every month. A lot of tutorials, even Bangalore section has done it. So what happens is, this is how it is structured. Right now, there's a steering committee consisting of 9 society members. Then, as I said, there's the education working group, publication, roadmap, conference, standards. So the standards working group, this is a great opportunity to create a pod, the project authorization request, like pre-standards. So you back up some new ideas, like I think Professor Abhay Karandikar and Pranav, right? They have done that. Through PAR, you go to the next level, so the standards get developed. So this is a good opportunity for anybody, any student also, right? So you don't have to pay any fee or nothing like that. In fact, there is an Open RAN Summit happening August 9th, followed by something called RRSA, Rapid Reactive Standards Activity, where we invite proposals from the rest of the world. You provide, and then let's say you got 20 proposals, maybe 4 and 5 or 6, take the next step. So Purba, you work with Purba. So this is a good opportunity. If you still have an idea about RRSA, August 10th, we are doing it in a hybrid mode. Please submit. But there is a Open RAN Summit also happening in Johns Hopkins Applied Physics Lab. And there are other things. Craig Polk used to be Brad Closure. Now Craig is our new program director for Future Network. This is the website. If you want to, there are lots of information out there. We keep updating. These are all free. Any new events coming up, seminars, all those you can see there. So just want to dwell with that. We in fact got an award from IEEE USA, Citation of Honor, for the work we did for IEEE roadmap, right? So what is the roadmap? The roadmap is this one, right? So as I was telling, we don't know when 6G will come, when 7G will come, when 8G will come, right? So our job as researchers or industry professionals, we need to see 3 or 5 or 10 years from now, how things are going to look like. What are the current challenges? What solution you need? To get that solutions, what kind of KPIs need? To get the KPIs, what do you have to change? Do we have to change any frequency on the millimeter wave side or edge computing or security, right? So if we do that, at some point you will see 3GPP or anybody will going to get benefited out of it. So any of the research work people are doing, this is the perfect place to contribute to that, right? So your work will be archived there. So key frame point, we are not forgetting the current, we are looking at current landscape, and we're also looking into 5 and 10 years from now how things are going to look like. So 2022 edition was published 2022 April, right? And right now it is in Explore. So we managed to get everything. So if you go to Explore, you can get all the access to all the roadmap chapters. Otherwise, also you can get from the website. We are working on a 2023 edition, which will be published just before the Future Network World Forum, and that's happening in November. The way we have categorized, I know there are some of you have shown interest to try new working groups. So when we initially started this, we had only 6 working groups. Then we got 9, then we got 15, then we merged millimeter wave and hardware. So now that we have 9 societies, there are talking about quantum communication and convergence working groups. We are going to add 2 more groups. And people have new suggestions, they can add new groups, right? So this is a good place to get people from around the world work on an interesting topic that needs attention today, right? Because, so just wanted to give you an idea how these have been categorized. Then I briefly go over some of those. So this is the 14 working groups. You can get access like application service. We have AI ML working group, connecting the unconnected, deployment. There are different deployment challenges around the world, right? We are looking for more volunteers there to focus on India. So David Witkowski, who is the working group co-chair, I've been asking him to get people from India as well. So this is an important thing. If you're interested, please let me know. Edge service automation. We heard a lot about edge cloud, ultra low latency, right? What are the challenges there? We have to take a look. Energy efficiency, there are lot of stuff about green stuff, right? NextG Alliance, you might know, they have also similar roadmap. There is something called sustainability and green as well. So there is a lot of common function there. We're trying to collaborate as well. Massive MIMO, millimeter wave signal processing, optics, talking about converged networks. We have a pretty big group. They are looking into optics. Satellite, some of you know, Dr. Sastrikota and Giovanni, they have done a lot of work on satellite, and this satellite working group is very, very active. And right now, as you know, all know, NTN is getting so much attention. So they just not write only roadmap, they also have workshops. Security privacy, which is, I'm very much involved. I'm a co-chair for that with Iman Hamad. Standardization building blocks, this one gives you a chance to write the project authorization, like PAR. So Mehmet, Alex, they are the founding co-chairs, Reinhard, who is the third one. Systems optimization, that came later. I heard a lot, linear optimization, other things today. So as things start getting deployed, there are a lot of dependency. right? Just to make sure we have the right trade-off. So systems optimization working group actually looking into that. And testbed finally. So I always believe it is important to have a testbed where you can make sure things work before you deploy. So that is some sort of a best current practice you have to have, right? So Ivan Sesker, Mohammed, and Ivan Sesker from WinLab, some of you might know, they are the working group co-chairs. I know many of people, Pratik, you are over there. You're a member of testbed working group. So they meet actually twice a month, and they had a survey of all the testbed available around the world. So if you want to do millimeter wave type experiment, so you can go and look at the glossary, which testbeds are out there. In fact, the innovation testbed is a separate project, but it actually came out of that, right, in a way. So these are some very important, and people who are doing PhD or trying to do research, you can get some good food for thoughts there. All right, so this, I need to get into, so I'll just briefly go over that, and these slides will be available because if I go over each of these, will be taking 1 hour. So this is the application services working group. So their job, they're looking into different types of ecosystem. In this case, right now, there are 8 ecosystems, which are over here, like healthcare, agriculture, education, public safety. So if you want to apply 5G and beyond technology to take care of the pain points that these pillars have, verticals have, they talk about that. The whole interaction between the KPI and underlying architecture, right? So this is, they have about like 120, 130 page document. It talks about Narendra Mangra is one of the working group co-chair. Over there, if you want to participate, you can go and send mail to that, it'll be added. Connecting the unconnected, I already talked about it. So the whole idea we started 3 years back to take care of the digital divide. So the first year, we had about 259 submissions from 70 countries. Second year, we got about 250 for some 46, 7 countries. We have a challenge, we have a summit. So we invite the proposals from around the world, proof of concept, in 3 different categories: technical innovation, business development, and community enablement. And we go through rigorous process. Finally, we award about 11 to 15 prizes. Then we have a summit. We invite like folks like Green Sir, father of the internet. He's actually involved in this as well as an industry advisory. So the challenge part for the 3rd edition has been completed. We got about 296 submissions. We're in the process of selecting. Some of you are probably judges as well. And if you want to get involved here more, it'll be very nice. This also has attracted many foundations, like Lemonson Foundation, for example. They are giving us money. They said, you know, we are interested to get something implemented in India. So they gave us some money for planning grant. We hired a consultant, Ritush Bastav, and he's going to work with local IEEE staff and volunteers to make sure where specific places where they're connecting the unconnected can, you know, we can implement some projects. We are talking to USAID, many other people. They are trying to see Africa and different parts of the world, right, where things are not there. And interestingly, there are some prize winners from India also, last 3 years. So this is a very novel idea. So Sudhir and I, with help of many other volunteers and wonderful staff, Brad, Craig, Biraj, Sarah Gowal, right? We have been doing a lot of work there. Security, I'll talk a little bit more about it. So I'll probably skip this slide. So the whole idea is to look at the ecosystem. I know there is a physical layer security. We have a new white paper being written for physical layer security. But we look at the whole ecosystem in terms of end-to-end. What are the different enablers like AI/ML, slicing, software-defined networking, orchestration? So these are the different enablers that help to provide the features that we need for 5G, right, or 6G. But there have lots of challenges, opportunities. So opportunities and challenges. I'll talk a little bit more about that when I get to my security stuff. This is the satellite working group that I was telling. You know, you can read from the slides, but they're looking at different architecture, LEO, MEO, you know, CubeSats. They're looking to see how virtualization, software-defined networking can be implemented, different architectural solutions, the problems, security problems, even using satellite as a user endpoint instead of just bent pipe, right? So there's a lot of interesting stuff happening there. If you see every slide, I have a email address there. So, and these slides will be available. So if you are interested, you can take a look. Masim Maimo, this is also a very active working group led by Chris and Weber. If you're interested in this specific area, you can again participate there. Millimeter wave signal processing, some team Lee. So we had a hardware roadmap. We kind of merged it. And this is a good place if you're talking about terahertz and other new area related to frequency. It could be a good place to get involved. Energy efficiency. This is also very important and active group. Brian is one of the co-chairs and Tim Pace, they are the co-chairs for this energy efficiency working group. So as you can see, I think there are a lot of interesting talks there, right? You have to see where the energy goes. So the areas of interest, network efficiency, small cell migration, base station power, economic factors, right? So these are all different things that affect the energy and how do you make the thing green, right? So this kind of contributing to the green side of that. Optics working group. So as I said, we are not limited only to the wireless. So, you know, the areas of interest are data centers, optical switching, Wi-Fi, XOL. You know, this is again 2022 edition. We are revising it to 2023. So if you're interested, you can actually join that optics working group. Edge services. So this is Prakash Sujata and TK Lal. Initially, it was 5 years back. I think we started this. So they used to be called edge automation. That's why we call formally edge automation. Now it's edge services working group. So this looks into the placement of the edge cloud, the scalability, all the trade-offs, depending on the what kind of latency you use. I think there are some interesting talks there. So you will get to see lots of those in this working group. Systems optimization, this is one of the newest one. So we're looking at the deployment challenges, dependency, you know, things like the service variance, right? The traffic variance, control variance, things like putting the loop. Should I put the loop in the RAN, the automation loop, or should I in the core, what part, right? So depending on the type of service, type of traffic, how do I define that, right? We wrote a nice paper in the Standards Communication magazine. They have multiple workshop. Lyndon and Miriam, they are the co-chairs for that. Testbed working group, I talked about it. This is just a one sample table there. But if you look at the working group roadmap, you have lots of matrices. What is happening in 3 or 5 year 10? What are the actual challenges? You get to see that. So there's the test bed. I think this is probably the last one, deployment. So if you see here, local government factors, legislative, regulatory, engineering factors, public, community, resident factors. So there are a lot of even the environmental factors, right? So that impede the deployment of 5G. It has impeded, right? I personally, I had one time I had United States State Department, they sent me to Europe, talk about 5G security, and they also have a lot of question about this environment, right? You know, when I talk about security, you have to know where is the RAN core. You know, they say, well, my core is protected. I don't worry about RAN, but you know, that's not the case, right? So this is where we have I have a call for, I think, people around the world also watching. If you're interested to talk about your deployment issues in your area, please get in touch with David Witkowski or send mail to that mailing list. AI/ML, I know there are a lot of talks about AI/ML. This is also one of the newest working group. And we are Deepak Kataria, Bo and Anwar Wali, they're the working group co-chairs. So network automation, slicing, digital twin, security. So how AI/ML, you can take advantage of AI/ML at the same time you wheels up AI/ML, right? And there are different use cases. So that's a pretty interesting step too. All right, this is the last one. Probably standardization building, basically SBB. So what happens is when these working groups, they define the technology, right? And they have meetings with these folks. They also have a best current practice how to get the standards. For example, I talked about CTU. Sandeep, you're here somewhere, right? Was here. Oh, yeah, he's here. So Sandeep, so the CTU, when we got this 200 or so submissions, we try to find out how many of those can be standardized. So we saw potential 50 of those, right? So we are in the process of setting up a RRSA, the Rapid Reactive Standards Activity, invite them and pick maybe 4, 5, or 6 and set them pairs. So they will be on their own running with that, and maybe 3 years after that, it may be standardized, right? So that's how the Frugal 5G started, right? Abhay Karandikar and group. And Pranav, you're probably involved in that, right? So this is a great opportunity where if the idea is good, IEEE gives a chance. You can be a student, you can be a professor, it doesn't matter, right? You don't have to pay any fee. So that provides the intellectual idea to actual implementation. So SBB does that. So we talk to them, like right now, Masi Maimo, they have a PAR. Security, we are going to have a PAR on that. CTU, Sandeep is working on that. So I think that's a very important aspect of standards. We work with Standards Association. So if you want to see, these are again available. This year, we actually, Brad Kloja, who is a program director, worked really hard to make sure these INGR roadmaps are available in Explore, right? So if you look for it, access to Explore, you can get that. You can also get to see them in the website. Okay, so right now, and this is the, anyway, so this is just a commercial, and this is, these are the different email address. I think some of the working group members, chairs have not been updated here, but the point is, while we have the existing working groups, we're trying to add maybe 2 more, quantum communication and convergence. We also have a chance to add anything new that you think is not being done. Maybe 6G, some of the 6G stuff which are not here can be added, right? Okay, so I'll finish up maybe next 10 to 15 minutes. So, oh yeah, so the other thing I want to give an idea about, Pamela, is that you? Pamela is here. No, this is one of the virtual World Forum we had, supposed to be in Bangalore, right? So I want to give this is one of our premier conference. If you see, we started in 2018, and Pamela, you were there. 2019 in Dresden with 5G labs. Then virtual event, it's supposed to be in Bangalore. We had to do a virtual. Then fourth and fifth ended up being virtual because Montreal, this was hybrid, this was virtual, and sixth one we are doing in Baltimore. Right, so this is a call per paper proposals. It just got extended. The due date was July 21st. Right now it's September 8th, I think. So if you have, you want to submit paper, submit tutorial, submit any topical vertical, like you want to host a session with invited speakers, panels, we are all open, right? So please look at the website, and these are the 9 societies who are the financial sponsor. All right, so with that, okay, I think I'm running late. So this is a 5G 6G innovation testbed. My colleague Anwar, myself, we are the volunteer leaders, and with Brad Kloja and Joss, who are the IEEE staff and consultant. So what is the idea? So idea is, these are some of the founding members, when we initially letter of intent and things like that. So we are in the process of getting more members. In fact, you'll see later on. So the idea is, if you create a virtual testbed end-to-end, you can do a lot of things. You have the specification testing, you can do any experiment, you can collaborate anybody to create some kind of your own proof of concept to take care of some specific use case, let's say Department of Homeland Security or whoever, right? They have different need. So if you understand the pain points and you get an operator, let's say Nokia, Ericsson, any vendor, right? Or in startup or university academics, they can get together and just do it. You can use it for class, right? So operators, vendors, application providers, and academics. So academics, we already started. For example, my university, Johns Hopkins, we have already logged in. Hopefully in September, I can teach my students using this IEEE testbed. So operators, vendors, application developers, we are doing it in phase-wise. I know Tech Mahindra folks are here. They have been helping us every week. We're having Scrum meetings, and we're in the process of getting phase 3 right now. We are collaborating with ONF, OpenAI. I met also Linux Foundation. I think some of you, I met you here, that VP also. So whole idea is to create an open source testbed without getting glued into any proprietary systems. But at the same time, if somebody wants to donate or contribute, right, they can get their own stuff. You can have your own customized branch. Right now, we have several use cases people can support: mission critical, massive IoT, mobile broadband, fixed broadband, right? So these are the kind of small, low-hanging use cases people can actually support. We had few events like Austin 5G event, ICC, Globecom. We are going into PIMRC. So and then plan is to really not to have an isolated testbed. We have a federated testbed, right? So let's say we don't have Open RAN. We can connect Open RAN being built in Montreal, for example. So we can have different parts of the testbed, different places, and you can connect them, right? And maybe one testbed we can connect to the testbed that's being built in India, for example, right? So that way you can have different roaming partners and things like that. So that is the idea going forward. So right now, in addition to those founding members, we are in talks with, as I said, or an alliance, a lot of folks there, ITU with the Federated Testbed Addiction, Telefonica, just to name a few. But this is taking a lot of interest from around the world because traditionally IEEE has been more like journal, conference, things like that. This will be more like a tangible thing because I think we all have to make sure things work. Anyways, if you have any question, please let me know. We can go on that. How much time I have? I want to talk a little bit technical. 10, 15 minutes, can I do that? 10 minutes? Okay, I'll be quick. I just wanted to see, some of you might have heard my talk, but I wanted to say a little bit about security, otherwise I won't feel good. So when I said, close to my heart, by the way. So security, when you talk about security, every generation has new challenges. You have opportunity too, right? So when we looked at 5G, you said, okay, there are some opportunity that you can take advantage of. There are also challenges, right? So I'll just very briefly go over some of those and I'll finish it up. So, and this is only on the network side. I'm not talking about device, right? So you all know that this is standalone, right? As you see, this is 5G network. You have these network functions, all those, these are all standalone architecture. So when we have to look at the security issues, we need to know where the attacks are coming from, what kind of protocols they're using, what kind of security protection they have, 3GPP as defined, but that may not be enough. So there may be any additional security risk that we have to think about and look at the risk, look at the mitigation technique, right? Do I have the right security control, right? Things like that. So I'll provide a organized way of looking at the security threats because I used to work in chief security office. That kind of trained me a little bit like that. So if you look at this, this is like the very high level picture, right? You have an end device, you have RAN, edge cloud, you have user plane, control plane, all those IMS roaming providers. But if I try to superimpose the type of attacks, denial of service, mobile endpoints, attacks on the radio interface, attacks from physical access G node B, man in the middle attack, child channel attacks with virtualization, attacks from the non-3GPP network like Wi-Fi, right? A lot of handing over between Wi-Fi and 3GPP. Insider attacks, modification, data leakage, API-based attacks. Nowadays, people have been using API, STTP, GTP, all those, right? The whole diameter is gone, right? So they have a lot of attacks. Attacks from the internet network side. Then roaming network, right? So because if you're roaming and SS7 had a lot of problems there, right? And people got rid of diameter now, so that has. So once you take a look at this threat taxonomy, then you'll see where the attacks might come. So this is an example of, I turn my endpoint on, I register with the network, right? So during the registration process, a lot of things might happen. Somebody may jam, somebody may just take my IMSI and impersonate me, a lot of things. And a lot of things that happens in the core, which are STTP, API, service-based architecture, right? So I'm just giving some example of points of attack that could happen. And do I have enough control point for that? So this is on the control plane. So once you're connected, then you have to start sending data, right? You should have the PDU context, and then you send the data through GTP user tunnel. So that point, GTP user tunnel has a lot of security risk. So how do I take care of that? This is just an example of what functions are involved, what protocol is involved, which interface is involved, right? Okay, so now, so that's a very high level view. But so what I said, these are the different pillars. Now each of them are each of them is an enabler, a feature, right, which 4G didn't have, 5G has, maybe 6G is going to use many of these anyway. And now each of them provides the benefits, but they also have challenges. So 3GPP is in the process of doing that, but they provide the basic security architecture, SA3, right? Like 33501, 502, those, but in addition, top of that, there are additional security risks for each of these we have to worry about, right? And then what you do, I'll finish in maybe 5-6 minutes. When you look at the end-to-end system, we have a radio access network, you have a core, you have an application, right? So what I am showing here, we go with a standard way of looking at it. So my first two columns are remaining same. So this is like the CIA, they call it 101, right? Confidentiality, integrity, availability. And if I'm a hacker, how I can do that? I mean, this is the process I do it, right? And then for each of these, you have to look at the mitigation technique. This is from the RAN side, right? Similarly on the core, so RAN then core. So core uses different protocols and different network functions, right? They're all service-based architecture. So first two columns still remain same, but the attacker use different ways because there are different protocols to attack. Like you can overwhelm the AMF, you can overwhelm UPF by sending lots of data. So for each of these, you need to have some kind of tools. We heard the talk from Keysight, for example. They have pretty nice monitoring tool. I have used personally in AT&T, now I'm using it to look at let's say you're setting up an IMS call, like SIP and RPH value might get changed. So that's on the core side. So this is on the IMS side. If you're doing voice over IP, like voice over LTE, voice over NR, so you're using such an initiation protocol, RTP, so there are potential risks to that. Somebody might, you're getting a voice over IP call, I think it's coming from my mom, but maybe the hacker is actually calling me, right? So they can change the parameters, SIP headers and everything. My priority service, resource priority header might get changed. The mission critical users, fast responders, they're using resource priority header to get the right quality of service. Somebody might change the RPH. So instead of getting right quality of service, they may not get that. All right, then what you do, so that's like a taxonomy, break it up. Then you see, we call it measures of cybersecurity, like denial of service, degradation of service, data manipulation, data exfiltration, pivoting, right? So these are different ways my cybersecurity measure might be compromised because I need to make sure I have enough security controls in the place to take care of that. The other thing is then you have to look at the risk. So risk is the function of likelihood and impact, right? So what is the likelihood of this attack? What is the impact it's going to have on the, what kind of business impact, whatever impact, right? So then you can determine the risk. So what we did, I'll just go through it briefly. Just see the first is the STTP because they're going to be using STTP. And this is from the CVE threat category. What is the attack? How it affects the users? What kind of threat it is? It is degradation, pivoting, manipulation, data exfiltration, right? Then you do the risk severity. This way, do I have to spend more money if something is red? I really want to turn it to green. I may not have enough security controls. I have to spend a lot of money to get it done, right? And then you see the mitigation technique. GTP on the user plane, right? As I said, if you send your traffic, it goes through GPRS tunneling protocol. So GTP has a lot of vulnerability. What if GTP is hacked? All your data gets exposed, right? So your threat category, attack description, how it affects the users, threat types, risk severity, and potential mitigation technique. API, nowadays REST API, JSON, there's a talk about SDN controller, right? Northbound, southbound API. So those APIs may be attacked, right? In that case, API parameters may get changed. So these are type of API attacks, then how it affects the users, the mitigation technique. This is 2 up to the more continuation to that. So I talked about control plane, data plane. Then this is an opportunity. I'll spend maybe 30 seconds, maybe 1 minute, just to give you an idea. So what happens is this is a standard. We all talked about SDN, orchestration, automation. These are all good stuff, right? And I'm trying to put them in one slide here. And this is could be 4G, 5G network, doesn't matter. So I may have attack on the control plane or data plane, right? And the UPF or MF. So I have some kind of a data analytics that detects. Then I send the alerts, either malware attack, denial of service attack. And then I have the platform orchestrator, security orchestrator. I have the SDN controller using Southbound API. Either dynamically institute this DDoS, IDS, IPS, or change the rules based on what kind of attack and where it is going. So thing I was showing here is a closed loop automation orchestration to detect the attack. And now talking about AIML, this is reactive, right? If you apply AIML type technique, you can predict the attack is going to happen, right? So you prevent the attack altogether. So that is one application of AIML. But there are challenges, right? Your SDN controller may be attacked. I mean, I personally in AT&T have tried it, ODL and others, right? In the lab, a lot of fun cracking it, right? So you have XML attack, or you see the southbound attack, the whole SDN controller may get completely overwhelmed. So what you do there in that situation, you see if I have an SDN controller, these are the potential opportunities that I can take advantage of. Enhance programmability. How can I change rules on the fly? But there are potential attacks, as I can see here, and how it's affecting the users, the type of attack, risk severity, and mitigation, right? So that is SDN controller. ORAN, right? There was lots of talk on ORAN, and next August 9th, you're going to hear from Scott. Maybe he'll tell more about it. So the whole idea, you're exposing a lot of interfaces. It's giving scalability, flexibility, but they all may be exposed to attacks, right? So these are all the opportunities, right? But since you are exposing the interfaces, opening up, so that might have denial of service attack during orchestration, types of attack, risk severity. This is similar structure, right? Mobile edge cloud. Why do you need mobile edge cloud? Because to provide ultra low latency, right? So that means at the same time you want to keep it secure. So a lot of times, a lot of security keys might get stored in the edge cloud. So if you're handing over quickly, you want low latency handover. You don't want to go all the way to core to get authenticated, right? So you do it at the edge. So that is a potentially you are getting a low latency, but you're also exposing the vulnerability. So we did a little bit of, potential attack risk and effect on users. If you see, these are some of the attacks, how the users might get affected, what kind of attack, risk severity, right? So this is, and the mitigation. So for each of those, you can figure that out. Network slicing, there are a lot of interesting talks on slicing too. So as we know, slicing is a cool thing, right? I mean, there are many applications of slicing, even from the green slicing, right? That Abhay's talk. So here I'm showing while you take advantage of the slicing, because you're using same UE might be connected to multiple slices, right? Or because the same physical device is being used by multiple slices with different security properties, right? So that might give rise to problems. So here you see that these are the opportunities, and we heard about 5 or 6 talks about network slicing. But side channel attack, one UE is connected to multiple slices, one slice starving another slice of resources, and what kind of attacks those are, and potential mitigation technique, right? Open source API security, I know people have started using open source. We have to just keep in mind, this whole landscape of different types of open source out there, right? For SDN controller, for your core, right? In fact, IEEE we are using Open5GS for that. So we have to keep in mind there are lots of advantages, disadvantages too. Supply chain, this is a very, very important thing. Many people are working on it. So as you can see in the 5G or 6G system, starting from your IC, RAN, core, everything, right? And this is a little bit old chart. There are many vendors in the world they provide. So we need to have some kind of best current practice to make sure they have something that could be tested. There may be some standards. So this is just one of the example of CSIS. They have this political governance criteria, business practice, cybersecurity. So I think every organization need to have some kind of an agreement with the vendors they're buying from. Talking about open, I know many of our maybe students, just like in IEEE, we are building an open source testbed. People in the university, they may not have enough budget, right? Or community college, they still want their students to get involved. So they can easily build the 5G testbed based of open source. I was talking to Open Network Foundation folks, Larry Peterson the other day, Open Air guys, right? So you have all these things available. If you want to build a testbed yourself in your lab, you can just use your students. They learn and they can build, right? You just have to guide. And there are TSDSI, there are other regional standards bodies, they are already contributing. So I just want to see set of things that you know. One more thing talking about testbed, I wanted to tell you, NSF has built something called POWER, Platform for Advanced Wireless Research, and they got like four of those in the Coliseum. The reason I'm telling is when you do something, let's have a customer comes in or a sponsor, right? They want to see, I'll give you an example of that. Well, I have so many 10 different pen points with 4G or 5G. Now I have to go to 6G. Why should you go to 6G? Let's see what kind of pen points you have. Can 5G take care of it? So we are a member of NSF Power. What we do at APL, we have our own test bed. We do a proof of concept. Then we go to New York City to do the millimeter wave experiment, or go to Salt Lake City to do massive MIMO test. They have a recent one, rural wireless broadband in ARA, right? Or drone-based stuff in Airpoint, North Carolina State University. So this is a good way to get involved in many of the test bed. You know, this is just an example of Columbia University in New York City, Salt Lake City, right? So this is an example I'll give you. We worked with the Department of Homeland Security. I personally worked on it. Talking about pen points and mapping, but at the end of the day, you have to see how this technology can be useful, right? Just developing a technology is one thing. Second thing is how the user population can use it, right? So I'll show you this example. So what they had with the 4G network, they had a drill for active shooter. This is one of the scenario they had. And they had so many different problems, packets dropping, congestion, all these things, right? Then they came back to say, do you think 5G can help us here? So we tried to do a mapping, right? So there's a gap analysis. So these are the different problems they had on 4G network. And these are the 5G enablers like Edge Cloud, SDN, NFV, new radio. So we try to map. We say, okay, you have a congestion. Let's use SDN, NFV to automatically control it. Or if you have ultra low latency problem, let's use Edge Cloud. So what we did the paper analysis. Then we actually went and built the actual test bed here. So in this case, we tried to emulate lots of traffic. Bandwidth went up. Then with this closed loop automation with on-up orchestration, and try to scale up the network, like control plane, user plane, right? So when there's a congestion, dynamically you can scale up the network. The congestion subsides, we bring it down. So 1 MF, 2, maybe we have 10 MF, and then bring down, right? So this is a good way to scale up, scale down the scalability. We also did ultra low latency. It was taking 10-second delay for the video distribution. So when we saw that, we said we dynamically instantiated the local UPF, user plane function, and there it came down to 5 milliseconds, right? And then we did the same for slicing, for example, because every fast responder have different kind of quality of service. The point I'm making here is while we develop standards, write papers and everything, we need to make sure it gets used before it gets deployed. And if something doesn't work, you go back to standards and fix it, right? So that's the whole thing. All right, so I'm last but one slide. Something got messed up here. So the key points of 5G adoption uses, technical barriers, a spectrum issue, complexity, cultural barriers, policy barriers, spectrum, right? I think we kind of touched most of it today, maybe not the environmental issues, but so these are the kind of things we have to worry about as a community. You may be the professional in the university doing research, postdoc, or startup. We all have to kind of work together to get this done. Supply chain issues. This is something interesting, maybe the spectrum side. Okay, all right, last slide. So I try to give a little bit idea about the INGR, how we can get involved. A lot of opportunity there now in a technical community. We are bigger, people know us better than they knew before. And then the 5G, 6G innovation testbed, this is a completely brand new project. I think a lot of things can be done there. If you are interested, let me know, let Brad or Anwar know, and we can, put you on board. I don't know, Tech Mahindra people, are you guys here yet? Oh, here. So they're here. I like to thank them again. I've been thanking you for 3-4 times, but now that you're here, and so I'd like to thank you in person because they have done a great job getting it off the ground. I really appreciate the team and their leadership, including the CEO as well. And it's still going on, by the way, right? We have, you're coming to New Jersey, right? Okay. All right. So anyway, so now on the summary slide, what I was telling you on the security side, as you can see, if there is a new evolution of the network, there are new security challenges, there are opportunities. So while we take advantage of the opportunities, we also have to look closely, open it up, do the threat taxonomy and try to find the solution, right? And then you build the test bed, investigate the gaps. If there is a problem, augment the security controls. And finally, the collaboration among operators, vendor is important. Standards, testbed, proof of concept are catalysts, right? So this will help us to advance 5G and maybe possibly move into 6G very soon. So with that, sorry, I know I took a lot of time, but I wanted to convey my message. Now I feel good. I came to Bangalore. At least I was able to talk to you in person. And people who are in the watching me remotely, at least I'm standing today and talking instead of sitting on my desk. But thank you very much again for giving me the opportunity.
Thank you, Dr. Ashutosh. So we'll just conclude this session. So Anindya, can we have the...
Done? I'm done, right?
You're done, right?
Okay. Thank you.
We'll just give the memento and to all.
Do I need a memento? I'm one of you guys. Yeah. Just go for a coffee or something.
Yeah. We are waiting for you.
Yeah, I like to really, this should be given to all the leadership team here. Thank you.
Yeah, Anindya, for Anand and Rashmi and Balaji is on maybe by electronics way. You can take it? Okay. Okay, so the last, we'll close this session. Thank you for all of it and a vote of thanks from Subhash.
Good evening. Yeah. Okay, so we started very early in the morning. I still see the room is almost full. So thank you. Thank you for staying back and making it really, really eventful. So I think this is our first workshop from ComSoc Bangalore on the 6G initiatives. So it's really great to see and spectacular attendance online and offline. So thank you, all of you. So let me start by thanking the sponsors. We have AMD as a sponsor and Shankya Labs. So, sorry, Tejas Network. I'm sorry. Tejas Network for sponsoring us. And I would also like to thank IISC for hosting the event and arranging the good foods, all logistics. I would like to thank all the speakers for enlightening us today. I think 6G is something that we still are imagining how it is going to be. Though the last month there has been a definition by IT on IMT 2030, but there is a lot of work that is happening. Some of the keynote speakers talked about the expectation from 6G. It was clear that 5G is going to be a stepping stone towards 6G. And Dr. Kumar said it without mincing word. 5G has not really delivered what it was supposed to. And 6G now is on a tighter spot to say, now we are setting the expectation for 6G, don't disappoint us, right? So that's essentially how the expectation has been set. Dr. Chandra covered a lot of ground in terms of the research directions. Probably the initial enablers to fulfill what is expected in 6G. So I would like to thank all the speakers, a great spectrum of technology. And I would like to thank all the audience, but last but not the least, the organizing committee behind the scene, amazing amount of work, all ComSoc Execom members, the student volunteers, and I would like to thank Ashutosh and all the technical collaborators, Signal Processing Society, Professor Hari was here, then INGR, Future Networks, and uh, yeah, the 5G, 6G test bed. So a great coming together. And before I conclude my vote of thanks, I also would like to invite all of you to be really, really active in furthering the technology towards 6G. IEEE is a great community, and I am sure most of you are the members. Those of you who are not, please do come join us. But member or otherwise, come together, work towards the technology to further the technical advances for the greater good of the humankind. So thank you, everybody.
We would like to have a group photograph. So before you pack up, if you can come here. Yeah, yeah. Please. Please come join us. Two row here, two row here.